Hello friends, welcome to our channel. In today's session, we will learn a few basic concepts of network security. So as we know, the network is a collection of computers, and nowadays everything is performing on internet. So it is necessary to provide the security for the data which is transformed between the systems. So here the network security, the main concept of network security means we have to provide the security for the data over a network. So providing security for the data over a network. So in this regard, let us know a few basic terminologies which are used in this network security. The first one is plain text. So the name itself indicates is a normal text which can be read by the user. That means this plain text is in a readable format. Next one is ciphertext, the quite opposite to the plain text. That means this ciphertext is a non-readable format. So the user have to convert this plain text to the ciphertext. So that is one way to provide the security for the data. So plain text is a readable format, ciphertext is a non-readable format. And the process of converting this plain text to ciphertext is called encryption. It is a process of converting plain text to ciphertext. So plain text to ciphertext, readable to non-readable. And at the receiver side, the receiver has to perform the reverse process. So that means he have to convert the ciphertext into the plain text in order to understand the message. So that process we call it as decryption. So decryption is a process of converting ciphertext to plain text. So generally this encryption process will be done on sender side, and this decryption process will be done on receiver side. So the sender will take the plain text as input, he will convert the plain text to ciphertext, and this ciphertext will be transferred to the receiver. So the receiver will receive the ciphertext, he will again convert this ciphertext to plain text so that he can understand the message sent by the sender. And the study of encryption is called cryptography. So this cryptography is the study of encryption. And study of decryption is cryptanalysis. Cryptanalysis. So this is a study of decryption. So the study of sender side encryption is called cryptography. The study of decryption is called cryptanalysis. So both are combined and we call it as cryptology. That means both the study of encryption and decryption. That means that both the cryptography and cryptanalysis, we call it as cryptology. And now the next term is key. So the key is also a group of bits which has a major role in the process of encryption and decryption. So whatever the algorithm we have taken for performing this encryption, we require a key. So a key is also a group of bits, but this plays a major role in the encryption and decryption processes. Now, this encryption can be done in two ways. One is stream cipher. That means here we have to the process of conversion of plain text to ciphertext is done bit by bit. So the conversion takes place bit by bit. So it will consider the first bit. So the first bit will be get converted into ciphertext, and then the second bit will be considered, and again it is converted into the ciphertext, and then followed by the third bit and followed by the fourth, and likewise. So the conversion takes place bit by bit. That is called a stream cipher. So basically this is valid only for the short length messages. So it will fail for long messages. And the second type is block cipher. Block cipher. So as the name indicates, a block is nothing but a grouping of bits. A group of bits, we call it as blocks. Block. So there is a size for each block that depends upon the algorithm. So here the process of conversion will be done block by block. So first the entire plain text message is divided into different blocks, depends upon the block size, and then each block will be converted to the ciphertext. So the first block is processed and the plain text is converted to the ciphertext, and then second block will be considered and the plain text of the second block will be again converted to the ciphertext. Likewise, it will process all the blocks. So stream cipher, the process is bit by bit. Block cipher, the process will be block by block. And this encryption can be done in two mechanisms. One is symmetric encryption, another one is asymmetric encryption. Symmetric encryption and asymmetric encryption. So here the symmetric encryption means here we have to consider a key. This is the same key will be used for both the encryption process as well as decryption process. So whatever the key we are using for the encryption, the same key must be used in the decryption itself. So same key will be used for both the encryption and decryption process. So that key may be a single key or a group of keys. So it doesn't matter. So what are the keys we are using for encryption? The same keys must be used for the decryption. So that is the process of symmetric encryption. Here this key is called secret key. And it is denoted by KS, secret key. Here asymmetric encryption, here there will be two different keys, two independent keys. and these two independent keys forms a pair, so it is called a pair of keys. One is public key, another one is private key. So every user will be having this pair of keys. So every user having this pair of keys. So every user will be having public key and private key. And here, if one key is used in encryption, the another key of the same pair must be used in decryption process. So here we are using the same key for encryption and decryption. Here we are using two different keys for encryption and decryption. So here one key, if you used in encryption process, second key will be used in decryption process. The only condition is these two must form a pair. That means if the public key is used for the encryption, we have to use the private key of the same pair in the decryption process. For example, if user A is there, so A is having both the public key, private key. So here the public key is denoted as KU, private key is denoted as KR. So if user A, the public key and private key are KUA and KRA. If the encryption process we are using KUA, in the decryption process we have to use the KRA. So other than this KRA, no other key will decrypt the data. And if the encryption process we are using KRA, that means private key of user A, automatically the decryption process we have to use the public key of user A. So these two must form a pair. So this process we call it as asymmetric encryption. So both the techniques are having different algorithms. So symmetric algorithms are there as well as asymmetric algorithms are there. So here in the symmetric, only single key is used. So it's not a single key. The same keys must be used for both the encryption and decryption. And whereas in asymmetric, two different keys will be used. One is for encryption, and another one is for decryption. But these two must form a pair. Next. Let us see a simple security mechanism. First, the sender will consider the plain text. So this is the plain text. He will apply the encryption process. So that we will get ciphertext. And this ciphertext must be transferred to the receiver through a secure channel. And here we will get the ciphertext. Again, so this ciphertext can't be understood by the receiver, so we have to perform the reverse process, that is decryption. So that after decryption we will get the plain text. So this is a normal security mechanism. First the plain text will be considered. So by applying this encryption, so here we use the key. That may be if we are using symmetric mechanism, the same key must be used in the decryption also. If we are using asymmetric algorithm, we can use one key here in the encryption and another key in decryption. So if we use the symmetric, we use KS, and here also the same KS. So this is symmetric. If it is asymmetric, if we use here KUA, here we have to use KRA. If we use here KRA, here we have to use KUA. So any one case, but these two keys must form a pair. So the plain text will be converted into ciphertext. That process we call it as encryption by means of key, either secret key or a public key, private key, so that we can get the ciphertext. And this ciphertext must be transferred to the receiver through a secure channel, and the receiver will receive the ciphertext, so which cannot be understood by him. So again the reverse process should be performed. That means the decryption process will be performed. If it is a symmetric key, the same key which we use in the encryption, the same key must be used in the decryption, or else private key or public key asymmetric. So after applying this decryption process, we will get the plain text so that it can be understood by the receiver. So this is a sender side, this is a receiver side. So this is a sender side and this is a receiver side. So this is the overall general security mechanism. So how the plain text is converted to the ciphertext, and the ciphertext again converted to the plain text. Here we will use the encryption algorithms, different algorithms, either symmetric algorithms or asymmetric algorithms. So finally, in this session, we have learned the different concepts of network security. That is a plain text which is in a readable format, and the ciphertext which is in a non-readable format, and the encryption, the process of converting the plain text to ciphertext. So the decryption, the process of converting the ciphertext to plain text, and the cryptography, the complete study of encryption, cryptanalysis, the complete study of decryption, cryptology, the study of both encryption and decryption, and the block cipher. So this is a technique where the processing will be done in terms of blocks. So a group of the complete plain text will be grouped into different blocks, depends upon the block size. So at a time each block will be converted to the ciphertext. Stream cipher, here instead of using the blocks, bit by bit conversion will be done. So first it will consider the first bit. So the first plain text bit will be converted into ciphertext, and then followed by the second bit, followed by the third bit. And the key is also a group of bits, but it plays a major role in the process of encryption and decryption process. Secret key. So before going to these three, we have to know about the symmetric and asymmetric ciphers. So in the asymmetric cipher, so in both these cipher mechanisms, we will use the key. So the major difference is, in symmetric cipher, whatever the secret key we are using in the encryption, the same secret key must be used in the decryption process. So that's why we call it as one key encryption or a single key encryption technique. So the same secret key must be used for both the encryption and decryption. In the asymmetric cipher, we are having two different keys. One is public key and another one is private key. And these two keys form a pair. So if one key is used in encryption, the another key of the same pair must be used in the decryption process. So that means if the public key is used in encryption, the private key of same pair must be used in decryption process. Or if the private key is used in encryption, the public key of same pair must be used in decryption process. So that's why we call it as asymmetric cipher or two-key cryptography or a public key cryptography. So in this session, let us have a look on a network security concept, that is attacks. So in our network security or information security, an attack is gaining an access of data by unauthorized person. Unauthorized user. So gaining the access of data by unauthorized user, we call it as attack. Here the word gaining means accessing the data, modifying the data, destroying the data. So whatever it may be, accessing or modifying or destroying the data is called defining. An attack is gaining the access of data by unauthorized user. So this unauthorized user may directly access the data or modify data or destroy the data. Here there are two categories of attacks. One is passive attack, another one is active attack. These are of two types. One is passive attack and active attack. So here the passive attack means the data will not be modified, just the data will be accessed by the third person. The third person is unauthorized person. So here no modification will be done. And coming to this active attack, the name itself indicates it is an active attack. That means here the data will be modified by the unauthorized user. So here modification will be done. Data modification. So no data modification will be done, and here the data modification will be done. So the final impact will be more for this active attacks, because the data will be modified and that modified data will be received by the user. So if sender sends the message and receiver receives the message, the sender sends one message and the receiver receives another message which is modified by the unauthorized user. Those attacks we call it as active attacks. And passive attacks are no data modification will be done, just they will access the data. Coming to this active passive attack. Coming to this passive attack, there are two methods for this passive attacks, two techniques. One is release the content, releasing the content. That means this is the sender and this is the receiver. This is the third party, unauthorized access. This is the unauthorized access. So if the data is sent to the receiver, the third party will just access the data. That means by listening or using some other techniques, he or she will gain the data which is sent by the sender to the receiver. So here there will be no modification, just this third party will get an access of this data. These type of techniques we call it as eavesdropping. Eavesdropping technique. That means no modification will be done, just they will listen to the messages. So this is the release of content. Release of the content. So the content will be released, that means accessed by the third party, that is unauthorized access. So there will be no modification, just it is an eavesdropping technique. Just the third party will observe the messages and he or she will gain the access. That's it. Coming to the second category, traffic analysis. So here also the sender will send the message to the receiver and third party, that means unauthorized access, unauthorized user, just observes the traffic flow. And based upon this observation and based upon this traffic, third party or unauthorized person will access the data. So based upon the traffic between the sender and receiver, here the word traffic means data sent by the sender to the receiver. So keep on monitoring the traffic between sender and receiver, and the unauthorized person will access the data. So in this process also there will be no modification will be done on data. So that means it is also one type of eavesdropping technique. So these two comes under passive attacks. One is releasing of the content, and the second one is traffic analysis. In the releasing of the content, just the content will be accessed by the third party. So no modifications will be done. And here the traffic analysis, the third party will keeps on monitoring the traffic in between the sender and receiver. And based upon the traffic flow, the third party will gain the access. That means the third party will get the data. So here also no modifications will be done. So that is passive attacks. Coming to the next category, that is active attacks. So here active attacks, the modification will be done on the data by the unauthorized person. So if sender and receiver are the authorized persons, if sender sends the data from the if the sender sends the data to the receiver, so in between the transmission, the unauthorized person will gain the access and the person will modify the data in between the transmission. So such type of attacks we call it as active attacks. So these type of attacks, the impact factor will be high. So here there are mainly 4 processes. So 4 different categories in this active attacks, 4 types of attacks. So first one is masquerade attack. Masquerade attack. So in this masquerade attack, the sender will send the data to the receiver. So, but the receiver will receive the data from the third party on the name of sender. So this is the sender and this is the receiver, and this is the third party. Third party means unauthorized section. So this is the unauthorized person. So receiver will receive the message from the third party, with the name of sender. So sends the data in the name of sender. So the receiver don't know who will send the data, who is sending the data. Just the receiver will know that the data which was received was sent by the sender, but actually the data was sent by the third party. So the third party, that means unauthorized person, will send the data to the receiver with the name of sender. So this type of attack, we call it as masquerade attack. So here the data is modified because actually the sender doesn't send any data to the receiver, but the receiver was receiving the data with the name of a sender. So this type of attack we call it as a masquerade attack, and here the data modification is done. And the second one is replay attack. Replay attack. Here again there is a sender and receiver, and if the sender sends the message to the receiver and the same message will be gained by the unauthorized person, and the modification will be done and the same message will be sent to the receiver once again. So that means a replay. So now the receiver will receive the message twice. One is from the sender and one is from the unauthorized person. So receiver doesn't know which message is the correct message. That means which message is the perfect message. That means which message was sent by the actual sender, because this receiver receives two messages, the same messages twice. So one is from sender, another one is from third party, unauthorized. So sender sends the message to the receiver and the same message will be accessed by the unauthorized person, and once again the unauthorized person will send the same message to the receiver. So this type of attack we call it as replay. The name itself indicates replay. So again and again we are sending the same message to the receiver. So that means the receiver receives the same message number of times, and the receiver doesn't know which one is the correct message. So this here also the modification is done. And the third one, coming to the third one, data modification. Data modification. Here also the sender sends the data but it doesn't go to the receiver. That message will directly accessed by the third party, and modification will be done on that particular message, and again this message will be sent to the receiver. So the data which was sent by the sender will be received by the unauthorized person, and the data will be modified, and the modified data will be sent from the unauthorized person to the receiver. So all these messages will be within the name of sender. So whatever the message this unauthorized person sends to the receiver will be in the name of sender. So receiver doesn't know there is a modification on data during the transmission. So that's why we call it as an attack. So data modification attack. So here name itself indicates there is a data modification. So here the data is modified. And here the data is accessed. Right? And the last one is denial of service. Denial of service. Here so this third party will interrupt the services which are sent by the server to the sender. So it disrupts. So disrupts or interrupts the services sent by the server. So this will be also done on the name of sender. So the unauthorized person will interrupt the services which are sent by the server to the sender. And this will be done on the name of sender. So this is the fourth type of attack. So hope you understood these two categories of attacks. One is passive attack and another one is active attack. So in the passive attack, there will be no data modification, just only they will listen to the messages. Those concepts we call it as eavesdropping techniques. So then there will be no data modification. Coming to this active attack, there will be data modification, so the impact factor will be high for these active attacks. So in the passive attack there are two methods, two techniques. One is release of content and second one is traffic analysis. And coming to this active attacks, there are four techniques. One is masquerade attack, replay attack, and the third one is data modification, and fourth one is denial of service. In all these four techniques, the data will be modified. So the data will be modified by the unauthorized person. So what are the services provided by our network security? So here the question is, we are sending the message to the receiver, so that how secure the data will be sent to the receiver. So here A and B, A is a sender and B is a receiver. So A have to send a message to receiver B. So we have to provide the security for this data over the network while transmitting from the sender to receiver. So here there are different security services. So among that, first one is access control. So here the access control, the name itself indicates the access control means the access should be given to only the authorized persons. So we have to prevent the unauthorized access of resources. So that means prevent unauthorized access to resources. And the second service provided by our network security is authentication. Here the authentication means verifying the receiver or a sender. That means we have to verify the identity of a person who is sending the message or who is receiving the message. So we have to check their identity. So whether the message has been received by the correct person or whether the message has been sent by the correct person. So that means the user identity, verifying the user identity. Verification of user identity. And the third one, the third service is confidentiality. This is also very important. So here the confidentiality means providing security for the data which is transmitted from sender to receiver. So sender will send the message to the receiver, so that our duty is to provide the security for that data which is sent by the sender. So that we call it as a confidentiality. That means security. Providing security to the data sent through a network. Next one, integrity, the data integrity. So we can refer it as data authentication or simply authentication. Here data confidentiality and data integrity, anything is right? So the next one is integrity. So by providing the security for the data which has been sent from sender to receiver is not the final thing. So one more thing we have to take care is there should be no modification done during the transmission from the sender to receiver. So that service we call it as integrity. So we have to take care that, so after sending the message from the sender, the unauthorized person should not modify the message during the transmission of the data from sender to the receiver. So this is, no modification should be done. No modification should be done during the transmission. During the transmission. So after sending the data and before receiving the data, there should be no modification done on the data. That service we call it as integrity. So first one is access control. So we have to prevent the unauthorized access of resources. And then next one is authentication. So before communicating the receiver or a sender, we have to verify the identity of sender and receiver. So after verification of sender and receiver identity, then the actual communication should be started. Then the next is confidentiality. So after authentication is completed, we have to send the data from sender to receiver. So we have to provide the security for that particular data which has been sent from the sender to receiver. Next, after sending the data from the sender and before receiving the data by the receiver, we have to take care about no modification should be done on the data during the transmission. That we call it as integrity. And the last one is non-repudiation. So here non-repudiation means preventing from the denial of service attacks. So as we have discussed in the previous session, the denial of service attack means without the intervention of user, the server will terminate its services, or the server will stop its services to all the users. So in such type of attack, in order to prevent such type of denial of service attacks, we have to, that process we call it as non-repudiation. So preventing from denial of service attacks. So these are the 5 services provided by our network security. That means we have to provide all these 5 services while sending the data from the sender to the receiver. So first one, access control, authentication, confidentiality, integrity, and the non-repudiation. Now, so there is a slight variation between authorization and authentication. Now let us see the difference between authorization and authentication. So now let us see the difference of authorization and authentication. So this is a familiar question will be asked by the any of the staff members during the Viva or in our projects, final year projects. So first of all, we have to know the difference between authorization and authentication. So authorization means access permissions, whether the user is having the access permissions or not. That means what the user actually want to do. User wants to do. What the user wants to do. This is called authorization. And now authentication. So here the authentication means who is doing the actual work. Who is doing the actual work and what the user wants to do. What the user wants to do is the authorization, and who is doing is a authentication. So we can say a simple example. I had an ATM card, right? I had an ATM card of a bank, so ABC, the bank name is ABC. I am having some ATM card. So as I am having this ATM card, I am an authorized person. Authorized person to get the services, because I am having the ATM of particular bank. So I can use the service, I can utilize the services provided by the particular bank. And coming to this authentication, whenever you will go and insert this ATM in the ATM machine, it will prompt for a password or a PIN. So a PIN is authentication. So after you press the PIN, corresponding PIN, so the machine will check, it will compare the actual PIN with your ATM card. If it matches, then only you will be get access the services provided by the particular ATM. So here the PIN is called authentication. That means PIN verification. Simply we can say it as PIN verification is called authentication. So ATM card, having an ATM card is only an authorized one, and if you had a correct PIN of that particular ATM card, we can say it as authentication. So this is a slight difference between authorization and authentication. So here authorization means just verifying the user permissions. And authentication means verifying the user identity. So that means our login details, our Gmail login password, username and password, or YouTube username and passwords. So this is, we call it as authentication. So it will compare the, or it will verify the user identity. So hope you understood the difference between authorization and authentication. Now, today's session we have learned various security services, that is access control, the prevention of unauthorized access of resources, and then authentication, verifying the user identity, confidentiality, providing the security to the data which is sent from the sender to receiver, and integrity. So after sending the data from the sender and before receiving the data by the receiver, we have to take care that no modification should be done on the data during the transmission. And non-repudiation, that is in order to prevent from the denial of service attacks. Now let us have a look on a simple encryption techniques. So first of all, the encryption can be done in two ways, that is a symmetric encryption and asymmetric encryption, that we have discussed in the first session. So let me explain in a brief that in the symmetric encryption, whatever the key is used in the encryption, the same key must be used in the decryption also. That means we have to share the secret key in between the sender and receiver in a secure communication channel, so that both the sender and receiver will use the same key for encryption and decryption. So asymmetric means here there will be a pair of keys, that means every user will be having two keys, one is a public key and another one is a private key. So as the name indicates, the public key is a public to all the users in the network, and the private key will not be shared between the different members. So it will be only with the receiver or a sender. So that if one key is used in the encryption, the other key of same pair should be used in the decryption. That we call it as asymmetric encryption. Now in this session, let us have a look on a simple symmetric encryption techniques. So this simple encryption, symmetric encryption techniques are also called as conventional encryption techniques. So here mainly there are two categories of techniques, a simple symmetric encryption techniques. The first one, substitution techniques. Another one, transposition techniques. So the name itself indicates the substitution techniques means we will replace the plain text characters with the ciphertext characters. So here the plain text will be in a characters and also the ciphertext will also be in a characters. And here the complete plain text characters will be replaced, that means substituted by the ciphertext characters. So in this there are mainly, we are going to discuss only two substitution techniques. Those are Caesar cipher and Playfair cipher. Playfair cipher, Caesar cipher and the Playfair cipher. So there are many more, that is monoalphabetic or a polyalphabetic or a Hill cipher. There are many more. So in this session we are going to discuss only two categories of these substitution techniques, that is Caesar cipher and the Playfair cipher. So the main drawback of these substitution techniques are these symmetric techniques are useful only for the short length messages. So these are very much vulnerable to the attack. That means it is very easy to be attacked by the cryptanalyst. So first let us start with the Caesar cipher. So before applying the Caesar cipher, so first of all let us give the numbering to the plain text alphabets. So here I am writing the alphabets A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y and Z. So let us start giving numbering from A to Z. So first let us give the numbering to the alphabets. So we can consider the starting number as a 0 or a 1. So that we have to mention. Here I am taking the first number as 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 and 26. So first I have given the numbers for the plain text characters. Let us consider these characters are the plain text characters. Here, in order to find the ciphertext, so we have to use one key, and as it is in symmetric encryption, the same key should be used in the decryption process also. So here the key is a numerical key which ranges from 1 less than 26. So 1 less than or equal to k less than or equal to 26. That means the k must be 1 to 26. Any number in between 1 to 26, including the numbers 1 and 26. So for finding the ciphertext is equal to plain text plus key mod 26. So this is the formula to find the cipher character. So here we have to consider each character and we have to apply this formula, and so that we will get the ciphertext character. Let it be example. Let the plain text be hello. So the key is some 4. So the ciphertext characters, first let us consider the H. So ciphertext character of H is equal to plain text. So H is having a number 8. So 8 plus key is 4. 4 mod 26. That means 12 mod 26, which is equal to 12. So ciphertext of H is a 12, which is equal to, what is the letter of 12? 4, L. So which is equal to L. So ciphertext of H is L. Now ciphertext of E is equal to, what's the number for E? 5. So 5 plus, what is the key here? 4 mod 26. So here we got 9 mod 26, which is equal to 9, which is equal to the character of 9 is I. So I. So for E the ciphertext character is I. And coming to this, the next one, the ciphertext character of L is equal to plain text. L is having a number 12 plus the key is 4 mod 26, that equal to 16 mod 26, which is equal to 16, which is equal to P. So the ciphertext character of L is P. Automatically the next character is also L, so it is P. Now ciphertext character of O is equal to, what is the number of O? 15. So 15 plus 4 mod 26. So here 19 mod 26, which is equal to 19. So what is the character of 19? Yes. So here the O, the ciphertext character of yes, O is yes. So given plain text is hello and the ciphertext is L I P P yes. So for the given plain text hello, with a key 4 we got the ciphertext L I P P S. So this is a simple technique of a scissor cipher. the conversion of the plain text to ciphertext. So the decryption is a reverse process. So we have to use a minus, ciphertext minus key. And here the use of mod 26 is if we got the plain text letter as Z. If our plain text, for example, let us take one more example so that you can clearly understood. If our plain text is, so here the plain text is zoo, Z-O-O, zoo. So we have to convert this zoo to the ciphertext. So plain text characters to the ciphertext. So here the key is same 4. Let us take the same 4. The ciphertext character of Z is equal to, what is the number of Z? 26. So 26 plus 4, key mod 26. So here it is 30 mod 26, which is equal to 4. 30 mod 26 is equal to 4. So the character of number 4 is D. So the D is the ciphertext character of a plain text character Z. Similarly, the ciphertext character of O is equal to, what is the number of O? 15. So 15 plus 4 mod 26, which is equal to 19. The letter of 19 is S. So the ciphertext character for the given plain text is D S S. So this is the ciphertext character for the given plain text. So for the repetition, we have to use the mod 26. Now let us see the calculation of mod 26. How to calculate the mod 26. So many of them will be get confused of using this modulo operator. So I will clarify your doubts, right? So if we use a mod operator, so because in our network security the mod operator is most important. So almost in every algorithm we will receive this mod operator. So we have to know the operation of mod. So here the mod operator will result the remainder of division. Remainder of division. So that means, so 5 mod 2. 5 mod 2 means that equal to remainder of 5 divided by 2. So 5 is divided into 2. 2 2s are 4 and the result is 1. So this is the remainder. So this will be the result for mod operator. So here 5 mod 2. So 5 divided by 2 and the remainder is 1. So 5 mod 2 is equal to 1. And the second case, 2 mod 5. What about the 2 mod 5? So here 2 is divided by 5, 0 times 0, 2, which is the remainder. So 2 mod 5 results 2. Here we can write in generalize A mod B is A if A less than B. So this we can remember. If A is less than B, then A mod B will be answer A. So by using this modulo operator, we have to perform the scissor cipher. So as it is a substitution technique, the plain text characters will be substituted with the ciphertext character. So this will be done by simply adding the value of plain text character to the given key, and the corresponding character of the result will be the ciphertext character. So the main drawback of this technique is only we are using the keys 26. So as I said that there is a brute force attack, that means checking each and every possibility will easily get the actual data. That means a plain text can be easily attacked because only we can apply only 26 possibilities in the brute force attack. So this is the main drawback, and this will be only suitable for short length messages. It cannot be implemented on long messages. So this is all about the scissor cipher. Next, moving on to the second one, that is play fair cipher. Playfair cipher. Playfair cipher. So here first we have to consider the key and we have to consider the 5 by 5 table. A table with a 5 by 5 columns. 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. So this is a 5 by 5 table. This is a 5 by 5 table. First we have to consider the plain text. Same we can take it as hello, and here the key is in a character, that means we can consider one word. So any word we can take it as. Let us take networks. Network is the key. It's a keyword. Next, we have to find the ciphertext. So what is the ciphertext for given plain text hello with the key network? So first fill the table, this 5 by 5 table, with the network. So write down every character in the table without any repetition. If you have any repeated letters, just you have to write only once. So ignore the repetitions. So write it down. N E T W O R K. So there are no repeated letters, so I have written the complete word in the table. Now fill the remaining boxes with all the alphabets which are not available in our key. First one, A, alphabet A. It is not available in our key, so I am writing A. Next, B. It is also not available, B. Next, C. C is also not available. D. D is not available. E is available. So don't write that E. We should not repeat the character in the table. F. It is not there. G. G is not there. H. It's not there. And I. Coming here. So as it is a 5 by 5 table, we will get only 25 letters. So one letter should be merged with another letter. Here in general we can merge I with J. So I and J letters can be merged into a single box. So here I or J. So I am merging both I and J into a single column. Next, K. As here it's L. M. N is there. O is there. P. Q. R is there. S. T is there. U. V. W is there. X. Y. And Z. So first step, we have to fill the key without any repetition. If our key is having any repeated letters, just ignore the repetition. Just write the unique letters. So we have to write all the 25 letters with one merged column, that is with I and J. Now we have to follow the 3 rules. The following rules we have to follow while converting this plain text to ciphertext. The first and foremost rule is divide the plain text into a pair of letters. Divide plain text to pair of letters. Next, second one. If any pair consists of repeated letters, just differentiate those repeated letters with any dummy letter. So differentiate repeated letters in the pair with dummy letter. So after dividing, now first we have to check whether the pair of letters, that means a plain text letters,
are in the same row or a column. So first, if a pair of plain text letters are in same row, then same row, if both the letters are in same row, replace them with rightmost letters. So we have to replace those letters with the rightmost letters. And similarly, if the plain text letters are in same column, if the plain text letters are in same column, then replace with beneath characters or letters. Replace with the beneath letters. So here beneath letters means downside letters. And the next one is in a diagonal positions. So if plain text letters are in different row and column, then replace with the character which is in the column corresponding to the row and row corresponding to the column. That is, simply we can remember it as a diagonal positions. So for this I am writing just for remembrance, diagonal positions. Replace with the diagonal positions. So whatever the characters we are taking, so replace them with the diagonal positions. So these are the rules we have to follow while applying the plain-text cipher. The first and foremost is we have to fill the 5 by 5 matrix. So 5 by 5 table. So first we have to fill with the key without any repetitions, and then we have to fill all the remaining blocks with the alphabets in an order which are not present in the key. And for this only 5 by 5 there are 25 blocks. The I and J characters must be merged into a single block. Then we have to apply the rules. First we have to divide the plain text into different pairs of characters. So, and next we have to find out whether each pair consists of the repetition letters or not. If you find any repetitions in the pair of characters, then differentiate those pair of repetition characters with any other dummy character. So then we have to find whether the plain text letters fall in the same row or same column or a different row and different column. So according to this, we have to convert this plain text to ciphertext. Now let us consider the plain text as hello and let us find out the ciphertext, corresponding ciphertext. See here, the first one is we have to divide the plain text into pair of letters. So I am dividing the plain text into pair of letters H-E, L-L and O. So first I have divided into pair of letters. So next I have to find whether the characters are in each pair are having a repetition or not. Yes, here I found L and L comes into same pair. That means there it is a repetition. So if there is no repetition, we have to add a dummy letter in the last one because it doesn't form a pair. Here there is only one character, so we have to add a dummy character. But before that, we have to check whether the remaining pairs are having the repeated characters or not. If there are repeated characters, first we have to differentiate those repeated characters with the dummy letter so that it will form a pair. So here this forms a repeated character, so differentiate with some x, some dummy letter, dummy character x. So after differentiation, HE forms one pair, LX forms one pair, LO forms another pair. So before it doesn't form a pair, and after checking the repetition characters, I have differentiated these two with another dummy letter so that the last character forms a pair. So first consider H and E, whether these two characters fall in the same row or same column or different columns. So H and E, H and E. So H is in the fourth column, E is in the second column. So both are in different rows and different columns. Here we have to replace in a diagonal positions. That means the letter which is corresponding to this column and which is corresponding to its row. That means H, E is replaced with diagonal. So W and F. So H, E is replaced with W and F. So same row column and same column row. So W, F. And coming to the second one, L, X. So here L and X. So L and X also in a different row and different column. So L, X is replaced with U and P. U and P. Similarly, the last pair L, O. L, O is, so here see L and O. Here also there are different in their forms. They doesn't fall in same row and same column. Both are in a different row and different column. So L, O are replaced with N and S. N and S. So the ciphertext characters are W, F, U, P and S for the given plain text. So like this we have to use the plain text. That means we have to substitute the plain text. Let us see one more example so that you can get a more understandable. First, let us take the plain text as balloon, right? So first we have to convert it into pair of characters. So B, A one pair, L one pair, O one pair, N another pair. First I have to differentiate with the dummy letter. So B, A, L, X, L, O, N. So there are no repetition in the pair. So first I am considering this B, A. So B, A, both are in same row. So if these are in same row, we have to replace with rightmost letter. So what is the rightmost of B? C. What is the rightmost of A? B. So plain text letter is BA and the ciphertext letter is C and B. So rightmost letter of B is C, rightmost letter of A is B. Next, LX. So LX is different. So LX replaced with UP. LX, UP. Next, LO. L and O. So L and O are replaced with N and S. N and S. Next, ON. ON and are in the same row. So we have to apply the rightmost character. What is the rightmost character of O? So we have to use a circular. So that means N. And what is the rightmost character of N? E. So ON is replaced with NE. We have to use the circular. Right? For this purpose, I have taken one more example, that is bell. So circular we have to use, and also here also we have to use a circular in the column wise and the row wise. So like this we have to convert the plain text to ciphertext. So these are the simple conventional encryption techniques, that is a substitution techniques, where we are substituting the ciphertext characters in the place of plain text characters. So the main drawback of these substitution techniques is these are only suitable for short length messages. and also the brute force attack will be very easier. That means these algorithms will be easily attacked by the cryptanalyst. Let's have a look on transposition techniques. So in this transposition techniques, we will just rearrange the order of bits to provide the security. So in the substitution techniques, we are just replacing the plaintext characters with the ciphertext characters. So here we will not replace any character, we will just rearrange the order of bit positions to provide the security. So in this transposition techniques, there are mainly two techniques. One is rail fence cipher and another one is row transposition cipher. Let us start with our rail fence cipher. So the main theme for this implementation of this transposition cipher is just rearrange the order of bits, order of plain text bits. You can say it as plain text bits. There will be no replacement or substitution. So this is very important. There is no replacement or substitution. Just we will rearrange the plain text bits in order to get the security. So there are mainly two techniques. First one, rail fence cipher. So in this, first we will consider a plain text and just we will rearrange the plain text characters, I mean jumbling the plain text characters so that we will get the ciphertext. So let us see an example so that you can clearly understand. The first one, example, let us take an example. So welcome to my session. So let us take this as a plain text. So this is the plain text which I need to convert into ciphertext. For this I have to write. So first I will draw a straight line and I will write one character just above the line and the next character just below the line. So I will continue until the end of this complete text. So I am writing W here, E here, L, C, O, M, E, T, O, M, Y, S, E, S, S, I, O, N. So just first I have draw a line and write one character just above the line and another character just below the line. Now write all the characters above the line in the one line and continuously the second line characters. So the ciphertext for the given plain text is W, L, O, E, O, Y, E, S, O, E, C, M, T, M, S, S, I, N. So this is the ciphertext for the given plain text, welcome to my session. So this we call it as a rail fence cipher. So as I have said in the substitution cipher session, so these messages are meant for only short length messages and these can be easily break down. That means these are very much vulnerable for the attack. So these can be easily attacked by the third party. So this is all about the rail fencing cipher. Just draw the line, write one character above the line and the other character below the line. So write all the characters which are above the line and continuously write all the characters just below the line so that we can get the ciphertext. So this is the ciphertext. So this is the simple technique of transposition. Here in this example, we just rearranged the position of the bits. We need not replace or substitute the ciphertext characters. We didn't add any additional characters, or we didn't add any replacements, we have done any replacements, right? So this is the rail fence cipher. There is one more cipher that we call it as row transposition cipher. So let us see that one. The second one, so row transposition cipher. Here first consider the plain text and key. So here let us consider the plain text as, so let us consider the previous example. So welcome to my session. So this is the plain text, and here we have to consider a key. So a key must be a numerical value. So any number of values, unique number, but unique number. So we have to write it as a unique. Unique numbers should be written. Should be considered only 0 to 9. So let us have a key as 3, 2, 4, 5, 1. So this is the key. In our example, let us consider 3, 2, 4, 5, 1 as a key. See, so these 2 points are important. This key is a numerical value. It should consist of only from 0 to 9, and unique numbers should be considered. So there must be no repetition in the key. So that we have to take care. Now, the key is 3, 2, 4, 5 and 1. Now we have to form a matrix, that means a table with a 5. So I will write here, so 3, 2, 4, 5 and 1. Now fill with the plain text characters. Sorry. W, E, L, C, O, M, E, 2, O, M, Y, S, E, S, S, I, O, N. So welcome to my session. So only 2 cases are remaining, that means 2 fields are remaining. Here you fill with the dummy letters, any letters you can consider. So I will consider it as X, Y. So these are the dummy letters, dummy characters, in order to fill the table. So here the key, this is the key, 3, 2, 4, 5, 1, and I am writing just the plain text in a 5 by 5 order. If you consider the 6-bit key, we have to consider the 6 by 6 order. So now write down the text with the order of the key value. So first the values are the cipher text, the order of 1, first one is 0, that is O, M, S, Y, and the second row, second column E, E, S, O, and the third column W, M, Y, I, fourth column L, T, E, N, fifth column C, O, S, X. So this is the ciphertext for the given plain text. So here we have to arrange the ciphertext according to the column numbers, right? So from ascending order, I mean lower order to higher order. So first consider the lower order number bits, and then towards the higher order number bits. So this is the ciphertext we got for the given plain text. So here also we are not using any substitutions or any replacements of a characters, just we are jumbling, that means rearranging the characters, and we have just added 2 dummy letters in order to fill this 5 by 5 table. if our key consists of only 4 characters, I mean 4 numbers, so then we have to consider a 4 by 4 matrix or 4 by 4 table. So if our key consists of 6 numbers, we have to consider 6 by 6 table. So we have to take care that every column should be filled successfully. So after completion, we have to write according to the lower column number to the higher column number. So this is the ciphertext we got in the row transposition cipher. So these two techniques, rail fencing cipher and the row transposition cipher, these two are the transposition techniques. So here also this message is also, I mean this technique is also used only for shortline messages. So this can also be easily break down. So in order to improve the security, simply we can have the dual, applying this transposition techniques 2 times, a dual cipher. So by applying the rail fence cipher 2 times, we will get a more security. Similarly, by applying this row transposition cipher 2 times, we can get the more security. Or we can do the combination of one, first we can do the rail fence cipher and we can apply the row transposition cipher. So the sequence of these 2 techniques also provide the more security. So for example, I have completed this, I have converted the ciphertext to this given plain text by using the row transposition cipher. Now in order to improve the security, I will consider this as a plain text and again I will apply with rail fence cipher. So this sequence of application is also improves the security of algorithm or technique. So hope you understood this transposition techniques. So here we are just rearranging the bit positions of the plain text characters in order to provide the security. So in the earlier sessions we have seen the difference between a block cipher and a stream cipher. So in the stream cipher we are just converting the plain text to the ciphertext bit by bit, and in the block cipher we are just considering a group of characters and we are considering a block, and at a time each block will be processed so that the plain text of each block will be converted into the ciphertext. So that means a stream cipher is a bit by bit and the block cipher is a block by block. The conversion of plain text to ciphertext is performed in a block by block. So let us have a look on a block cipher design principles. So what are the design principles of a block cipher? So before going to this block cipher design principles, so most of the block cipher techniques will follow a common structure, that is a Fiestel structure. So most of the block cipher techniques will follow this Fiestel structure. We can call it as a Fiestel or a Fiestel, right? So Fiestel structure. So what is a Fiestel structure? So before going to the algorithms of a block cipher, we have to know this Fiestel structure. So here in this Fiestel structure, the first step is the plain text blocks is processed in 2 equal halves. So that means the first step is we have to divide the plain text in 2 halves, 2 equal halves. So plain text, and we have to divide it as 2 equal halves. This is the left half and this is the right half. And on the right half, we have to apply in a function. We have to apply the function. So a function may be anything, any logical function it may be, right? So depends upon the algorithm, the function will be varying. But the right half will be applied in the function. So this is the function. That function, what is the function? Means that depends upon the algorithm. So it may be a logical functions. So, and in function we will use a separate key. So key 1, and this output from this function will be XORed with the left half, and the output from this left half
and this right half will be swapped. So that means the left half will be stored in rightmost bits, and similarly the right half will be saved in leftmost bits. So here again left and R. So the same process we call it as a round, a single round, and the process of converting this plain text to the ciphertext will be done in number of rounds. So the count, that means that the how many rounds we have to apply, that depends upon the algorithm we are using. So each algorithm will be having a different number of rounds. So, but if any plain text follows this structure, we call it as a Fiestel structure. That means that particular algorithm follows the Fiestel structure. That means any plain text in any algorithm, if the plain text is divided into two halves and all the functions are applied on the right half, and the result of this function is XORed with the left half, and next a swapping is there, and this process is continuously repeating in number of rounds, then we call that algorithm as a Fiestel structure. That algorithm is having this Fiestel structure. So here the security mainly depends on the functions, the number of rounds, and the number of keys. So here the key also, we will have a master key, and in each and every round we will use a separate subkey. That means from the master key we have to generate different subkeys. So depends upon the number of rounds, we have to then create a number of subkeys. So for example, if our algorithm is having a 10 rounds, that means a processing is done in 10 rounds, so we need to generate 10 subkeys from the master key. So this is again the left half, right half. Again the right half is applied to the function where the subkey 2 is used, and the result is XORed with right half. Again this will be saved in right half, and this will be saved in left half. So this we call it as a round function, round function. So likewise it will be keep on going. So this is called a Fiestel structure. That means the first, the plain text in two equal halves. In two equal halves. Next, number of rounds. So the plain text is processed in number of rounds to get the ciphertext, and number of subkeys, and swapping. So swapping of two halves, right to left and left to right. So if any algorithm follows these concepts, we simply say that that particular block cipher algorithm follows the Fiestel structure. So this is very important. And now if we look at the block cipher design principles, all these are the block cipher design principles. So first one, two halves. Next one, the number of rounds, number of subkeys, swapping, and the subkey size and the block size. All these are the block cipher design principles. Now let us see that. Alright. So this is all about the Fiestel structure. So in the next classes we are going to see the block cipher algorithm, that is called a DES algorithm, data encryption standard algorithm, which follows the Fiestel structure. So that means in that algorithm also the plain text is processed in two equal halves, and the right half is applied to the function in which the subkey is used, and the result will be XORed with the left half, and finally the swapping is done. And this process will be repeated in number of rounds, and this number of rounds will be dependent on the algorithm. Now, so hope you understood this Fiestel structure. So if you see the example for this Fiestel structure, so that you can clearly understand. So in the next session I will say the example for this Fiestel structure, that is a DES algorithm, data encryption standard algorithm.
So now let us have a look on block cipher design principles. Block cipher design principles. Block cipher design principles. So first one is block size. So this is a silly one, that is, as we are seeing this block cipher design principles, the plain text is processed in terms of blocks, so compulsory there must be a block size. So here the block size is the size of the plain text. So whatever the plain text size is there, automatically we will get the same size of ciphertext. So if you process 10 bits of plain text, we will get the 10 bits of ciphertext. That means the length of the plain text and ciphertext are same. So the first one is block size, key size. So we have to use a key from which we have to generate the subkeys. So key size. Next, number of rounds. So the plain text is processed to the ciphertext in number of rounds. So in each round the same process will be going on. And subkeys. Subkeys count or number of subkeys. So in each round we have to use a separate subkey. That means from this key, master key, we have to generate the subkeys. That depends upon the algorithm. Next, round function. So in each and every round we will use the function. One function. That's it. It may be a logical function, right? So that depends upon the algorithm. So for every round we have to use the same function. And last but not the least, the plain text in two equal halves. The plain text is processed in two equal halves. So these are the design principles of any block cipher algorithm. So hope you understood these design principles. And here the security depends on the number of rounds, subkeys, and this round function. So if number of rounds increased, the complexity will be increased and also the security will be increased. The data will be more secure. And if the subkey count, if number of rounds are increased, automatically the number of subkeys will also increase. So automatically the security will also increase. Round function. So if the round function is more complex, the analysis of that algorithm will be very strong. So it is very difficult to the cryptanalyst to attack the data or to break the algorithm. So the security related issues are number of rounds, number of subkeys count, and the round function in the block cipher algorithm. So this is all about the Fiestel structure and the block cipher design principles. Hope you understood this simple concept. So let us stop here. In the next session we will go with the algorithm, very important algorithm, that is a DES algorithm, data encryption standard. So which is a block cipher symmetric algorithm. DES. So it stands for data encryption algorithm. So this algorithm is a block cipher algorithm. That means the plain text is processed to the ciphertext in number of blocks. So here the block size of a plain text is 64-bit. So at a time the 64-bit plain text is processed to get the ciphertext. Next, so it follows the Fiestel structure. So it blindly follows the Fiestel structure. So here the plain text is processed in number of rounds. So number of rounds to implement this DES algorithm is 16 rounds. So total it requires 16 rounds. Next, key size. Here the key size is also 64-bit. So in some materials you will find it is as a 56-bit. But actually the key size is 64. So from this 64 it will be converted into 56. So later I will explain it. Next, as we have seen in the Fiestel structure, if any block cipher follows the Fiestel structure, that means the plain text is processed in number of rounds, each round should have a separate independent key. That means here the key size is 64. So we are having 16 rounds in this DES algorithm. So totally we have to generate 16 subkeys. So number of subkeys, 16 rounds there we are processing, so we require 16 subkeys. Now the question is, what is the subkey size? Subkey size. So here the subkey size is 48-bit subkey. So this is the plain text, 48-bit subkey. So from the 64-bit key we have to generate 16 48-bit subkeys. So in each and every round we are supposed to use the subkey, each subkey. So these are from 1 to 16 subkeys. So finally ciphertext, the result of this DES algorithm, that means the ciphertext, size of a ciphertext is, so here we are considering 64-bit plain text. So obviously we will get the 64-bit ciphertext. So this is a simple overview of DES algorithm. The first and foremost point is it follows the Fiestel structure. So if it follows the Fiestel structure, it's a block cipher algorithm. So block size is 64-bit. So if number of rounds, so plain text is processed to ciphertext in number of rounds. So in the DES we have to implement 16 rounds, and the key size is 64-bit key, and from this 64-bit key we have to generate 16 48-bit subkeys, so where each subkey should be used in each round, and finally we will get the ciphertext as 64-bit ciphertext. So this is a simple overview of a DES algorithm. Now let us move on to the block diagram of DES algorithm. See, coming to this block cipher algorithm, the first point is, here we will use some transposition orders which are predefined. So we have to arrange the bits in the given order. So that is fixed. So we have to follow the order, transposition order. So here the transposition order means rearranging the bit positions, which we have seen in the transposition ciphers. So like that, in like the transposition techniques, here also we will use a more number of transposition orders. So here in number of times we are required to rearrange the order of bits. So there is some order given, so I will show you that order. So we have to follow the order in order to implement this DES algorithm. So first, let us see the block diagram of DES, and then we will move on to the next step. So first and foremost, we have to consider the plain text, and we have to apply the initial permutation. So this is the initial permutation. Here we have to give 64-bit plain text. So here the transposition order, we call it as a permutation. So wherever the permutation concept came, there we have to follow the transposition order, which I will show you in the next coming minutes. So here the 64-bit plain text is given as input to the initial permutation, where we have to follow the transposition order. So that means we have to rearrange the bit positions, and from this we will get again 64-bit as output. So this 64-bit will be given to a round 1. So in this round we have to use a key. So parallelly we have to generate the sub keys which we have to use in the round function. So parallelly I will write here So here the key is also, as I have said, it is 64-bit key. For this 64-bit key, first we have to use permuted choice 1. Permuted choice 1. So the input for this permuted choice 1 is 56-bit key, and the output from this is 56. So the input is 64-bit, the output is 56-bit key. And from here we have to apply left circular shift operation. Left circular shift operation. From this we will get again 56-bit key. From that we have to again apply permuted choice 2. So here also the permuted choice means rearranging the bit positions. So from this we will get the key which is of 48-bit. Hope you understood. First we have to consider the 64-bit key, and this should be given as input to the permuted choice 1, where the transposition order will be given. So according to that transposition order we have to rearrange the bits. So in that purpose some 8 bits will be ignored, and the output from this permuted choice 1 is 56-bit, and this is given to the left circular shift operation. So depends upon the round how many bits we have to shift is given in the example, given in the algorithm. So depends upon the round function, we have to consider how many number of bits should be left circular shifted. So the output from this LCS is 56-bit, and that is again given to the permuted choice 2. Here the permuted choice 2. So here also we have to follow the transposition order, where again 8 bits will be ignored, so that we will get the 48-bit key which is used in the round function 1. So this is key 1. Again after round 1 again apply round 2. Again apply round 2. Again after this circular shift, once again give to left circular shift. Again you have to perform the left circular shift operation. So how many bits we have to shift is depending on the round number. So again this is a 56-bit key. Again this is applied to the permuted choice 2. Where some bits will be ignored. So this is 56-bit key, and from this we will get 48-bit key 2. Similarly we will follow the same procedure till round 16. So we will follow the same procedure till the round 16. So here also we will use left circular shift operation. So the number of bits to be shifted depends upon the round number. So from this we have to give into the input to the permuted choice 2. From this again we will get here 56 bit is given to PC2, here 48 bit will be output from PC2. So key 16. After completion of all these rounds, we have to perform 32-bit swap. So we have to perform 32-bit swap. Here it is a 64-bit. We have to divide it into two equal parts, 32 left half and 32 right half. Those 32-bit will be swapped. That means exchange. The left 32 will be copied to the right side. Right 32-bit will be copied to the left side. So after completion of this 32-bit swap, again we have to apply inverse initial permutation. Inverse initial permutation. So here this inverse initial permutation is also the transposition order. So where we have to rearrange the bit positions. So the output from this is a ciphertext. So this is the block diagram of DES algorithm. So first consider the 64-bit plain text, give it as input to the initial permutation. So where we have to rearrange the bit positions of this plain text, and the output of initial permutation is again given as input to the round 1, where the sub key is generated, key 1 is generated, and key 1 is used in the round 1. And then the output from round 1 is given as input to the round 2. Similarly, here the second key is generated with a 48-bit, and this key 2 is again used in round 2. And the output of round 2 is given as input to round 3. So likewise we have to complete until round 16. So after completion of round 16, the output of round 16 will be given as input to the 32-bit swapping. That means now we have to exchange the two equal 32 halves. So after exchanging, it will be given as input to the inverse initial permutations. Once again we have to rearrange the order. So here we are rearranging the order. So that's why we have to again rearrange the order of the positions, order of bits. And the output from this inverse initial permutation is the final ciphertext, which is a 64-bit ciphertext. So this is the block diagram of DES algorithm. Now we have to elaborate this round function. This round function, that means what actually happens in this round function. So parallelly we are generating the subkeys. So here 16 rounds, so 16 subkeys should be generated. And in each round, what is happening? That means what operations or what functions will be applied on round function. So let us see the round function now. So let us see the round function now. So first, the 64-bit is divided into two halves, left half, right half. And similarly, let us consider the key. Key is also divided into two halves, left key and right key. Okay, now, so this is a a 32 bit, and this is also a 32 bit. This is 28 bit, and this is also 28 bit. So we have to divide it into two equal parts. So this one, the 32 bit is given as input to the expansion permutation. Expansion permutation. So here this is the 32 bit. After giving the 32 as input to the expansion permutation, as its name indicates, we have to add 16 more bits, and this completely becomes a 48 bit. So that means additional 16 bits will be added in this expansion permutation. So that's why the name indicates expansion. So we have to add more number of bits, and this must be XORed. This must be XORed with key. Now first we have to use left circular shift. So apply the left circular shift. Here also left circular shift, and after this left circular shift we have to apply for the permuted choice 2. So this will be given to permuted choice 2. So here also it will be 28 and 28, and from this we will get 48 bit key 1. So here some 8 bits will be reduced. So this can also be called as contraction. That means reducing the number of bits. Here we call it as expansion, here contraction. That means reducing. So after XORing this, we have to apply this 48 bit to S boxes. S box is called a substitution box. So the input for this S box is 48 bit, and the output from this S box is 32 bit. Again, some bits will be reduced. So 48 will be reduced to 32 bit. So after coming from the S box, again apply the permutation function. Apply the permutation function. That means again this is a transposition order given by the DES implementation. So here also we have to rearrange the order of bit positions. So from this we will get 32 bits, and this will be XORed with left half. This will be XORed with left half, and this will be stored in R, and this will be stored in left half. Right? So these are the inputs for the next term. So L and R are the two 32 bits, and this 32 bit will be expanded to 48 bit, and parallelly the key will be generated, the sub key is generated of 48 bit, so which is XORed with the expansion output of expansion permutation, and that 48 bits will be given as input to the substitution boxes, where it will be converted into 32 bits. Some 16 bits will be reduced, so 32 bit will be generated, and this 32 bit must be given as input to the permutation function, where again we have to follow the transposition order to rearrange the bit positions, and the output of permutation function will be XORed with the left 32 bit and stored in the right half, and the right half is stored in the left half. So these two will be input for next round, and here also after applying this left circular shift, store it in LK, store it in RK. So here these two are the inputs for the next round, that means next key generation, inputs for next key generation. These are the initial inputs and these are the inputs for the next key generation. So this is the actual round function. Round function of DES. Round function of DES. So here we have to see what actually happens in the expansion permutation, S boxes, and the permutation, and the permuted choice too. Now let us see one by one so that you can clearly understand, right? So first, let us start from the beginning, block diagram. So considering the 64-bit plain text. So after considering the 64-bit plain text, we have to give that 64-bit plain text as the input to the initial permutation. So here the initial permutation, see, this is the block diagram. So coming to this block diagram, here we have given the 64-bit plain text to the initial permutation. So where we have to rearrange the order of bit positions. That means we have to follow the transposition order. So before applying the initial permutation, for easy understanding, we will represent this 64-bit as 8 by 8 representations. That means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on, 16, 17 and so on, 24, so on, 64. So for easy representation, we are representing this plain text as 8 by 8 table. So applying to initial permutation, first applying to initial permutation, so we have to follow the procedure. That means we have to follow this initial permutation, the transposition order, where the 58th bit will be in the first position, 50th bit will be in the second position, 42nd bit will be in the third position, and similarly 7th bit will be in the last position. So blindly we have to follow this transposition order. So in the DES algorithm, so this will be the transposition order of initial permutation. So after this initial permutation, I mean after arranging this order of bit positions, again consider this as a first position, second position, third position, fourth position. So actually the plain text, in the plain text, the first position will be the 58th bit, second position will be the 50th bit. So now we are rearranging the order of bit positions according to the given transposition order. So after initial permutation, so again we have to give the output of initial permutation to round 1. So in that round 1, the first thing is we have to divide the plain text into two halves. So this is the right half, this is the left half, and this is the right half. So the right half is given as input to the expansion permutation. So expansion permutation means we have to expand the number of bits. So here the input for this expansion permutation is 32 bit and the output from this expansion permutation is 48 bit. So 16 bits will be added in this expansion permutation. So this is the transposition order given to the, which we have to follow for the expansion permutation. So arrange 1, 2, 3, 4, 5, 6, so and so 32, and these 16 bits will be added. So 32nd bit will be added once again, 4th bit 8, 12, 16, 20, 24, 28, 5, 9, 13, 17, 21, 25, 29 and 1. So these 16 bits will be added so that the complete length of this expansion permutation becomes 48. So the input is 32 and the output is 48. We are adding 16 bits. So after applying to this expansion permutation, so we have to XOR the output of expansion permutation with the permuted choice 2. That means the output of permuted choice 2. So for this permuted choice 2, we have to generate the subkey. For this, so as I have said that in the block diagram, the key size is a 64 bit, and from this 64 bit we have to apply that 64 bit as input to the permuted choice 1. So where we have to again follow the transposition order. So here again we have to follow the transposition order given for this permuted choice 1. So simple thing is, here just in the permuted choice 1 we will eliminate the multiple of 8 bits. That means 8, 16, 24, 32. So all these bits will be eliminated. So you can observe you can't find the multiple of 8 bits in this permuted choice 1. So this is the output of permuted choice 1. So the input for this permuted choice 1 is 64 and the output is only 56 bit. So that 56 bit is again given to the left circular shift. So we have to apply the left circular shift, and that 56 bit is again divided into 2 equal halves. So here we can see 2 equal halves, so left half and right half. So 28 bit and 28 bit, so total 56 bit. So after applying the permuted choice 1, the output of permuted choice 1 is 56. So that 56 is again divided into 2 halves, 28 and 28, and that 28 bit is given as input to the left circular shift. So the number of bits to be shifted depends upon the round number. See, so depends upon the round number, how many bits we are going to shift. So in the round 1, round number 1, round number 2, round number 9 and round number 16, we have to perform 1 bit circular shift operation. So 1, 2, 9 and 16. So in all these 4 rounds we have to shift only 1 bit, and in the rest of the round numbers we have to shift 2 bits. So we have to apply the 2 bits left circular shift. So after applying the left circular shift, we will get again we have to give this output of left circular shift to permuted choice 2. Once again we have to apply the transposition order, where the 56 bit key will be reduced to 48 bit. So that's why here we can see it as permutation or a contraction. Permutation or a contraction. Contraction here means reduces the number of bits. So here the permutation choice 2 is applied. So here the permuted choice 2 is also the transposition order which we have to follow in the AES algorithm. So this is the permuted choice 2, where we have to rearrange the bit positions according to this transposition order. So here some 8 bits will be reduced. So 56 bit key will be reduced to 48 bit. after applying this permitted choice 2. So some 8 bits will be reduced. So according to this bit positions, we have to rearrange the bits. So output from this permitted choice 2 is a 48 bit. So input is 56 and output is 48. And now the output from this permitted choice 2 is given XORed with the output from the expansion permutation. See, here the output from this permitted choice 2 is XORed with the output of expansion permutation, where we got a 32 bit to 48 bit. So output of this XOR operation is again 48 bit. So obviously, so this 48 bit will be applied to the substitution boxes, where again the 48 bit will be reduced to 32 bit. So let us see this operation, how this substitution box, how that 48 bit will be reduced to 32 bit. So here we will apply this S boxes, transposition boxes, substitution boxes. See, so in our AES algorithm there will be total 8 S boxes. So the input for S box is 48. The output from the S box is 32 bit. So this 48 bit will be divided to 8 S boxes. That means, so each S box, S1, S2, S3, S4, S5, S6, S7, S8. So each S box will get 8 bits as input. 6 bits as input. Right? So 8 S boxes, so 6 bits as input. So 6 bits. 6. So the output from this each S box will be 4 bit. So 2 bits will be reduced. So total will be 8 4s 32 bit. So that means the input is 48. The input is 48. The 48 is divided to 8 S boxes, and each S box will take 6 bit as input and it produces 4 bit as output. So let us see. Each S box will be having input 6 bit and output 4 bit. So how this 6 bit is reduced to 4 bit? Let's have a look. So if you consider 6 bits, let it be 1 0 0 1 1 0. If you consider these 6 bits, these are the 6 bits. The first bit and the last bit represents the row number. So here the S box is a table of numbers. S box is a table of values. It's a table of values. So obviously if it is a table, we must know rows and columns, right? So here the first and last bit, first plus last bit represents row number, and the between 4 bits represents column number. So the first and last bits, that means 2 bits, right? So here 2 bits, here 4 bits. So what is the maximum number we can represent using 2 bits? So the combinations are 0 0 0 1 1 0 1 1. So the maximum number is 3. And how many combinations? 4 combinations, right? So 4 choices. So there will be 4 rows in our S box, and here it is 4 bits. So the maximum number we can represent using the 4 bits is 1 1 1 1, and the least number is 0 0 0 0. So this is a 15, 0, this is 0. That means total 16 columns will be there. So our S box consists of 4 rows and 16 columns. So here the 4 is represented as 0, 1, 2, 3, numbering of rows. 0th row, first row, second row and third row. And the column representation is 0, 1, 2 and so on 15. 0th row, first row, second row and so on 15th row. 15 column. So in this example, let us see the first and last bit, that means 1, 0 represents the row. So 1, 0 means, what is the decimal number? It's a 2. Second row, and the remaining bits, in between bits, 0 0 1 1. So here 8 4 2 1. So it is a column number. It represents the column number 3. So we have to consider this table of values, and we have to consider the corresponding element with a row 2 and a column 3. So let us have an example. So each S box will be having 4 rows and 16 columns. So this is a sample S box which is having 4 rows and 16 columns. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. Total 16 columns and 4 rows. 0th row, first row, second row, third row. So in our example, we got a second row and a third column. See, second row. Here, second row is 0th row, first row, second row. And the third column, 0th one, 0th column, first column, second column, third column. So here the value in the third column is 0, 1, 2, 3. So here the third column is 8. So the result of this one is 8, which is again represented in a binary format. So 8 is represented as 1 0 0 0. So the output of this 6 bits is 1 0 0 0. So this is for S1. So like this table, we will be having total 8 tables. That means 8 S boxes. Each S box is having 6-bit input. So from that 6-bit input, we have to consider the first and last bits as a row number and the remaining 4 bits as a column number. And in the table, we have to find out the corresponding value of given or calculated row number or a column number. So here in this example, we are taking 1 0 0 1 1 0 as a input, 6 bits. So first and last bits 1 and 0 represents the row number, and the last in between 4 bits represent the column number 3, 2 and 3. So we have to consider the value in the second row, third column. So second row is 0th row, first row, second row. Third column is 0th column, first column, second column and the third column. The value is 8. So 8 is again represented in binary value. So 1 0 0. So which is the output of S box 1. So likewise, we have to consider, we have to calculate the output from all the 8 S boxes. So here each S box is containing 6-bit input and we will get a 4-bit output. Totally we will get the 32-bit output from the S boxes. So here in the DES the security will lies on the S boxes, right? So similarly we will have total 8 tables. 8 tables. So after getting the output from the S box, and we are applying the permutation for the obtaining output. That means 32-bit will be, again we are applying to the permutation. That means again we have to follow some transposition order. So the permutation for this transposition order is, so this one. So here the length of the bits will not be changed, only the 32 bit. The arrangement of bit will be changed. So we have to rearrange the bit positions according to the given transposition order. So we have to follow this order. So no bits, so the number of bits will not be reduced or the number of bits will not be added. So the input for this permutation is 32 and the output from this permutation function is also 32. Here only the rearrangement will be done according to the given transposition order. So here the 16th bit will be in the first position, 7th bit will be in the second position, 20th bit will be in the third position, likewise. So after applying to the permutation, the output of permutation function is 32 bit and which is XORed with the left 32 bit. So in the starting position, in the initial stage, we have divided the plain text into two halves. This left half is now XORed with the output from the permutation and it is stored in the right. And rightmost 32 bit before applying to this expansion permutation, it will be given, it will be stored in the left half. Left half. So these two will be the inputs for the second round. And before applying to the permuted choice 2, the output from the left circular shift will be given as input to the next round. Here we will see C and D. So here these two are the inputs for next round for the next key generation. Here these two are the inputs for the next round of the plain text processing. So this is a single round which is applied in the AES algorithm. This is a complete single round function. So we have to follow the same round function 16 times. So after completion of 16 rounds, we have to apply the 32-bit swap. So that means the left half will be stored in right half and the right half will be stored in the left half. So 32-bit swap will be done. Again here we will get the 64-bit. So after that, after applying this 32-bit swap, this 64-bit will be again given to the inverse initial permutation. So initial permutation we have applied. So we have to apply the inverse initial permutation where we have to rearrange the order of bit positions. So here also the input is 64 and output is 64. So no bits will be added, no bits will be discarded. So whatever the input we are giving to the inverse initial permutation, we will get the same number of bits as the output. So this is the final permutation function. Inverse initial permutation, final permutation, that called inverse initial permutation. Again we have to rearrange the order of bits in the given transposition order. So this is the ciphertext. So the output of this final permutation or inverse initial permutation will be the ciphertext. See, the inverse initial permutation, the output from the inverse initial permutation is the 64-bit ciphertext. So likewise we have to apply this AES algorithm in 16 rounds, and in each round we have to apply the round function. Parallelly we have to generate the subkeys from the given master key, and each subkey will be XORed, used in each round. And here we have to use a left circular shift, perform the left circular shift according to the round number. The number of bits should be left shifted. So in the round numbers 1, 2, 9 and 16, 1 bit left circular shift should be applied, and in the rest of the round numbers we have to perform 2 bits left circular shift. So this is the complete round function. So the important thing is S-box conversion. Here 8 S-boxes will be there. So each S-box will be having 6-bit input and 4-bit output. So in the 6-bit, first bit and last bit will be considered as a row number, the decimal value of 2 bits, and the decimal value of the in-between bits will be represented as a column number. So the 2 bits, the maximum number of maximum number representation with the 2 bits is 3. That means the combinations are, the possibilities are decimal values 0, 1, 2 and 3, total 4 rows, and a column in between 4 bits we will get the maximum number 15 and the minimum number 0. So each S box will be having 4 rows and 16 columns. The numbering for rows is 0, 1, 2, 3 and the numbering for columns is 0, 1, 2, 3 and so on 15. So we have to consider the decimal values and we have to consider the corresponding decimal value and convert that corresponding decimal value to binary value. So this is the S box. So we have to consider the corresponding row value in the corresponding row and column, and we have to again convert it into the binary value. That means we have to represent it into a 4-bit representation, so that we will get the output as 4-bit. So after combining all these 4 bits from the 8 S boxes, we will get 32-bit. So this 32-bit will be again given to the permutation function, where the permutation, that means rearrangement of bits, will be done, which is XORed with the left half, and the rightmost 32-bit will be saved in the left, which is given as input to the next round, and the output from the XOR will be saved in the right, which is given as input to the next round. So hope you understood this DES algorithm. Look on one more block cipher algorithm, that is AES algorithm, Advanced Encryption Standard. AES algorithm. So AES stands for Advanced Encryption Standard. So similar to the DES algorithm, here also the plain text is processed in blocks. So that means here also there will be a block size. So we will not process the entire plain text to the ciphertext. First the plain text will be divided into different blocks. So at a time we will process each block. So here the block size is 128 bit. 128 bit block size. That means here the plain text. And next, here also we will use a key in each and every round, and similar to the DES algorithm, in AES algorithm also the plain text is processed in number of rounds to get the ciphertext. So here the number of rounds the plain text is processed is 10 rounds. 10 rounds. So in the DES we are performing 16 rounds, and in each and every round we are using a separate subkey. Here also we have to use a separate subkey in each and every round. So the master key, the key size here is 128 bit. The key size is also 128 bit, but here the key is processed in terms of words. In terms of words. So here the word means 32 bit. One word is equal to 32 bit. So 128 bits are processed in 4 words, or we can say it as 16 bytes. 4 words or 16 bytes. So here the key size is 128 bit, which is processed in terms of words or bytes. In terms of words, we will say it has a 4 words. If we are representing in bytes, it is a 16 bytes. So here number of keys, number of subkeys, we are using a 44 subkeys. 44 subkeys. So each subkey size is 32-bit or 1 word. 32-bit or 1 word. So, or we can say it as 4 bytes. Anything. We can represent in bit, word, bytes. So 32-bit or 1 word. 1 word is 32-bit. 4 bytes. That means 4 into 8 bits. So 32-bit. And in each round, we are going to use 4 keys, 4 subkeys. Each round, we are going to use 4 subkeys. That means the size of key in each round is 4 subkeys. That means 4 into 32. That means 128 bit or 4 words or 16 bytes. So we can represent in either bits or words or bytes. So in each round we have to use 4 subkeys. So total how many rounds? 10 rounds. In each round 4 subkeys. Total 40 subkeys. So before starting the round function, we have to use 4 more words. So pre-round calculation. So in the pre-round calculation, we will use 4 words. That means So 4 subkeys will be used. That means 128 bit or 4 words or 16 bytes. So total we are using in the 10 rounds. So that means in each round we are going to use 4 subkeys, total 40 subkeys. And before starting the round function, we have to perform this. We have to apply these 4 subkeys. We are going to use these 4 subkeys in the algorithm. So total 40 plus 4, 44 subkeys will be generated. So once again, the block size of this advanced encryption standard is 128-bit plain text. So which can be processed in similar 4 words or 16 bytes. And the number of rounds the plain text is converted into ciphertext is 10 rounds. The key size is 128-bit again, which is represented in 4 bytes or 16 bytes. And the number of subkeys used in this algorithm are 44 subkeys. And the subkey size is 32-bit or 1 word or 4 bytes. And in each round we have to use 4 subkeys. That means the size is 128-bit or 4 words or 16 bits. So 16 bytes. And before applying the round function, we have to use 4 more subkeys. So totally 4 into 10, 40 plus 4, 44 subkeys will be generated from the master key 128-bit. So this is all the summary about this AES algorithm. So finally, the ciphertext. The ciphertext will be obviously 128-bit, which is again 4 words or 16 bytes. So this is all about the summary of algorithm. Now let us move on to the block diagram of AES algorithm. First of all, consider the plain text. so which is 128 bit, and this is applied to add round key So we have to apply the add round key, that means just XOR operation. So here we will use 4 words. So that means a key, one key. Let us represent K0. Okay, K0, which is in terms of words. I mean, if we represent in terms of words, we can write it as word 0 to word 3. So word 0, 1, 2, 3. 4 words. So that means one key, 128 bit. So after applying this add round key, next we have to apply substitute bytes. Substitute bytes. So which we call it as S boxes in our DES algorithm. Here the substitute bytes are equal to S boxes. And after applying the S boxes, so first I will write the block diagram, I will draw the block diagram, then we will move on to the each and every operation. So what will be happening in these S boxes and what will be happening in the add round key, and one by one we will see. Before that, first we will see the block diagram. So first substitute bytes, so which is S box. Here also the input is 128 bit and the output is also 128 bit. Here after the S box we have to apply shift rows. Shift rows. So here the shift rows means just applying the circular right shift operation. Just we have to apply the circular right shift operation. And after this, here also the size will not vary, 128 bit is the input and output also 128 bit. Next, after coming from the shift rows, we have to apply mix columns. Mix columns. Here we have to multiply with a predefined matrix. So a matrix is predefined, so 4 by 4 matrix, and we have to consider one word and we have to multiply that particular word with the predefined matrix, and the resultant will be stored in the another thing. So that is mix columns. And the output, here also there is no change on the size of the bits. The size of the input is a 128 bit and the output from this mixed columns is also 128 bit. And the output will be again given to add round key. Where we have to use the key 1, which is W4, 5, 6, 7. So 4 more words we are using. So this process, so this box, this complete box is a round 1. The complete box is a round 1. So we have to repeat the same process for 10 rounds. In each round we have to use a separate subkey. So before applying to this round function, we are performing the add round key where we are using 4 words. And in the round 1 we are applying next 4 words. In the second round we have to apply, so round 2 we have to apply the words from 8 to 11. So 8, 9, 10 and 11. In the round 3, again we have to apply 12 to 12, 13, 14 and 15. Similarly, in the round 10, we have to apply W, 43, 42, 41 and 40. So 42, 43. So total 44 words will be used in our AES algorithm. So these 44 words are generated from 128-bit key. Hope you understood. So this we call it as K2, K3 and so on K9. So 0, 1, 2, 3 and so on 9. So this is the single round function in AES algorithm. So we have to process this round function 10 times. That means 10 rounds. So in each and every round, the first step is applying to the substitute boxes, and the output from substitute box will be given to shift rows, and the output from shift rows will be given to mixed columns, and the output from mixed columns will be given to add round key. So by adding this round key, the first round will be completed. So in the last round, in the 10th round, a small change will be there. There we need not apply the mixed columns. So we will apply only 3 processes, 3 functions. First one SBox, next shift rows, and directly we can add the, we can perform the add round key. So in the last round, only in the last round, in the 10th round. So for all the 9 rounds, we have to apply the 4 processes. So SBox, shift rows, mixed columns and add round key. In the second round also we have to apply the 4. Only in the 10th round, that means in the last round, we can ignore the mixed columns. We need not perform the mixed columns. So hope you understood this block diagram. So let us continue with the each and every process. So before going to each and every process, first let us look on about the representations. What about the representations? Here the 128-bit plain text is stored in input arrays. So here the input array is represented as 4 by 4 table. In each and every column is represented as 1 byte. So input is stored in input array, so which is a 4 by 4 table. Here we can have input 0, input 1, input 2, input 3, input 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So this is how we will represent the plain text. So here each column represents 1 byte. So total 16 bytes. So 16 bytes, so which is equal to 16 into 8, that is 128 bit. So intermediate results are stored in state array, which can be represented as S00, S10, S20, S30. Similarly, S01, S0, 11, S21, S31. Similarly, S02, S12, S13, S14. Similarly, 1, 2 and 2, 2. Similarly, 3, 2. Yes, 0, 3, 1, 3, 2, 3, 3, 3. So this is the state array where the intermediate results will be stored. So here this representation is also 4 by 4, that means 16 bytes. So in each block the size is, each column the size is 8 bytes, 8 bits, right? So 8 bits means 128 bit. Total size of the state array is 128 bit. And similarly, the output will be stored in output array. Similarly, output array. So which is again 4 by 4. So output 0, output 1, output 2, output 3. Similarly, output 4, output 5, output 6, output 7, output 8, output 9, 10, 11, 12, 13, 14, 15. So this is the output array, which is again represented in 4 by 4 table. So each column represents 1 byte. So total we will get 128 bit. So input array is stored in, input is stored in input array. So each block will be consists of 1 byte. So total 16 bytes, that is 128 bit. So all the intermediate results will be stored in state array. This is called a state array. We will call it as a state array. State array, so which is represented as S00, that means 0th byte of 0th word. So this is the word. So this one is the first column. So this column is a one word. It is treated as a one word. So 0th byte of 0th word, first byte of 0th word, second byte of 0th word, and 4th byte of 0th word. Similarly, the 0th byte of first word, 0th byte of, first byte of first word, second byte of first word, third byte of first word, 0th byte of second word, first byte of second word, second byte of second word, third byte of second word. Similarly, we will consider each column as a one word. So this totally 4 words. So this is the state array, this is the output array. So state array is used to store the intermediate results. Similarly, so all these are the representations, right? So similarly, key. What about the key? So key also 128 bit. So the key is also stored as 4 by 4 table. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is the key. So now this 128 bit, from this 128 bit, that means it is a 128 bit, or we can consider it as a 4 words. 4 words. So this is the first word, second word, third word, fourth word. First word, second word, third word, and fourth word. So these 4 words, we have to generate 44 words. So from this we will expand the key with column W0, W1, W2 and so on, W43. So this key is expanded to 43 words. So 44 words. From 0 we are starting, total 44 words. Where 40 words are used in 10 rounds and 4 words are used in pre-addition. So from 4 words we are expanding to 44 words. Right? So now, this is how we will represent the data in AES algorithm in terms of words. First, let us take the substitution bytes. So here the substitution bytes is S box. So the implementation of S box. So here the input of S box is, so we are considering first 8 bits will be considered as input, and this 8 bits will be calculated, in S box. In the AES algorithm we are considering 6 bits as input for S box and 4 bits as output from the S box. There we have seen the first bit and the last bit representation, the decimal value of the first bit and the last bit will be representing the row number, and the in between 4 bits representation will be in the column number, and we will consider the corresponding value and we will again convert into binary so that we will get the 4 bits output. Here from the 8 bits, first 4 bits is represented with row number, and the next 4 bits represents the column number. First 4 bits represents the row number, second 4 bits represent the column number. So that's why again, so what is the maximum number using this 4 bits? It's 16 or 15, right? So 15. So 0 to 15. We can represent the numbers from 0 to 15. Here also 0 to 15. So here the 15 is represented as F. Here also F. We can represent it as an F, right? So the output is also 8 bits. So the input here for the S box is 8 bits and the output is also 8 bits. And this 8 bits again saved in the state array. So this is the state array. This is the input array. So consider the first 8 bits. From the 8 bits, first 4 bits will be representing the row number and the next 4 bits represents the column number. So the size of S box. So size of S box is 16 by 16. The table with 16 by 16. So in the AES algorithm we have seen the size of S box is 4 by 16. That means 4 rows and 16 columns. But in the AES algorithm we are representing first 4 with row number, second 4 with the column number. So we have to use 16 by 16 table in the S boxes. So this is 16 rows and 16 columns. And the remaining procedure is same. We have to get the corresponding value from the S box, and again we have to convert into 8 bits. So this is all about S boxes. So I will show you the here. So this is the representation. So this is the input representation 4 by 4 table. This is the state array representing S, S00, S10, S20 and so on. So this is the state array to store the intermediate results, and this is the output array to store the output. And here the key also represented using 4 words. So each column represents 1 word. So 4 words, and from the 4 words we are expanding it to 44 words from W0 to W43. So this is the key expansion. So coming to this S boxes, so consider one block and 8 bits. That means one block size is 8 bits. In that 8 bits, first 4 bits represents the row number and column number. So this is the S box, that is 16 into 16 S boxes. That means 16 rows and 16 columns. So corresponding value we have to get. So again the representation will be in 8 bits, and we will save it in the corresponding word number, I mean row, block number. So this is the S box in AES algorithm. So 16 rows and 16 columns. So if you consider the example, these are the 8 bits, right? So if you consider these are the 8 bits from the S box input, first represent a row number, second 4 represent column number. So row number is 0, column number is 5. We have to get the value from 0th row, 5th column. So here in this example, see, so 0th row, 5th column, it is 52. 0th row, 5th column, it's a 52. So the result is 52, which is again converted into 8 bits. That means 0101, 0010. So this is the output from S box with a value 0000, 0101. So this is the input of S box, and this is the output from the S box. So this will be this will be stored in state array. So according to this, we have to find the output. So we have to apply the same procedure for all the blocks with 8 bytes. So first consider the first block with S00. So find out the corresponding output, store it in the S-00. Next, consider the S10 and find the corresponding value and store it in S-10. Similarly, we have to find out all these things. So like this, we have to apply the S box in AES algorithm. So after completion of S box, the next process is shift rows. So let it be S01, 00, S10, so that means the first byte of first word. So 20, S30, S01, 1 1, S 2 1, S 3 1, S 0 2, S 1 2, S 2 2, S 3 2, S 0 3, S 1 3, S 2 3, S 3 3. So this is the state array input for S box, and the output will be stored in another state array called S dash. So S dash 1 0. So just representation is different. So input is S and output is S dash. So this is only for S box, and this will be given as input to shift rows. So shift rows, the next process is shift rows. So in this shift rows, depends upon the row number, we have to shift the rows. So if it is row 0, we have to shift the 0 bits. Circular right shift, we have to perform circular right shift. So if it is row 1, 1 bit is shifted. If it is row 2, 2 bits are shifted. If it is row 3, 3 bits are shifted. So if you observe here, so this is the state matrix which is given as input to the shift rows. So 0 0, 1 0, 2 0, 3 0, 0 1, 1 1, 2 1, 3 1, and as it is the first 0th row, 0 bit should be shifted. So this is the output after performing the shift operation. So no change, because as it is the row number is 0, we should not shift any bits. So it is a 1 bit circular right shift. It is a row 1, we have to perform 1 bit circular right shift. So after circular right shifting 1 bit, so the output will be S11, 12, 13, 10. So here 10, 11, 12, 13. After performing the circular right shift, 11, 12, 13 and 10. And coming to the second row, 2 bits we have to shift. So initially it is 20, 21, 22, 23. And after performing the right shift, it becomes 22, 23, 20, 21. And it is a row number 3. 3 bits we have to shift, right shift. So before applying this shift operation, the value is 30, 31, 32, 33. And after performing the shift operation, we will get 33, 30, 31, 32. So similar way we have to perform the shift operation. So we have to apply this shift operation based upon the row number. Row number 0, 0 bits. Row number 1, 1 bit. Row number 2, 2 bits. Row number 3, 3 bits. And the result will also be stored in shift arrays. So this is about shift rows. And after applying the shift rows, next we have to perform mixed columns. The next process is mixed columns. Mixed columns. So initially, again, consider the mixed columns. So take the state array. So this is the output for the shift rows, and this output will be considered as input to the mixed columns. Consider this and consider each column as one word, and take one word and apply the multiplication operation with the predefined 4x4 matrix, and we will get again a one word which is again stored in the state array. So here the predefined matrix is 2 3 1 1 1 2 3 1 1 1 2 3 3 1 1 2. So this is the this one is the matrix, and consider each column and perform the multiplication. So it is 4 by 4 and it is 4 by 1. So if you apply the 4 by 4 order with 4 by 1, the constraint for applying this matrix multiplication is the columns of first matrix should be equal to rows of second matrix. So the columns of first matrix is equal to rows of second matrix. The constraint is satisfied, so we can perform this matrix multiplication, so that the resultant matrix will be 4 by 1. So we will get again 4 by 1, which is again stored in state array. So this we have to consider from, this is one word and this is also one word. That means each column. See, so each column is considered as one word. Apply with the predefined matrix. So we will get again a 4 by 1, which is again stored in first column of the resultant state array. Consider the second one. Apply the multiplication, stored in the second column of resultant array. Third column, apply the matrix, stored in third column of resultant matrix, resultant array. And the fourth column, again perform the multiplication and save in the fourth column of the resultant array. So in this way we have to apply the mix columns. So after applying the mix columns, again the state array, that means the result from this mixed columns will be given to the add round key, where we have to add 4 keys. So here the next process is add round key. So where we are adding, here adding means XOR, right? Here adding means performing the XOR operation. XOR operation with state array, which is output from mix columns XORed with key. So which is again 4 words. So again consider a column as one word. Consider one word from state array and first word in the key, perform the XOR operation. So I will show that. See here. So consider, so this is the state array, that means the output from mixed columns. The output from mixed columns. So consider this first column as one word, XOR with the first word of key and stored in the first column of the resultant array. Consider the second column as a second word, XOR with second word of key and stored in the second column of resultant array. Third column as a third word, XORed with the third word of key and stored in the third column of the resultant array. Consider the fourth column as one word, fourth word, and XORed with the fourth word of key and stored in the fourth column in the resultant array. So here in each round we are using 4 words. So as we have seen in the first diagram, see here. So in the first round we are applying from word 4 to word 7. So here 4 words in each and every round we are using 4 words. So in the state array also we are using 4 columns, each column considered as a one word. So XOR each column with each word and store in the resultant array. So after applying this round key, the first round will be completed. So we have to repeat all these 4 steps in 10 rounds, 10 times. And in the 10th round, we need not apply the mixed columns. So before applying to the first round, first we have to add the key. That means 0 to 3. Word 0 to word 3, we have to apply the add round key. So hope you understood this. So initially we are using add round key 0 to 3, and round 1 words from 4 to 7. Similarly in the round 10 we are applying words from 40 to 43. So total 44 words we are using in our AES algorithm. So briefly I will explain once again so that you will not get confused. So first, take the plain text 128-bit, apply the add round key where we will apply the 4 words, and then the output from this will be given as input to the substitution bytes, which is called S box, and the output from this S box is given to shift rows, and the output from shift rows is given to mixed columns, and the output from mixed columns is given to add round key. So coming to this S boxes, so consider the S box. Consider the S box. Here the S box, the input for the S box is 8 bits and the output from the S box is 8 bits. So in that 8 bits input, first 4 bits will be considered as row column, and the next 4 bits are considered as a column number, row number and a column number. So we will get the corresponding value, and again we have to convert it into 8-bit representation. So similarly, we have to consider each 8 bits and convert it, and again store the result in the resultant state array. So this is the S box. So after applying the S box, the output will be given as input to the shift rows. So it depends upon the row number, we have to apply the circular right shift. So row 0 bits will be shifted, and first row 1 bit will be shifted, second row 2 bits will be shifted, and the third row 3 bits will be shifted. So after applying this shift operation, we have to give the input to the mixed columns. So here in the mixed columns, again we have to apply we have to consider each word and perform the multiplication operation with the 4x4 predefined matrix, and we will get 4x1 resultant, which is stored in the first column of resultant matrix. So similar in the same should be repeated for every word. So after applying these mixed columns, we have to apply the add round key. So here we have to apply the 4 words XORed with each word in the resultant array. So consider each word, XOR with each word, and store it in the each column. So consider this column as one word. So I am once again repeating, consider the column as one word. Consider the first word XOR with word 0, and the first word of the key. In the key we are using 4 words. The first word of the key and resultant word will be saved in the first column of the resultant array. So this is an example for S boxes. So here the S box, in the S box there are 4-bit representation for row number and 4-bit representation for column number. That means 16 columns and 16 rows will be there. So total 256 entries will be there. And similarly, first find out the row number, find out the column number, and find out the corresponding value and convert it into equivalent binary, which is 8 bits. And initially the input is stored in input array and the output is stored in output array, and the intermediate results will be stored in state arrays. Right? So hope you understood this AES algorithm. Don't get confused. So once again, just go through the video, and if you are having any doubts regarding this AES algorithm, feel free to post your doubts in our comment section so that I will try to clarify your doubt early. Hello friends, welcome to our channel. So in today's session, let us have a look on one more algorithm related to asymmetric key encryption. So in the previous sessions we have seen 2 algorithms, the data encryption standard DES algorithm and advanced encryption standard, that is AES algorithm. So both the algorithms are related to the symmetric key encryption. So the symmetric encryption means whatever the keys we are using at the encryption side, we have to use the same keys on decryption side. So here in today's session, let us have a look at an example algorithm for asymmetric key encryption. So in the asymmetric encryption, there will be two keys. One is public key and another one is a private key. The name itself indicates the public key is public to all the users in the network. So for every user in the network will be having both the keys, public key and private key. So here the public key is public to all the users in the network, and private key should not be shareable between all. So it must be kept secret. So the only user can use this private key. So if one key is used at encryption side and we have to use the other key of same pair at the decryption process, so that we call it as asymmetric encryption. So for every user there will be public key and a private key. If the public key is used at encryption, we have to use a private key of the same user in the decryption process. So let us have a look on algorithm, that is RSA. So this is the RSA algorithm, which is an example for asymmetric key encryption. Here we have to find both the public key and private key, and one key should be used at encryption and the other key should be used at decryption. So for this process we have to consider, first we have to consider the two prime numbers. Consider two large prime numbers let us say it as P and Q. P, Q. So here P, Q are two large prime numbers. So this is very important. Large prime numbers. In order to be this algorithm very secure, we have to use the large prime numbers. Next, after considering this P and Q, calculate N, which is equal to P into Q, the product of two prime numbers. Then calculate phi of n, that is Euler's totient function. Euler's totient function. So P minus 1 into Q minus 1. So Euler's totient function phi of n is equal to P minus 1 and Q minus 1. So I will explain about this Euler totient function once I have completed this RSA algorithm, writing this RSA algorithm. So after calculating this phi of n, now we have to calculate or find the public key and a private key. Now assume E. E means a public key which we have to use in encryption side. Assume E such that the GCD of E comma this Euler's totient function phi of n should be equal to 1. So in other words, we can say it as we have to assume E such that E should be a co-prime to phi of n. Co-prime. So in other words, we can say that we have to assume E, we have to select the E such that the GCD of E comma calculated phi of n, that is the Euler's totient function, should be equal to 1. Next, so after finding out this E, now we have to calculate the decryption, I mean private key which is used at decryption. That we represent it as D. Assume D such that equal to, D congruently modulo of, congruent equal to e power minus 1 mod phi of n. D congruent equal to, I have mentioned here triple lines. So if we write double line, it is called equal. Triple line, it is called congruent modulo. It is called congruence modulo. Now, so from this we have to find out the E. So in order to convert this congruent modulo into is equal to, so we have to apply the mod operation on both sides. So I will simplify this. D into E congruent modulo of 1 mod phi of n. So this becomes equal to, once you multiply mod on both sides. So apply this mod operation. D E mod phi of n is equal to 1 mod phi of n. So this always equal to 1. 1 mod phi of n is always equal to 1. So this can be written as D into E mod phi of n is equal to 1. So we have to assume D value such that D into E mod phi of n is equal to 1. So I will replace this one with this simplified one. So I am converting the congruence modulo 2 is equal to D into E mod phi of n is equal to 1. So I have to find out the value of D. Now, after calculating this E and D, now we had the public key and a private key. So here the public key is encryption comma n, and private key is the decryption comma n. Right? So after finding out this one, at the encryption side, we will get the ciphertext. Right? So we have to select them, we have to consider the plain text message that must be less than 1. So plain text message which is less than small n. And convert, so find out the ciphertext. Ciphertext is equal to plain text power E mod n. So this is a formula to find out the ciphertext. We will get the ciphertext. Next, at the decryption process, we have to convert the ciphertext to the plain text. So we will get the plain text. Plain text is equal to ciphertext power D mod n. Plain text is equal to C power D ciphertext power D, that is a private key, mod n. So like this we have to calculate the ciphertext and the plain text. So here first of all we are generating the keys, public key and private key. So this is called a key generation. So all these steps are key generation. So once these keys are assumed, then we have to do the encryption process. And after this encryption process, we will get the ciphertext, and this ciphertext should be decrypted in the decryption process to the plain text message. So in this process, we are using encryption, public key in the encryption and private key in the decryption. So one key we are using at the encryption side, the other key we are using at the decryption side. So that's why we call this algorithm as an example for RSA, that is asymmetric key encryption algorithm. So hope you understood. So once again, this very important is we have to consider the large prime numbers. So we can consider very small prime numbers like 3, 5, 7 and all these things. So if you find these large prime numbers, then that implies our algorithm is more secure. So it is not vulnerable to the brute force attack. The possibilities are very less. The attacking possibilities are very less. So we have to consider the large prime numbers. So once again I will repeat. First we have to consider the large prime numbers P and Q, and then we have to calculate the product of two prime numbers N, and then we have to calculate phi of N, that is Euler's totient function. So here I have to explain the Euler's totient function. So see, Euler's totient function of 10, for example, let us take this 10. So we have to write the numbers from 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. These are the Euler's totient functions. So write down the factors of 10. Factors of 10, that is 2, 5. Now cross over all the multiples of all the factors. That means 2, 4, 6, 8, 10. Then 5. 5 and 10. And count the remaining 1, 2. So this is 1, 2, 3, 4. So Euler's totient function of 10 is 4. So once again I am saying that Euler's totient function, finding the Euler's totient function means first write down the numbers from 1 to given Euler's totient number, then write down the factors and cross the multiples of all the factors. So count the remaining, that will be the value of Euler's totient function. So for this, simply if the number is prime, that means if you want to find the Euler's totient function for a prime number, see, if for example 5, we have to find the Euler's totient function for the number 5. That means I have to write all the numbers from 1 to 5, write down the factors 5. So cross out the multiples of factors. That means 1, 2, 3, 4. So because the prime number will be having only the factors 1 and itself, so that number we are crossing, so only 4 numbers will be considered as Euler's totient function of 5. So that's why we can simplify as Euler's totient function of P is equal to P minus 1 if P is a prime. If P is a prime. So for prime numbers, the Euler's totient function is P minus 1. So hope you understood this Euler's totient function. Here we are considering P into Q, that means P is a prime number and Q is a prime number. So Euler's totient function of M is P minus 1 into Q minus 1. So like this we have to find this Euler's totient function, and then from this Euler's totient function we have to calculate the value of E, which is a public key, and then we have to calculate the value of D, which is a private key. And the public key is E comma N, private key is D comma N. At the encryption process, we have to convert the plain text into ciphertext. So ciphertext is equal to plain text power E mod N. Here E is a public key. And at the decryption, here we are using the public key. So in the decryption, we have to use the private key. For that purpose, we have, so decryption means the conversion of ciphertext to plain text. So the result is a plain text message. So message, plain text message, M stands for plain text message, C stands for ciphertext. Plain text message is equal to ciphertext power D, which is a private key, mod N. Right? So hope you understood this RSA algorithm. Now let us look at simple example so that you can clearly get it. See, for simple calculations, I will consider small numbers, but in order to be this RSA more secure, we have to consider the large primes. So let it be P is equal to 3, Q is equal to 5. Now N is equal to P into Q, which is 15, and phi of N is equal to P minus 1 into Q minus 1, which is equal to 2 into 4, that is 8. So phi of N is equal to 8. So after calculating this Euler torsion function, we have to find out the public key and the private key. So I have to find the public key. So the GCD value of E comma phi of N should be equal to 1. So I will assume here E as 3. So we can assume 3 or 5 or 7, anything. So for 3, 5, 7, we will get the GCD for all these three values 1. So GCD of 3, 8 is 1. GCD of 5, 8 is 1. GCD of 7, 8 is also 1. So I will consider 3. Let us consider 3 as a E value. So E is equal to 3. Now I have to find out the D value. So in order to find the D value, so D into E mod phi of N should be equal to 1. So that means D into 3 mod 8 is equal to 1. So we will get, so here we will get, let us take here 3. 3 into 3, that is 9. 9 mod 8. 9 mod 8, which is equal to 1. So we can consider these as 3. So moving on to the other numbers, we can also find some other number which satisfies this condition. So here I am considering this 3, simple 3 as a D value. So here D value is also a 3. So if you consider the small numbers, as I have said, that the security is very less, because here we can observe that public key and private key are equal. So if the public key and private key are equal, so it is easily vulnerable for the attacker. So if you consider the large numbers, definitely you can get the different value for D value. So for simple calculations, I have considered the small values. So once you check with the large numbers using a calculator, and if you find any difficulty, please let me know the values so that I will solve your clarify your doubts. So here E is equal to D and 3 and D is equal to 3. So here the public key is equal to E comma N, which is equal to 3 comma, here N is 15, and private key is equal to D comma N, which is equal to 3 comma 15. So here both the public key and private key are 3. Next, at the encryption side, consider plain text message as 4. So I have to convert the which is less than N. Ciphertext is equal to plain text power E mod N, that is equal to plain text 4 power E is 3. 3 mod 15. Here 64 mod 15, which is equal to 4. 15 fours are 60, so 4 will be the remainder. C is equal to 4. The ciphertext is also 4. And then at the decryption process, consider the plain text message is equal to C power D mod n, which is equal to again 4 power 3 mod n. So mod n means here 15. 4 power 3 mod n. So here the ciphertext is also here 3. So 4 power 3 mod 15, which is again equal to 64 mod 15, which is equal to 4. Here again plain text is equal to 4. So which we have considered in the encryption process. So plain text is equal to 4, ciphertext is equal to so and so, and at the decryption also we got the 4 value. So this is only for the simple values. So once you try with the large primes, so consider P is equal to some 11 and Q is equal to some 19, and do the problem using the calculator, so that you will get the plain text message in the decryption process. Right? So hope you understood this simple RSA algorithm, very important algorithm. So this is an example for asymmetric key encryption algorithm. So 2 keys will be there, 1 key will be used at encryption and the other key will be used at decryption process. So in this today's session, let us have a look on one more algorithm which is used to exchange the secret key between two users. So as we know, the symmetric encryption means whatever the keys we are using in the encryption process, the same keys should be used in decryption process. That means the secret key which we are using in the encryption process, we have to send securely to the receiver. So how this secret key is shared between two users in the symmetric encryption? The one way is by calculations we can generate the secret key at the sender side and the receiver side. That we call it as Diffie-Hellman key exchange algorithm. So the name itself indicates key exchange. So exchanging the secret key between user, a sender and receiver. And for this exchange we will use the asymmetric key encryption. So Diffie-Hellman key exchange algorithm is used to exchange the secret key between sender and receiver by using symmetric encryption techniques. Right. So in today's session, let's have a look on Diffie-Hellman key exchange algorithm. So Diffie-Hellman key exchange. This is also a very important algorithm. The first point we need to remember is this is not an encryption algorithm. It's not an encryption algorithm. Second point. This is used to exchange the key. Exchange secret or symmetric key between sender and receiver. And the third one is you make use of, and this will be happen with the use of symmetric encryption. So asymmetric encryption. That means in order to send the secret key, exchange the secret key between sender and receiver, we will use public key and private key. So by the calculations done on this public key and private key, we can generate the secret key at the sender side and as well as at the receiver side. Now let's move on to the algorithm, actual algorithm. So as in the RSA algorithm, here also first and foremost step is we have to consider a prime number. The first step. Assume prime number Q. Prime number Q or P, whatever it may be. Next, after assuming the prime number, select alpha such that alpha must be primitive root of P. Oh, sorry, Q. Here we have considered it as a Q, right? So alpha should be primitive root of Q and alpha should be less than Q. So two conditions to be satisfied. One, the alpha which we are selecting must be primitive root of Q, and second one, it must be less than Q. First, what is meant by primitive root and how to get this primitive root? So A mod P, let us consider A mod P. Oh, sorry. So A is primitive root of P if A mod P comma A square mod P comma A cube mod P comma and so on A power P minus 1 mod P gives the results 1, 2, 3 and so on P minus 1. So once again I am repeating, A is a primitive root of P if A mod P comma A square mod P comma A cube mod P and so on A power P minus 1 mod P should give the results 1, 2, 3 and so on P minus 1. So we have to get all the values from 1 to P minus 1. So the value should not be repeated in the result. So if this condition satisfies, we call A as a primitive root of P. Right? So I will explain you how to find the primitive root when we see the problem. Right? So first, assume the prime number Q and select alpha such that alpha is a primitive root of Q and alpha should be less than Q. Then, hope you understood this primitive root, how to find the primitive root and what is exactly the primitive root. So if you see the example, you can get an idea of primitive root. Next, after selecting alpha, next, assume XA, which is a private key. So XA is a private key and it should be less than Q, and this is a condition. Again, we can consider any value. It is a random number, right? So it's a private key. Assume XA. Now calculate the public key. So XA refers to private key of user A. Private key of user A. Now calculate YA, which is public key of user B. YA is equal to alpha power XA mod Q. Next one, assume XB, so that XB is a private key of user B. Private key of user B, and here also XB should be less than Q. This is the common constraint, right? Next, calculate YB, which is the public key of user B. That means YB is equal to alpha power XB mod Q. Now we had XA comma YA, which is public key and private key. So this refers to public key, private key, and this refers to public key. And here we had XB comma YB. This refers to private key of B, and this refers to public key of B. So after the four steps, we had a prime number and a primitive root and a public key and private key of A and a public key and private key of user B. Now the next step is key generation. So how to generate the secret key at the sender side and at the receiver side. So I will just erase this first two steps. I will write here Q is a prime, alpha is a primitive root, and alpha should be less than Q, right? Then now the key generation at user A and user B. This is the key generation. A side and B side. At the A side, so as we know, we are having both the public key and private key of user A and the public key and private key of user B. And we know that the public key will be available for all the users and the private key should not be shared. So that's why at the sender side, A, the key generation K is equal to public key of B. So this will be available for user A also, right? YB power private key of A mod Q, right? So here YB, I am using the public key of receiver and the private key of user, sender. Here also secret key K is equal to public key of sender power private key of receiver mod Q. So this is the key generation, calculation of key generation. So K is equal to YB power XA mod Q. K is equal to YA power XB mod Q. Here YB is a public key of user B, so which is available in the network. And here YA is a public key of user A, which is available in the network. And XA is a private key which is not shared. So XA is used at the sender side itself. and XB is also a private key which is not shared, so XB is used at the receiver side itself. So finally we have to get the values of K at both user A and user B must be equal. So after calculating all these things, we should get both the K values equal. Then only we can say the exchange is successful. So as we said that in the symmetric encryption, whatever the key we are using at the encryption side, we have to use the same key at the decryption side. So here we are exchanging the key. So we are not exchanging the key, just we are generating the key on both the sender and receiver side. So which is getting an equal value by a simple calculations. So hope you understood this algorithm. First step, we have to select the prime number Q, and then in the second step we have to find or assume the primitive root alpha, which is a primitive root of Q, and it must be less than Q. And then we have to assume the private key and calculate the public key of sender. And in the next step we have to assume the private key of receiver and public key. We have to calculate the public key of the receiver. And by using this public key and private key of sender and receiver, we will generate the key at both sides, at the sender side and the receiver side. So here A means sender side, here B means receiver side, sender side and receiver side. So hope you understood this algorithm. Now let us have a look on a simple problem so that you can get a clarity about this primitive root, how to select that primitive root and how this K will be equal. So without any sharing, only by generating, only by calculations, these both the K values will be equal. So let us start the example problem. So now let us see the example for RSA algorithm. So first I have to consider the prime number, which is Q. Here I am considering Q as 11, which is a prime number. Now in the second step I have to consider the alpha, which is a primitive root of Q. So as I have said that if alpha is said to be a primitive root of Q if alpha power 1 mod 11, alpha power 2 mod 11 and so on, alpha power 10 mod 11 gives the result from 1, 2, 3 and so on 10. That means all the numbers from 1 to Q minus 1. So we have to get the result as all the numbers which are unique numbers. That means we should not be repeated. We have to get all the numbers, every number from 1 to Q minus 1. So such number we call it as a primitive root. So in the second step we have to find the primitive root of Q. So how to find this primitive root? See, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Similarly 3, 4, 5, 6, 7, 8, 9 and 10. So this implies the number, so which we are selecting the primitive root, and this represents power. Here we have to find mod 11. So first consider the number 1. 1 power 1 mod 11, which is equal to 1. 1 power 2 means 1 square mod 11 is equal to 1. So for 1 we will get all the values as 1s. So this condition fails for 1 because there is a repetition and we didn't get any number other than 1. So 1 is not a primitive root of given number 11. Now consider 2. 2 power 1 mod 11, which is equal to 2. 2 square, that means a 4 mod 11, which is equal to 4, 2 cube. So 8 mod 11, which is equal to 8, 2 power 4, 16 mod 11, which is equal to 5, 2 power 5, 32 mod 11, so 32 mod 11, so that means 2s are 22, the remainder is 10, so here we get the 10. 2 power 6 means 64, 64 divided by 11, I mean 64 mod 11 means 5s are 55, the difference is 9, so remainder is 9, so the value will be 9. And 7s, 128, 2 power 7, 128 mod 11. So 11 ones are 11, and here we got 18. So again ones are 11, the difference is 7. So we got a 7, right? Next, 2 power 8, that means 256 mod 11. So 11 2s are 22, 36, 3s are 33, the difference is 3. So the result is 3. Now 2 power 9, that means 512, which is we have to check 512 mod 11. That means 5 4s are 44, 72, 6 are 66, the difference is 6. So here we got 6. Next, 2 power 10, which is equal to 1024 mod 11. So 11 ones, so 11 nines are 99, 34, 3s are 33, we got the difference 1. So 1 is the difference. So if you observe these values of number 2, we got each and every number from 1 to q minus 1. That means 1 from 1 to 10 without any repetition. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So in such case, if we get this result, that means it satisfies the condition. So that implies 2 is a primitive root of 11. So if you find this 3 power 1 mod 7, mod 11, which is equal to 3, 3 square, 9 mod 11, 9, 3 cube, 27 mod 11, so 2, 27 mod 11, so 2s are 22, which is equal to 5, 3 power 5, 3 power 4, that means 81, 11, so 7s are 77, which implies a 4. So likewise, we can calculate the mod values for all the numbers from 1 to 10. So we may get more numbers which are primitive root of 11. So we may get 3 as a primitive root, and 5 as a primitive root, or 7 as a primitive root. So whatever the primitive roots we got, we can select one among all those things as alpha. So here I am selecting 2 as a primitive root. So I am not calculating all the values. So you can calculate all the values, and you can find the primitive. First you can find the primitive roots of 11, and you can select one among those primitive roots as alpha. Here I am selecting 2 as primitive root, because for 2 the power of 2 mod 11 gives the result from 1 to q minus 1, that means 10. Now, so after calculating or after finding the primitive root of 11, now select XA, that means private key, which is 8. So here the condition is it must be less than q. So I can select any number which is less than q, just assume. So XA, I have selected XA, which is equal to 8. Now I have to calculate the public key, YA, public key. So this is the private key. I have to calculate the YA public key, which is equal to alpha power XA mod q. So alpha is 2 power XA. So here XA is 2 power 8 mod 11. So this value we can observe from the previous table, or we can find it. So 256 mod 11, So 2 power 8 is 256, right? Mod 11, 11 2s are 22 and 36, 3s are 33, so we got a 3. YA is equal to 3. And next, select XB, which is a private key, so this is a public key. Next, select XB, which is a private key of user B. I will select it as 4. Here also the condition is it must be less than Q. I will select 4 as a private key of user B. So this is a private key. Now I have to calculate public key. YB is equal to alpha power XA mod Q. So which is alpha here 2 power 4 mod 11. So 2 power 4 means 16 mod 11. 16 mod 11 means YB is equal to 16 mod 11 means 5. Which is a public key. Right? So first I have selected XA, that means a private key of user A, which must be less than Q. We can select any number. I have selected 8 and I have calculated the public key using the formula alpha power XA mod Q. So I got the number 3 as a public key of user A. So let us write here user A, the public key is YA is equal to 3, XA is equal to 8. So this is the public, this is the private. Next, user B, YB is equal to 5, XB is equal to 4. Here it is a public, here it is a private. Now we have to calculate the secret key at both the sender side and receiver side. So this is the sender side. This is the receiver side. So that means here A, here B. So as we know that the public key is available as a public for all the users in the network. So A can know the public key of B and B can know the public key of A. Now here the formula I have written is K is equal to public key of B power private key of A, which is not shared, mod Q. Here also K is equal to public key of A power private key of B mod Q. So let us calculate YB. So YB is 5 power XA 8 mod 11, and here also YA 3 power XB 4 mod 11. So we have to calculate this and we should get the equal, K as equal. See here 5 power 8, calculate the 5 power 8, that means 5 square 25, 25 into 25, 625. So 625 into 625. So we have to calculate the 625 into 625. So 5, 2, 5 to 10, 12, 2, 1, 5, 6, 30, 31, 2, 5 is 10, 2, 5, 12, 6, 5 is 30, 6, 2 is 12, 15, 6, 36, 31, sorry, 36, 37. So 5, 2, 6, 0, 1, so 9, 3. So this is the value of this one. So 39 0 6 2 5 divided by 11. So 11 3s 33. So we got the value 60625, 5s 55, 5625, again 5s 55, 125, 1s are 11, 15, again 1s are 11, so 4. We got the 4 as a reminder. So 11 into 35511 will be the result 390621. The remainder is 4. So we got the remainder as 4. So just I have calculated the 5 power 8 mod 11. So I got the remainder as 4. So at the sender side, the key value is 4. And we should get the same value at the receiver side, because in the symmetric key encryption, as we discussed in the previous sessions, so symmetric key means whatever the key we are using at the encryption, the same key should be used at the decryption. So here, by using the public key and private keys, we are exchanging the secret key from sender and receiver, in between the sender and receiver. So here also 3 power 4, 9 9s are 81, so 81 mod 11. So 11 7s are 77, automatically k is equal to 4, which is equal to the key value which we have calculated at the sender side. Right? So in such way we have to exchange the secret key just by doing the calculations and by using the public key and private key of sender and receiver. So I will give once again I will just give a brief overview. First we have to select the prime number q, and then in the next step we have to select the primitive root, so that the primitive root power of 1 to q minus 1 should give the results from 1 to the numbers from 1 to q minus 1 without any repetition. We have to get all the numbers, and then in the third step we have to select the private key of user A, and from that private key of user A we have to calculate the public key of user A by using this formula alpha power xa mod q, and then we will get the public key. Now user A, at the user side, at the user A we have the private key and the public key. Same you have to repeat for the user B. So that means assume or select the public key of, private key of receiver, and based upon the private key of the receiver calculate the public key of the receiver YB. Now here also we got the public key and private key of user B. So after getting all those 4 keys, public key and private key of both user A and B, now at the sender side you have to generate the key, that means calculate the key. So k is equal to public key of B, which is available for all the users, while public key of B power private key of A, which is not shareable, mod q. And at the receiver side we use the formula public key of user A power private key of user B mod q. So if you calculate this key, we will get the same key, so which we call it as the symmetric key. The key is exchanged between sender and receiver for the secure, for symmetric encryption. So that's why we call it as key exchange algorithm. So once again I am repeating. So in the previous sessions we have seen the 3 algorithms. All the 3 algorithms are the encryption algorithms. That means conversion of plain text to ciphertext. And today's algorithm is not an encryption algorithm. This is just to exchange the secret key from sender to receiver. So in order to perform the symmetric key encryption. So in the previous sessions we have seen the various encryption algorithms related to symmetric encryption and asymmetric encryption. So in those we have seen first the DES algorithm and AES algorithm, which are related to the symmetric encryption, and then we have gone through the RSA algorithm, which is an asymmetric encryption algorithm. So these algorithms are meant for conversion of plain text to ciphertext, and that is for achieving the confidentiality. So which is one of our security service. So that means providing the security for the data. So in today's session, let us have a look on another security service, that is authentication. So as we have discussed in the previous sessions, the authentication means verifying the user identity. So if a network consists of 4 different users, let it be A, B, C and D. So in this network I had 4 systems or 4 users, A, B, C, D, and if A wants to communicate with C, A should communicate with C. That means, first of all, this C should be authenticated by A and A should be authenticated by C. That means C must know that the message which have been received is coming from the perfect sender. So the authorization, that means all the 3 users are having permissions to communicate with each other. So that we call it as an authorization. And here the authentication means verifying the user identity. So among these 3 users, C should receive the message only from A. So that identity is called authentication. So similarly, A should send the message only to C. So A should authenticate it by C and C should be authenticated by A. So this is called authentication. So this is one more service of our security. So here first let us see the different types of authentications. First, types of authentications. So there are mainly 3 types of authentications. First one is message encryption. Next, message authentication code. And the third one is hash functions. So coming to this message encryption, the ciphertext. The ciphertext will itself act as an authenticator. So the sender should be authenticated by the receiver, and similarly the receiver should be authenticated by the sender. And this process will be done only through the ciphertext. So that's why we call it as authenticator. So here the ciphertext itself acts as an authenticator. In this message authentication code, we will have some authentication functions. So we have to apply these authentication functions on the plain text along with the key, which produces a fixed length code that is called message authentication code. So consider the plain text, apply the authentication function along with the key. So here C represents the authentication functions. So C of M comma K, M stands for a plain text message and K stands for a simple key. So applying the authentication functions on plain text message along with the key will produces a fixed length code. Fixed length code, which we will call it as MAC, that is message authentication code. So the output of this message authentication code is MAC. This can also be called as message digest message digest, right? So this is a fixed length code, and this will be acting as an authenticator here. So in the second function, I mean in the second category, there is message authentication code, we will get an fixed length code which is a MAC or a message digest which acts as an authenticator. So in order to in order to authenticate by the sender or a receiver, we have to use this fixed length code. And coming to the third one is also similar to the message authentication code. Here we will apply hash functions. So capital H represents the hash functions. So applying these hash functions on a plain text message, that is M, which is independent of key. In the second case, we are using the key. So this message authentication code depends upon the key, and in this hash functions is independent of key. So we should not use the key for generating the authenticator. So hash functions, applying the hash functions on the plain text message will also produce the fixed length code, which is also called as hash code. It is represented as H, small h. So here the capital H represents the hash function, small h represents the hash code, and this fixed length code will act as an authenticator. So if the sender wants to authenticate by the receiver and the receiver wants to authenticate by the sender, excuse me, we have to use this hash code. So these are the three categories of authentications, three ways we can achieve the authentication: message encryption, authentication code, and hash functions. So let us see how this ciphertext acts as an authenticator, and here how this MAC acts as an authenticator, and here how the hash code acts as an authenticator. Let us look one by one. First, message encryption. So here the ciphertext is an authenticator. So in the first case, let us see in the symmetric, and then we will go to the asymmetric. Consider the plain text message. So this is the plain text message. Apply the encryption algorithm. So use the key. This is symmetric. So we have to use the same key at the decryption, right? So after applying the encryption, we will get the encrypted message, and then at the receiver side decrypt this encrypted message using the same key, so that we will get the plain text message. So here we have to share this secret key securely between the sender and receiver. So this is the sender, this is the receiver. Right? So the key will not be shared among the different persons. So here the ciphertext only acts as an authenticator. So this is the symmetric encryption. Coming to the asymmetric encryption, if you consider the plain text message, encrypt this with public key of B for receiver. Let it be A, B, public key of B, so that we will get the encrypted message and decrypt it. So if we encrypt with public key of B, we have to use the another key of same pair. Here we are using the user B public key. So here we have to apply user B private key, right? So that we will get the plain text message. So here at the encryption side, we are using the public key of user B. That means the public key of B is available with all the users in the network so that any person can encrypt the message and send to the receiver. That means, so here the confidentiality is achieved, but authentication is failed. So A is not authenticated by C. Now the third one. So in order to avoid this, so hope you understood, at the sender side anyone can send the message. At the receiver side only the B can receive the message, because here we are using the private key of B which is not shared. So that means authentication fails, only the confidentiality is achieved. So in the third case, if we apply here the private key of A, so that encrypted message will be appeared, and at the decryption side if we decrypt, so here we are using the private key of user A, here we have to use the public key of user A, so that we will get the plain text. So in this case authentication is achieved, confidentiality is achieved, authentication is failed. In this case, see, here at the sender we are using the private key so that the message will be sent only by the user A. That means user A is authenticated, but at the receiver we are using the public key of A which is available with all the users in the network. So anyone can decrypt the message. So here authentication is achieved, signature is achieved, but confidentiality is failed, because here there is no secrecy, there is no security, because at the receiver side anyone can decrypt this message, because here we are using the public key. So in this case authentication is achieved, but confidentiality is not achieved. It fails the confidentiality. Here authentication fails and confidentiality is achieved. So in order to get both the authentication and confidentiality in asymmetric, we have to apply the dual encryption. So at the sender side we will use two encryptions, and at the receiver side also we will use two decryptions. So in order to achieve both authentication and confidentiality. So in all these cases, this ciphertext only will act as an authenticator. So let us see the third case, which is in which we will achieve both the authentication and confidentiality. See, plain text message. First encrypt it with private key of A. We will get the message which is encrypted using private key, and then again encrypt with public key of B, so which is available with all the users in the network, so we can use the public key of receiver. And here we will get one more encryption So in the reverse, in the receiver side, first decrypt. So recent encryption is with KUB. So first we have to decrypt this message with KRB, because the recent decryption is KUB. So I mean recent encryption is KUB. Here recent decryption must be, the first decryption must be using KRB. And after getting the encrypted message, again decrypt using the second one is KRA. Here we have to use KUA, so that we will get the plain text message. So here in this case we can achieve both authentication and confidentiality, because at the sender side we are using the private key of sender which is not shared, so that compulsory the sender will send the message. And again we are encrypting the encrypted message using a public key of B, so that at the decryption first we have to decrypt the received message with private key of B. So here also we are decrypting this message with private key which is not shared, only the receiver can receive, and the receiver can decrypt the message in the first level. So after that we will get the another ciphertext, inner ciphertext, so which can be further decrypted by using public key of A. So sender is authenticated and receiver is also authenticated. So only sender can send the message, here only receiver can receive the message. So this case will achieve all the authentication, confidentiality and also signature, because at the receivers, at the sender side, we are encrypting the message using the private key of sender. So that's why we call it as it achieves the signature. So this is the first type of authentication, that is message encryption, where here we didn't use any separate functions and any separate keys, just a ciphertext only will act as an authenticator. Right? So this is the first type of authentication, message encryption. Now let us move on to the second one, that is message authentication code. The second one is message authentication code. So here we have to apply, here MAC will act as an authenticator. So we have to generate that MAC. So in order to get that MAC, we have to apply the functions on plain text message along with the key. So C must be applied on message along with key, which gives MAC, and which acts as an authenticator. So here consider the plain text message. Apply the functions along with key, so that we will get one code which is appended with the plain text message, so that we will get plain text message and MAC. So here we will get MAC. So we are applying the functions along with the key on plain text message, which gives the MAC, which is appended with the plain text message. So this is plain text message. Right? So this will be sent to the receiver, and at the receiver again the same functions will be applied on the message along with the key, so that again MAC will be generated, and this appended MAC and a generated MAC will be compared. So hope you understood this. Consider the plain text message, apply the authentication functions, message authentication functions along with the key which generates the MAC, and append this fixed length code. Here this MAC is a fixed length code. So append this fixed length code with a plain text message, so that plain text message and MAC, and send to the receiver. At the receiver side, again apply the same authentication functions with the same key, so that again we will get the MAC, and the appended MAC and calculated MAC will be compared. So if both are equal, that implies the message has been received successfully from the perfect sender. And also integrity. Integrity means in between the transmission, the data is not modified. So this implies the data is not modified in between the transmission. So if the data is modified during the transmission, even a change in a single bit will get the difference of this calculated MAC and generated MAC. So these two will not be equal. So if any one bit change in the plain text message will gives the result of this MAC mismatch. So if we get this MAC mismatch, that implies the data is modified or the data is not coming from the perfect sender. So here we are using this MAC, which is called authenticator. So here this MAC is used to authenticate the sender by the receiver, and also vice versa. So in this case, we have achieved the authentication, but there is no confidentiality, because here the plain text message is transmitted only in the form of plain text message. Here no encryption has been done. So we are applying the key with the MAC functions, message authentication functions, right? So here we are not performing any encryption process. So that means the transmission, the bits will be in the plain text format. So there might be a chance that anyone can modify the message during the transmission. So there is no security for the data. So there might be a chance to change the MAC also. So that means authentication is achieved, but there is no confidentiality. So for that, we will just add the confidentiality. Consider the plain text and apply the same functions. K is applied so that we will get the MAC, and append this MAC and apply the encryption process. Use a symmetric key. So here the K1 and K2, and send to the, so see, so this is the MAC and this is the plain text which is encrypted using the K2. So that first the decryption process will be done by using the same K2, and then we will get the plain text message and MAC. Now apply the same functions K1 so that MAC will be generated, and compare this appended MAC. Hope you understood. First, consider the plain text message, apply the MAC functions along with the key K1 so that we will get a MAC. So this is the MAC and this is the plain text. So append the message with the plain MAC and encrypt that message with K2 so that we will get the encrypted format, and send to the receiver. At the receiver side, first decrypt this encrypted message using K2 so that we will get the message and MAC, and now apply the message authentication functions along with the key on plain text message so that MAC will be generated. Now this MAC and the generated MAC will be get compared. So here also same process. So two MACs, that means generated MAC and a calculated MAC. Calculated MAC and appended MAC should be equal. So if both are equal, that implies the data is transmitted or sent from the perfect sender. So that means sender is authenticated by the receiver. So there is another form to achieve this authentication. So this is right. So let us see another format. So this is authentication tied to plain text. So authentication tied to plain text. That means we are applying this authentication functions on the plain text. So authentication is tied to plain text. So if we change this, there is one more format. So first consider the plain text message. Now immediately apply the encryption with K2 so that we will get the encrypted message. Now apply the functions with K1 and append both. See, so this is the plain text message which is in an encrypted format, and this is the MAC. And at the decryption, so send this to the receiver. So at the decryption, first apply the functions using K1 so that we will get the MAC and compare. Apply the decryption process using K2 so that we will get the plain text message. Right? So here first we have to apply this function with the K1 so that we will get the MAC and appended MAC, and this generated MAC will be compared, and similarly the encrypted message will be decrypted by using the K2 so that we will get the plain text. So this is called authentication tied to ciphertext. So because first we are generating the ciphertext and then applying the functions on the ciphertext. Here we are applying the functions on the plain text message. So that's why we call it as authentication tied to plain text and authentication tied to ciphertext. So this is the second process. So here first we have to generate the fixed length code by applying the message functions on the plain text message along with the key, and we have to append that fixed length code with the plain text message, and we have to send that to the receiver. At the receiver side, again they will calculate. So at the receiver side, the receiver will calculate or generate the MAC by applying the same functions and the same key on the plain text message, and the generated MAC and the appended MAC will be get compared. So if both the MACs are equal, that implies the data is sent by the perfect sender. That means sender is authenticated. If the message, both the MACs are unequal or not equal, that implies the data is modified or the data is not sent by the authorized sender, authenticated sender. So hope you understood the second one. And similarly the third one, that is hash functions. Let's move on to the hash functions, the third process. Hash functions. So in this hash function, here also there is a separate authenticator. That is, first we have to generate the fixed length code, and then we have to use those fixed length code for this authentication process. So that fixed length code we call it as hash code. Hash code which acts as an authenticator. hash code which acts as an authenticator. So here let us see, here the difference between these hash functions and message authentication code is independent of key. So in the MAC we are using the message authentication functions along with the key, and here we will use only the hash functions without any key. So let us apply. So before that, so let us see, capital H means hash functions applied on plain text message will produce fixed length code which is called H is a hash code. Now consider this plain text message. Similarly, apply the hash functions. Apply the hash function. Next, encrypt this hash function by using PRA. So encrypted MAC, hash code, encrypted hash code will be appended to the plain text message. So H, so here H is a hash code. This is a plain text message. This will be sent to the receiver. So at the receiver side, again apply the hash functions. So here we are not using any key. Apply the hash function so that again we will get hash code. So decrypt this one by using a public key of A, which is available with all the users, and then compare with the generated hash code. So this is the one way we use this hash function. So there is a drawback of in this case, because here we are applying encryption to the hash code but not to the plain text message. Here the bits will be transmitted only in the form of plain text, so that there is a chance to modify the plain text. And the second one is, here we are applying encryption, we are performing the encryption on the hash code using the private key of A. That means sender is perfect. And at the receiver side, we have to decrypt the same by using public key of A, which is available with all the users in the network. So anyone can decrypt this hash code. So that is the drawback in this case. So in order to avoid this, again we have to use the encryption. We have to perform the encryption algorithm on this plain text message and the encrypted hash code. So let us see that. So first, apply the plain text message, consider the plain text message, apply the hash code and apply the encryption process by using private key, so that appended, and again encrypt this using the secret key. Now the message will be hash code, plain text message, so this is the encrypted format. Now first we have to perform the decryption by using the secret key, so that we will get the plain text message and encrypted hash code, where again we have to apply the hash function, apply the hash code, so that we will get hash code and decrypt this using public key of A, so that we will again get the hash code, which is to be compared with the calculated hash code. So this is the process. Right? So in the sender side, first we are applying the hash function, and here we will getting the hash code. We are getting the hash code and encrypt the hash code by using the private key of A, and then append with the plain text message, and the complete message with the encrypted hash code will be encrypted by using the secret key. So again here we are using the symmetric encryption. So this is a combination of both the symmetric and asymmetric encryption. So by combining these both symmetric and asymmetric encryption, we will achieve the authentication. So here we are using the public key encryption only on the hash code, and we are using the symmetric encryption on the plain text message. So after applying the private key on the hash code, append with the plain text message and encrypt that with the secret key, so that it will be sent to the receiver, and at the receiver first decrypt this complete encrypted message with the secret key, so which is shared between only sender and receiver, so that only the receiver can decrypt the message. So after this decryption, we will get the plain text message along with the encrypted hash code, and this hash code is encrypted by using the private key of user A, so it must be decrypted by using public key of user A. So we can decrypt this message by using public key of user A, so that we will get the hash code. Now on the plain text message, apply the same hash functions, so that we will again get the hash code, which is to be compared with the appended hash code. If both the hash codes are equal, that implies the sender is authenticated by the receiver. So that means the data is coming from the perfect sender, a valid sender, and also the data is not modified during the transmission. So during the transmission, if any one bit is changed, automatically this hash code will be mismatched. So that's why we call it as authenticator. So here the hash code is an authenticator. In the MAC, message authentication code is an authenticator. So both the MAC and hash code, MAC or hash code, both are the authenticators. And this MAC and hash code both are also called as message digest. Right? So once again I am repeating, these are not the encryption algorithm, this is the authentication. And there are different algorithms to generate this hash code and to generate this message authentication code. So similar to the encryption algorithms. So encryption algorithm, don't get confused. Encryption algorithms means conversion of plain text message to ciphertext. And these authentication algorithms are to generate this authenticator. That means either MAC or hash code. So in order to append with the plain text message and send to the receiver. So hope you understood. So there are, once again I am repeating, there are three types of authentications. So one is message encryption, where the ciphertext will act as an authenticator, and the second one is message authentication code, where a fixed length code should be produced by applying the message authentication functions along with the key on the plain text message, and that message authentication code will act as an authenticator. And coming to the third one, hash functions. Here we have to apply the hash functions on the plain text message, which again produces the fixed length code, which is called as hash code. Here, independent of key, we will not use any key on the plain text message. So this hash code or MAC, both are called as message digest. So this will act as an authenticator. In today's session, let us have a look on one more algorithm, that is message digest algorithm. So in the previous sessions we have seen two algorithms similar to this message digest algorithm, that is secure hash algorithm and HMAC algorithm. So similar to that secure hash algorithm and HMAC algorithm, this message digest algorithm is also used for authentication purpose. So here the output of secure hash algorithm, we call it as hash code. Similarly, the message digest algorithm, now we are going to see the message digest algorithm, which we call it as MD5. So the output of MD5, we call it as message digest. So here the names only the different, but the working is same. So what is the working or what is the use of hash code? We have seen that. So after generating this hash code, we are appending with the plain text message. We are appending with the plain text message, and we are sending to the receiver. Again, the receiver will apply the same functions and again generate the hash code, and these two hash codes will be compared so that we will achieve the integrity. That means we know that there is no modification done during the transmission itself. So during the transmission, if any one bit is changed, automatically the hash code will be different. Similarly, the MD5 is also such type of algorithm to achieve the authentication and integrity. So first, we have to generate the message digest. Second, append this message digest to plain text. Third, send to receiver. Fourth, the receiver will again generate the message digest. Five, this generated message digest and appended message digest. So 4 and 1 will be compared. First one will be generated by the sender. Fourth one is generated by the receiver. If both are same, that implies there is no modification done during the transmission of the message. So for getting this MD5, we are going to apply this message digest 5 algorithm, MD5, right? So which is similar to our secure hash algorithm. As we have seen in the previous sessions, the secure hash algorithm is also implemented for achieving the integration and authentication. So that's why we call them as authentication algorithms. So let us see the MD5 algorithm. So it's a very simple algorithm. So first one, here the plain text is processed in 512-bit blocks. The plain text is processed in 512 bits. The length of the plain text is 512 bits. So first step, if the length is less than 512, we have to append some padding bits. So append padding bits, right? So how many bits we have to pad? So here in the second step, similar to our secure hash algorithm, we are going to add the 64-bit representation of the plain text to the first step, right? So we are going to append 64-bit representation. So after applying these two, the plain text length should be equal to multiples of 512. Hope you understood. So the same steps we have followed in secure hash algorithm. So in the first step, if the plain text message is less than 512, we have to append the padding bits. So up to when we have to add. That means in the second step we are going to add a 64-bit representation to the first step. So the first two, adding the first two steps, the plain text length should be a multiple of 512. So that means if the plain text is 512, right? Here the block size is 512, right? So we are appending the 64, that means minus 64. So we will get a 448, I think so, right? 448. So in the first step, if the message is less than 448, we have to pad the number of bits until the message length is equal to 448, because in the second step we are going to add the 64 bit. So after adding the 64 bit in the second step, we will get the 512. Hope you understood. So by applying these two steps, the plain text length must be multiple of 512. And if the plain text is of 2 blocks, that means 1024, it must be processed in 2 blocks. So 1024 minus 64 is around 960. So in the first step, we have to pad until the length is equal to 960. Because in the second step, we are going to add one more 64 bits, so that we will get 1024. Right? So we have to pad the bits such that the length must be equal to 64 bits less than multiple of 512. 64 bits less than multiple of 512, because in the second step we are going to add the 64 bit. Right. So after this 64 bit representation, appending the 64 bit representation, we have to initialize the buffers. The same steps which we have followed in the secure hash algorithm. We have to initialize the buffers. Initialize the MD buffers. So here the buffers are used to store the output of the MD5. That means finally the message digest will be stored in this MD buffers. So here what is the output is 128 message digest. 128 bit message digest. The output of MD5 is 128 bit. And here each buffer is of size 32 bit. So to store this 128 bits, we require 4 buffers. Let me call A, B, C and D. 4 buffers. A buffer, B buffer, C buffer and a D buffer. Next, so after initializing these buffers, so we have to initialize these buffers, 4 buffers, each buffer is of size 32 bit. So total 128 bit, which is the output of MD5 algorithm. Next, process each block of 512. So process each 512 bit block. So once completion of first 512, we have to apply the second 512. And the last step is the output, which is message digest in buffers A, B, C and D. So these are the steps to be followed for implementing this MD5 algorithm, message digest 5 algorithm. So first append the padding bits, next 64 bit representation, MD buffers, initialize the MD buffers and process each block, that means a 512, output the message digest in buffers. Right. Let us see the function, what we will going to do, how the processing of plain text will be done. That means the third step, how the message is processed. So consider 4 buffers A, B, C and D. Right? So it will be given as input for the first round. So in the first round, so totally in the MD5 we will process each block in 4 different rounds. So here we will apply 4 rounds. So again after the first round the output will be A, B, C and D. Again, A, B, C and D. B, C and D. So 4 buffers, right? So each of size 32. Okay, each of size 32. Now, after completion of 4th round, apply the addition modulo of the same to the output of the buffers. This is not an XOR operation, it's an addition modulo. And the output from this addition modulo will be the message digest. Message digest. And here we are going to process the plain text as a part, the 512-bit plain text as a part for each and every round. And along with this, here see, X is a plain text, a part of plain text. Okay, X is a part of plain text. So along with the X, we will use one more function, some logical function F in each and every round. F, G, H and I, and also the constants 1 to 16. 1 to 16 constants will be used in first round. That means this round consists of 16 steps. Here also 16 steps. So in each and every round is processed in 16 steps. In each step we are going to use one constant. So 4 rounds and each round 16 steps. So totally 64 constants will be used. Constants, that is represented as T. And next 64. And the next is 64, and the next is 64. Right? So each round we will use some part of plain text, 16 constants in 16 steps, and one logical function of these buffers. Similarly, second round, another part of plain text, next is 16 constants and one more logical function of buffers A, B, C and D. Similarly, this will be happen, and the initial buffers will be addition. We will have to apply the addition modulo for initial values of buffers and the output of the 4th round, so that the output will be the message digest. And this is completely for first block. Coming to the second block, we have to apply this message digest as a initialization vectors. So these are the inputs, whatever the output we are getting for the first block will be given as input buffers for the second block. So here we are not having the previous block, so we are using the initialization vector, similar which we have seen in the block cipher modes of operation. Similar to these initialization vectors, we have to initial these MD buffers and we have to process for the first block, and the output of the first block will be given as input to the second block, and second block will be continued and again we will get the 4 buffers as output, and which is given as input for the third block. So like this we have to apply the rounds, different rounds. Now let us see what are the logical functions we have to consider for each and every round. F, G, H and I. See, let us see what are the different logical functions. F of B comma C comma D. So we have to apply, we are going to apply the logical function for only the 3 buffers B, C and D. B and C negation B and D. Right? Next, the second function G of B, C, D, B and D, or C and negation D. So this is the negation, right? Not, negation or not. H of B, C, D, B XOR with C XOR with D, I of B, C, D, C XOR with B or negation D. So these are the logical functions we are going to use in each and every round. And what is the steps? 16 steps. So A buffer, B addition modulo. So see, in our network security, if you write addition in a circle, this is represented as XOR. If plus is represented as a square, inside the square, it is an addition modulo 2 power 32. This is the addition modulo 2 power 32. So this is B, A addition modulo function of B, C, D addition modulo X as a part addition modulo constant circular left shift of S bits. So this formula, I mean this equation should be performed 16 times. So B is addition modulo with all these terms, that is A plus, I mean A addition modulo with the function which is F, G, H, I. So first 20 steps, I mean first 16 steps we have to use F of BCD, right? F of BCD for first 16 steps. Addition modulo with part of plain text message. It's a part of plain text. Addition modulo with T of I, which is a constant. So depends upon step. So T of 1 to T of 16 for first 16 steps, right? And this is a circular left shift. Of S bits, circular left shift of S bits, and complete everything will be, again apply the addition modulo with the content of B, and which is saved in A. Right? So this is for first 16 steps. Coming to the second 16 steps, everything is same, but here the function will be G of BCD. That means we have to apply this logical function. And part of plain text, the same plain text, and the constants from 17 to 32. The next 16 constants. And the equation is same. The circular left shift of S bits. And coming to the next round, third round, for next 16 steps, we have to use the function as H of BCD. So that means this function should be used in the third round. And this is again same, a part of plain text, and this is a constants for next 16 steps. That is 33 to 48. T of 33 to 48. And after completion of third one, fourth round, which we have to use I of BCD. That means this logical function will be applied here. And part of plain text, at the same time constant, the next 16 constant, that is from 49 to 64. And this is circular left shift of S bits. So everything is same, right? Like this, the plain text is going to be processed for complete 4 rounds and the 64 steps. So after completion of these 4 rounds, the output is stored in A, B, C and D buffers. And this will be, we have to perform the additional modulo for this and the initialization of MD buffers, initial values of MD buffers, so that we will get the message digest, which is again given as input for the next 512-bit block. If our plain text is only one block, the output is stored in the MD buffers. So if our plain text is processed in 2 different blocks, the first block output must be given as input to the second block, and the chain will be processed. So hope you understood this simple MD5 algorithm. So let me explain by using some diagrams so that you will be clearly understood. I will explain everything. See, MD5, first step, append the padding bits. So we have to pad the bits until the length must be equal to 64 bit less than multiple of 512, because in the step 2 we are appending the length in 64 bit representation. And the third, initialize the MD buffers. So here to store the 128 bit we require 4 32-bit buffers. So 4 32-bit buffers will be initialized, and the fourth step we have to process the message in a 512-bit block, and finally the output. See how the block diagram of MD5. See, first consider the plain text message, pad the bits until the less than the 64 bit length. In the second step we have to add the 64 bit so that the complete message should be a multiple of 512. See, here we can observe 512 bits, right? Initially the length is k bits, we are padding, and then we are adding the 64 bit. So complete the 3 steps, completion of 3 steps, we are getting the multiple of 512. So we are processing at a time only 512 bit, y0, y1 and so on, y12. So y0 is a 512 bit block, y1 is a 512 bit block, and similarly. So all the 512 bit blocks will be processed, and we will get the message digest for every block. So first block we will get the message digest, and we have to give a chain for the second block. So we are just giving this message digest to the second block, and the second block output will be given as input to the third block. Similarly, the last block output will be the 128-bit message digest. We can see here 128-bit message digest. So this is a chain process. The output of one block will be given as input for the second block, and in each block each block of plain text. Here we have seen Y is representation of plain text block. So plain text block, initialize the buffers A, B, C, D and apply the functions. So in each round, so this plain text block is processed in 4 rounds. Each round there will be 16 steps. So in each round there will be one logical function and 16 constants and the part of plain text block. So like this, total 4 rounds will be processed. That means 4 into 16, 64 bits, 64 steps will be processed. So after completion of 4th round, the initial values of buffers will be addition modulo with the output of buffers, so that we will get the output for the first block. If there is a second block, we have to give this first block output as chain for the second block. So that's why we will call it as a CV, that is chaining variable, right? So if there is only one block, this CV is a message digest. If there are 2 blocks, this CV is a chaining variable for the second block, and the output of output of the second block will be the message digest, right? So in every round we will use this 512-bit block as a part, that we call it as X of I, and 16 constants for each step, 1 constant. See, so in each step we are going to perform this equation. We have here plus means addition modulo. Here G of BCD means the function. So for the first round, see, for the first round we have to apply the function F. Second round we have to apply the function G. Third round we have to apply the function H. Fourth round we have to apply the function I. So in general, we have written here the function of BCD, G of BCD. And X of I is nothing but a part of a plain text, and T of I is a constant, circular left shift of S bits. So every step this equation should be computed, and these are the logical functions we have seen, which we are going to use in every round. So this is for first round, second round, third round and fourth round. So this is a pictorial representation of each step, that means equation which we have seen earlier. So the function is applied only for the buffers BCD and it is added with A. So in that A we are adding the plain text block, the constant, and at the same time circular left shift of S bits, and we are saving it in B, right? So this is the pictorial representation of each and every step, the equation which we are going to compute in each step. Next, we have seen in each step we are going to use the 16 constants. So these 16 constants for each round. So there are 4 rounds, total 64 constants we have to declare. So these are the 64 constants. So as we know, constant is a there will be no change in the value, right? So these constants should be used for MD5 algorithm. So T of 1 to T of 64. So first 16 will be used in first round. Second 16 will be used in second round. Third 16 will be used in third round. Fourth 16 will be used in fourth round. Along with this, function F in first round, function G in second round, function H in third round, function I in fourth round. Along with this, we are going to use the part of 512-bit plain text, right? So the output of this MD5 is 128-bit message digest. So after calculating this message digest, after completion of all the blocks, we will get the 128-bit message digest, and this message digest should be appended to the plain text message and it will be sent to the receiver. Again, the receiver will apply the same process to get the message digest, and the appended message digest and the calculated message digest will be compared. If both are equal, that implies there is no modification done during the transmission. So if any one bit is modified during the transmission, the message digest will not be equal. So like this we are going to achieve the authentication and mainly integrity. So these algorithms we call it as a authentication algorithms. So the purpose of MD5 and the secure hash algorithm and HMAC algorithm, all the three algorithms' main motto is to achieve the authentication and integrity. And now let us have a look on authentication algorithms. So as we have discussed in the previous session, there are three types of authentication functions. One is message encryption, other message authentication code, and hash functions. So coming to the two categories, the second and the third one, the second type and the third type, we have to generate the fixed length value which acts as an authenticator. So coming to this message authentication code, we have to apply some message authentication functions along with the key on the plain text message, which will produce the fixed length output. And this fixed length output will be appended to the plain text message and we will send it to the receiver. So similar to this message authentication codes, the hash functions will also work. So the only difference between this message authentication code and hash functions is independent of key. So here also in the hash functions also we are going to apply some hash functions on the plain text message. So without any key, which produces the fixed length output. And here also we have to append this fixed length output to the plain text message and we have to send to the receiver. So at the receiver side, again the receiver will apply the same hash functions or message authentication functions which will produce or which will again generates the fixed length value, and this generated fixed length value and appended fixed length value will be get compared. So if both the generated and appended fixed length values are equal, that implies the message has been received from the perfect sender. That implies the sender is authenticated by the receiver. So and also the message has not been modified during the transmission. So that we call it as authentication and integrity. So here the question is how to generate this fixed length value. So if you use this message authentication code, there are different algorithms to generate this MAC message authentication code, and coming to these hash functions, here also there are different algorithms to generate the hash code. Now in this session, let's have a look on one algorithm, that is an hash algorithm, which generates the hash code, that is a fixed length value, which is independent of key. So here we are not going to use any key and there is no encryption and there is no decryption. Just our aim is to generate the fixed length value by applying some functions on the plain text message. And we have to apply this fixed length value to the plain text message and send to the receiver. Now this algorithm is called as authentication algorithm, which generates the fixed length value. So in this, let us have a look on first algorithm, which depends on the hash functions, secure hash algorithm. So there are different variants in this secure hash algorithm, which we can call it as SHA algorithm, secure hash algorithm. There are different variants. So depends upon the size of the output, we have to define this SHA algorithm. If the output is 128 bit, we call it as SHA-1. If the output is 256 bit, we call it as SHA-256. If the output is 512 bit, we will call it as SHA-512. Now, so the complete implementation is same, but the only difference is the output of the algorithm. Now let us have a look on this SHA-512. So as the name indicates, our output is 512. So after applying this SHA algorithm, we will get 512-bit hash code. So that means capital H stands for hash functions. Applying the hash functions on the plain text message, we will get a small h, that is a hash code, which is 512 bit in this variant. Now let us look this SHA-512 algorithm. Coming to this SHA-512. So there are different steps involved in this SHA algorithm. First one. So before going to the steps, here the plain text is processed in terms of blocks. So plain text block size for this SHA-512 is 1024 bits. So at a time we have to process 1024 bits of plain text. Next, and here there are total number of rounds, or we can call them as steps, or so number of rounds or steps are 80, which are numbered from 0 to 79. And in each round, we will use a word, we can call it as a Q word. A Q word of 64 bit. Q word. So this Q word is generated from plain text. And in each round we will use constant K, and also in each round we will use buffers, and these buffers are used to store intermediate results. And also used to store output, which is called as hash code. So here the size of our hash code is 512, and each buffer size is 64 bit. So 512 by 64, which gives 8. So 64 8. Right. Sorry. So total 8 buffers. So hope you understood. So each buffer size is 64 bit. So how many buffers we require is 8 buffers. Right? So here the plain text is processed in blocks, number of blocks, and each block size is 1024 bits, and number of rounds or steps are 80, and in each round or each step we will use a Q word which is represented as W, So Q word, which is a 64 bit, that is generated from the plain text. So there is a process to generate the word for all the rounds. So each round we will use each constant, which can be filled with a random number, which is represented in a hexadecimal. And also we will use buffers, and these buffers are used to store the intermediate results and also to store the output, that is hash code. And each buffer size is 64. So here the output from the first block, whatever the output we are getting from the first block, will be giving as input to the second block. That means like similar to chaining process. So the output from the first block will be given as input to the second block, and the output of the second block will be given to the output of third block. The third block output will be given as input for the fourth block. So till the end, the same chain process will be continued. And at the last block, that means the output from the last block is our hash code. For example, there are 6 blocks of plain text is there, and the first block will be given as input to the second block. Second block output is given as input to the third block. Third block output is given to the input for the fourth block. Fourth block input is given to the fifth block. Fifth block input is given to the sixth block. And the output from the sixth block is hash code. So this is the chain process. Now, hope you understood this summary. Now let us move on to the block diagram and what is the function actually done in each round. So let us see the steps. So first step is we have to pad the bits so that the plain text message must be a multiple of 1024. So as we said that the plain text block, the plain text is processed in terms of blocks, and each block size is 1024 bits. So first step, we have to pad the bits 1 followed by zeros so that length of plain text is multiple of 1024 bits. So hope you understood this. And there is a constraint while padding the bits to the plain text message in the step 1, because here in the step 2 we have to represent the original plain text message in 128 bit. Append 128 bit representation of original, that means before padding, plain text such that the length should be equal to multiple of 1024 bits. So after adding this 128 bit, the length should be equal to 1024. So here we have to pad the bits so that the length of plain text should be 128 bits less than multiple of 1024. So hope you understood. So adding both the step 1 and step 2 should be the result of multiple of 1024. So first we have to pad the bits. So when we stop, that must be 128 bit less than a multiple of 1024. And this 128 bit will be appended in the second step. So after the second step, we need to get the length of plain text, which is a multiple of 1024. In the third step, initialize the buffers. So as we have said that there are 8 buffers which are represented as A, B, C, D, E, F, G and H. All these are the buffers, each of size 64 bit. So we have to initialize these buffers in hexadecimal format. Just like our initialization vector, we can fill these buffers using a random number, that is initialization vector. We call it as an initialization vector, and those must be in hexadecimal format. And the fourth one, process each block of plain text in 80 rounds or steps. We can call them as also steps. So 80 rounds or steps. And the fifth step, last step, is output in buffers. So output which is stored in buffers is hash code, which is of length 512. It's called as hash code, which is a length of 512. So this is the complete steps involved in this SHA-512 algorithm. So as the output is 512, we call it as a 512. If it is 128, the buffers will be reduced. And once again I am repeating, first we have to pad the bits, that is 1 followed by zeros, until the length is 128 bit less than a multiple of 1024. And in the second step, append the 128 bit representation of original plain text message to the first step. So that length must be equal to multiple of 1024. Now the plain text is processed in multiple of 1024 bit blocks. In the third step, we have to initialize the buffers each of 64 bit in order to store the intermediate results or the output. And the fourth step, process each block of plain text in 80 rounds or steps. And the output of each block will be given as input to the next block. And last step, the output which is stored in buffers is a hash code. It's a fixed length output which is a hash code of length 512. So hope you understood these all 5 steps. Now let us see one by one. So first of all, let us have a look on block diagram. So coming to this block diagram, so you can observe here. See, this is the plain text message which is of length L, and we have to pad that with 1 followed by zeros and 128 bit representation. So all these together will get the multiple of 1024 bits. And here at a time each block will be get processed and the block size is 1024, and this 1024 will be given as input to the function, round function. In this round function, the input is initialization vector, which we call it as a buffers, and these buffers will be involved in this function, and this buffers will be given as input to the second the output of this function will be given as input to the second block. The output of function in the second block. So likewise, we will continue for each and every block, and the last block, the output from the last block is the hash code. So after processing all the blocks, we will get the hash code. So hope you understood this block diagram. So don't get confused. The first step is append the 1 0 0 0 1 followed by all the zeros, that is padding the bits such that the length must be equal to 10 multiple of 1024 minus 128. And in the next step, we have to append this 128 bit such that now the length will be a multiple of 1024. Now the process will be started. Now, so after applying these two steps, now we have to initialize the buffers. So how to initialize the buffers? So these buffers are initialized using the hexadecimal, and these buffers are represented as A, B, C, D, E, F, G, H, which of 64-bit in hexadecimal. And now each block will be processed in number of rounds. So what will be done in the round function? See, this is a process done in the round function. So in this round function there are totally 80 steps or 80 rounds which are numbered from 0 to 79. And for each round, what are the inputs? One is the word, which I call it as a Q word, which is generated from the plain text in each round. So W0, W1 and so on, W79. And also the constant K0, K1, K2 and so on, K79. So for each round, so these are the buffers A, B, C, D, E, F, G, H. So there are 3 inputs for each and every round. One is the 8 buffers, another one is the word which is generated from the plain text, and the constant. And the output will be given to the input for the next round. So round 1, round 2, round 3 and also round 79. After completion of all the 79 rounds, the initialization vector, that means the data which is present in the buffers, will be added with the output from the round 79. So here the plus indicates addition modulo 2 power 64. Addition modulo 2 power 64. This is not an XOR operation. That is addition modulo 2 power 64. So the initialization, initial values of buffers will be added with the output of round 79, and this value will be given as input to the next function, next block. So this is for complete one block, and this output will be given as input to the second block. That means, so here the HI is this one, H1. So this will be given as input to the function for the second block of plain text message. Likewise, we have to continue all the plain text messages, right? So here the 3 functions are given as input to the round function, all the 8 buffers and the word and the constant. Here the constant will be in hexadecimal and the word size is 64-bit. So how to generate this 1024 plain text message to 79 words? 80 words. So for this, there is a word generation. So word 0 to word 16, which gives, word 0 to word 15, that is 16 words. Each word size is 64. So word size is 64. There are 16 words. So there are 15, 0 to 15. This implies so 1024. So the complete plain text will be processed as it is for the first 15 words. So first 64 bits comes under W0, second 64 bits comes under W1 and so on. The last 64 bits of plain text message will stored in W15. Now the formula starts from W16. That means we have to generate from W16 to W79. So how to generate the word for each round? That means for 16 rounds we need not generate these words, because we will just access the plain text message as a words in the first 15 rounds. So we have to generate from the 16th round. So this is the formula to generate the word in each round. So that is sigma 1 to 512 W of t minus 2 plus W of t minus 7 plus sigma 0 to 512 W of t minus 15 plus W t minus 16. So here, what is meant by sigma 1 to 512? So consider the values from 1 to 512. sigma 0 to 512 means ROTR. ROTR stands for circular right shift of the 64-bit argument X by n bits. So whatever we are using the buffer, we have to shift this buffer, circular right shift. We have to apply the circular right shift to this buffer to power or 1. Here 1 indicates 1 bit shift. In the second one there is an 8, so we have to circular right shift 8 bits. And in the third one, SHR, this is called left shift operation of 7 bits. So this implies for sigma 0 to 512, the first term is circular right shift of 1 bit of given word XORed with rotation of 8 bits of the given word. Rotation means circular right shift of given word XORed with left shift of 7 bits of given word. This gives sigma 0 to 512. So this one. And here sigma 1 to 512. So there is another term called sigma 1 to 512. So sigma 1 to 512 means left shift of 64-bit argument X by n bits with padding by zeros on the right. Left shift and by padding the bits, 0 bits on right side. So this one. Again, rotation of 16 bits of a word X XORed with rotation of 61 bits of given word XORed with left shift of 9 bits of given word. So like this formula, by applying this formula, we have to generate the words from 16 to 79, because we are using the plain text from word 0 to word 15. So we need to generate the word from word 16 to word 79, and we have to apply the same formula for all the words. So here T is a round number. Here T is a round number. Here the starting number of T is from 16 to 79. Right? So, and what about the constants? As I have said that we have to apply there are 3 functions. One is buffers, 8 buffers which are in hexadecimal format, and words which I have shown you the formula, and now constants. What about the constants? So here the constants are, again we have to use a total 80 constants for each and every round. So these are the constants which are represented in hexadecimal. So total 20 constants and 4 columns. So 20 columns, 4 rows. So total we had 4 columns and 20 rows. That is total 80 constants are there. So this we can apply a random number generator. By using the random number generator we can get the constant. So we have to use each constant in each round. So total 80 constants are there. And now what will be done on the buffers? So as I have said that there are totally 8 buffers, A, B, C, D, E, F, G, H, total 8 buffers of each 64 bit. So in each round we have to apply this formulas. We have to apply these formulas. So here we have to use 2 variables T1 and T2, and in the T1 that is equal to H. H is nothing but the hash code, the initialization vector. First one is initialization. Coming to the second block, the output of first one is H. H plus CH, that is a conditional function of buffers E, F, G. So here 3 buffers, taking the input as 3 buffers to the conditional function, and plus sigma 1 to 512 of buffer E. So I will say that I will show that what is exactly the sigma and what exactly this conditional function and what exactly this majority function. So plus WT, the word which we are generating, plus the constant that will be assigned to T1. And coming to the next one, T2, sigma 0 to 512 of buffer A, the content of buffer A, plus majority function applied for 3 buffers A, B, C. So here using 2 functions, one is a conditional function and the majority function. In the conditional function, we are applying the inputs as E, F, G, and for the majority function we are applying the functions A, B and C. So those are the logical functions which I will show you in the next one. So, and also 2 terms we have seen, sigma 1 to 512 and sigma 0 to 512. Now coming to the next one, so sorry, here H is not an hash code, sorry, H is a buffer H, this one, the last buffer, okay, I'm sorry. So as I have said that H is a previous hash function, sorry, H is a buffer, the content of buffer H. See, now assign the content of buffer G to buffer H. Assign the content of buffer F to buffer G. Assign the content of buffer E to buffer F. And the content of D is added with the term T1 and assigned to buffer E. And the content of buffer C is assigned to D. The content of buffer B is assigned to buffer C. The content of buffer A is assigned to buffer B. And the terms, the addition of 2 terms T1 and T2 will be assigned to buffer A. And this formula is implemented in each and every round. Now let us see the conditional function, majority function and these 2 functions. So here the conditional function and majority functions are the logical functions, the simple logical functions. See, this is the majority function and we are applying A, B, C as inputs to this majority function. See, here we can see the majority function of ABC. We are applying ABC as input to the majority function, which is a logical function. So what is the majority function? The content of buffer A is AND buffer with content of buffer B XORed with B and C XORed with C and A. Apply the logical AND operation. So we know that how to perform the AND operation, right? So if both the bits are true, then only we can get the output as true. If any one is false, the output will be the false. So apply the AND function for all these buffers A and B XORed with B and C XORed with C and A. That is the majority function. Coming to this conditional function, so which we have seen, CH of E, F, G, the buffers E, F and G. So here also we will use the AND and NOT operations. E and F XORed with NOT E and J. Here the NOT operation means if there is 0, it will be shifted as 1. The NOT A is, NOT 0 is 1, NOT 1 is 0. So E and F XORed with NOT E and G. And again this one, sigma 1 512 of buffer E, that is called rotation of E. As I said that ROTR stands for circular right shift. So circular right shift of 28 bits, you can see here 28 bits of content E XORed with circular right shift of 34 bits of buffer E XORed with circular right shift of 29 bits of content of buffer E. So this will be the result of sigma 1 to 512 buffer E. And next, sigma 0 to 512 of buffer A, the formula for that function is rotation of A. So here ROTR is circular right shift of 28 bits of content of buffer A XORed with rotation of 34 bits of content A XORed with rotation of 29 bits of buffer A. So this will be applied and these formulas will be calculated and assignment will be applied for all these buffers. So hope you understood these buffers, and this will be implemented in each and every round. This will be implemented in each and every round. So the same formula is picturized so that we can get like this. So here you can see the content of A is stored in content of B, the buffer B, and also the sigma plus addition with the majority function of ABC and addition of K1 will be applied and assigned to A. So the same function, the same formula is picturized so that we will get the diagram like this. So the complete one is buffers. Here A, B, C, D, E, F, G, H are buffers. So the length is 512 bit. So this is the output for each and every round. This is the output for each and every round. This will be given as input to the next round. This will be given as input to the next round. So round 1, round 2, round 3. Likewise, after the completion of round 79, the output will be added with the initial values of buffers, and it will be coming the final output, which is 512 bit, which is the input for the second process of plain text block. If there is only one block, this will be the hash code. If there are 3 blocks, this will be input for the second block, and the second block will be processed the same way, and the output will be given as input to the third block, and the third block process will be in the same way, and the output of the third block will be the hash code. That is a fixed length hash code. So hope you understood this. So this is not an encryption algorithm. This is an authentication algorithm. So here we are generating the fixed length output, which we are appending to the plain text message, and we are sending it to the receiver. So there is no question of encryption and decryption. Right? So once again I will say the steps. SHA-512. First we have to pad the plain text message with 1 followed by all zeros until the length is 128 bit less than multiple of 1024, because in the second step we are adding this 128 bit. In the second step, add the 128 bit representation of original plain text message, that means before padding, the plain text message before padding. That 128 bit will be added such that the length must be equal to the multiple of 1024. Now initialize the buffers A, B, C, D, E, F, G, H. So totally 8 buffers are required, each of size 64 bit, and these buffers are initialized in hexadecimal. And next, process each block of plain text in 80 rounds or 80 steps, and chain the process. That means the output from each block will be given as input to the next block, so that the final output in the buffers, final block, will be the hash code, which is of 512 bit. And in each round there are totally 80 rounds. In each round there are 3 inputs. One is 8 buffers, the content of 8 buffers, and the constant and the word, which is of 64 bit. That is a Q word. That is of 64 bit. So here also the complete plain text is divided into 16 Q words. So that is represented as W0 to W15, and from the W16 we have to use a formula to generate the 64 bit word. And there are different constants. We have seen total 80 constant, which each constant is used in each step. So these are the constant. So you can use a random number generator, which is a constant. So everything is represented in hexadecimal. So as I have seen, I have shown the formulas for word generation of word, and the formula for content expressions in the buffers. So how the content is manipulated in the buffers. So there we have seen two options, that is rotation and circular right rotation and left shift rotation, and we have to apply the same formula in each and every round. So the final output from the last round is XORed with the initial value, so that we will get the 512-bit output. So don't get confused. These are the authentication algorithms. So far we have seen the three types of algorithms. One is the encryption algorithms. In that encryption algorithms, we have seen two more categories. One is symmetric encryption and asymmetric encryption. So here the encryption algorithms is just conversion of plain text to ciphertext. And then we have seen the exchange algorithm, key exchange algorithm, that is how to exchange the secret key between sender and receiver in the symmetric encryption, that is Diffie-Hellman key exchange. And now we have seen this secure hash algorithm, which is an authentication algorithm, so which develops or generates the fixed length output, which is appended to the plain text message and sent to the receiver, so that the receiver will authenticate the sender. In this class, let us have a look on one more authentication algorithm, that is called HMAC algorithm. So as we know that there are three types of authentication functions. One is message encryption, next message authentication code, and hash functions. So here the major difference between this MAC and hash functions are dependent of a key. So for generation of MAC, that is a message authentication code, we have to apply the message authentication functions along with the key on the plain text message, and in the hash functions to generate the hash code, so we just apply the hash functions on the plain text message. So here for generation of hash code, there is a independent of key. Here this is an HMAC algorithm where we can use the hash algorithm and also the key. So that's why we call it as a HMAC algorithm. So here the hash function will be applied to the plain text message. So before applying to the plain text message, we have to compute one S bits, and we have to append that S bits to the plain text block, and then we have to apply the hash functions. So for that S bits, generation of that S bits, we will make use of a key. So we will use a secret key here. Key is a secret key which is shared among only the sender and receiver. So key we will use, which is shared key between sender and receiver, and from this key we have to generate K plus. So how to generate this K plus? For getting this K plus, we have to pad 0 bits, or we can say it as zeros, on left side of key until length becomes B bits. So until the length becomes B bits, we have to append or pad the zeros on left side. So why this is left side? For example, let us have a look. Consider the decimal number 2 represented in a 4-bit manner. So that is 0, 0, 1, 0. Right? So if you pad the zeros on the right side, so I will pad zeros on right side. Pad 1 0 on right side, so it becomes 0 0 1 0 0. So the decimal number of this one is 4. This is 2. That means after padding zeros on right side, then value will be changed. And if we pad zeros on left side, this is a right side padding. If we pad zeros on left side, that implies 0 0 0 1 0. the decimal value of this number is 2. So the value will not change if we pad zeros on left side. So that's why we will pad zeros on left side of the secret key until the length becomes b bits. See here, why b bits? Here the plain text is also processed in b bits. The block size of plain text is in b bits, and we will use two paddings, iPad and OPAD. iPad and OPAD. So iPad is 0011. So padding these bits b by 8 times. Here OPAD means padding this bits b by 8 times. So these are the predefined padding bits. So this will be done before applying the hash functions to the plain text message. So that's why we call it as a pre-computed message. So before applying to the plain text message, we have to perform all these things. So first we have to select the key, and which is length between 0 to b bits. So if it is less than b bits, we have to pad zeros on left side until the length becomes b bits. Next, consider the iPad and OPAD. So iPad means this one 00110110. Repeat this until the length becomes 8. That means we have to repeat this b by 8 times. And OPAD, here also repeat 0101100 by b by 8 times, so that the length will be in b bits. Now after computing all these things, now we have to calculate s bits. So how to calculate s bits? So k plus, which is XORed with iPad, k plus which is XORed with iPad will produce S1 or SI, we can represent. So which is of b bits, because k is a b bits, iPad is a b bits. So obviously the output of XOR operation will also be b bits. Now after getting this S1, we have to append with the plain text message. So let us represent y as a plain text message. So y1 or y0, y1 and so on, yl. Sorry, l minus 1. y0, y1 and so on, yl. Here s is b bits, y0 is b bits, y1 is b bits. Similarly, yl minus 1 is also b bits. So here l represents number of plain text blocks, and y represents plain text. B represents size of plain text block, and k plus we have seen earlier, iPad we have seen earlier. So this S1 should be appended with the plain text message, and now we have to apply the hash functions. So here we have to apply the hash algorithm. We can apply any variant, SHA-1, SHA-256 or SHA-512. So after applying this SHA-512, we will get n bits. So for this we have to apply initialization vector, which is of n bits. So as we have seen in the secure hash algorithm, so here initialization vector are nothing but the buffers. So the size of the buffers will be the output of the HMAC algorithm. Secure hash algorithm. So which is called hash code. So here initialization vector I have taken as n bits, so definitely I will get the output as n bits. Now again repeat the same procedure. We have to append bits so that length is equal to b bits. So here we will get again a b bits, h of k and m. Now again repeat the same procedure. Consider the k plus. Now XOR with OPAD as I have shown in the previous one. So k plus XOR with OPAD, obviously we will get some b bits, right? That we call it as S2. Here S1, here S2, which is of b bits. So here also it is b bits, it is b bits. So append this with the output from the first hash function. So S2 is appended with this one. Now again apply the hash. Now again apply the hash so that we will get again n bits, which is called HMAC algorithm. So this is a HMAC algorithm, which is a hash code. These n bits are called hash code, the output of HMAC algorithm. So here we are applying, first we are generating the b bits and appending those b bits to the plain text message, and then we are applying to the hash functions with the input of initialization vector n bits, so that it produces again the fixed length output, which is n bits, and it is again appended to the S2. S2 is generated from XORing the k plus with OPAD. So we will get the S2, which is of b bits. So again n bits is appended so that the length will be equal to b bits. So both are appended, and again apply the hash function so that we will get again n bits output, which is called a hash code. That is the output of HMAC algorithm. So this is the complete algorithm, and now let us look on the block diagram clearly. See, now first k plus XORed with iPad, k plus XORed with iPad will give S1, which is appended with Y0, Y1 and so on, YL minus 1. So here S is a b bits length, Y0 is b bits length, Y1 is b bits length, similarly YL minus 1 is a b bits length. Now apply the hash algorithm, which is secure hash algorithm, with inputs initialization vector of n bits. So obviously we will get the output as n bits, right? So this is the n bits. So we will get this n bits. So this is HMAC of k appended with plain text, appended with plain text message. Now again pad to b bits length, so that we will get, so here after padding we will get again a b bits length. Now again apply k plus XORed with OPAD, we will get S2, which is appended to here. So S2 is appended to here. Here it is a b bits length. Again apply the hash function with initialization vector. Apply the hash function with initialization vector of n bits, so here also here hash function of s2 appended with HMAC of s1 appended with plain text message after padding, right? So from this we will get n bits output, which is called hash code. So this is a hash code, this is the output of HMAC algorithm. So this is the process actually done in the HMAC algorithm. So here we are using the secret key. So whereas in the hash functions we are not using any key, so that's why we call it as a hash function. And here in this HMAC algorithm we are also using the secret key. So that's why we call it as HMAC algorithm. So let us write the steps here. First, select the key. If key is less than B, pad zeros on left until k is equal to B. If k greater than B, here we have to take care that k must be in between 0 to B, right? So this is the condition, right? Next, so after getting the key, XOR k plus, so this is the k plus, with iPad, k plus with iPad, so that we will get B bits. Next, third step, append S1, so this is called S1, with plain text message. Fourth, now apply SHA-512 on S1 appended with M. That means the output of step 3. Next, so that we will get n bits. Then again pad n bits until length equal to, so this is a n bits, length equal to B bits. Now again XOR k plus with OPAD, which will generate B bits. It is called S2. Now append S2 with output of step 5. So this one, B bits plus S2. The next step, apply SHA-512 on step 7, so that n bits will be output. This is called hash code. So these are the steps for the algorithm. First we have to select the k bits. So we have to pad zeros on left side so that the length will be equal to B. And now XOR this k bits, k plus, the k plus with iPad. So here iPad, we can write here iPad as, right? Next, here the OPAD is this one. So this is the OPAD, right? So XOR, so we have to repeat it B by 8 times. Here also repeat B by 8 times. B by 8 times. So the S1 will be appended to the plain text block and hash applied. So n bits will be the output, and for this n bits again pad some more bits until the length becomes b bits, and again apply the k plus and O pad, so that we will get S2 which is appended to the b bits, and again apply the hash function so that we will get the hash code. So this is called the HMAC algorithm. In this session, let us have a look on very important concepts, that is key distribution. So this is very important concept. So here, so we are dealing with two types of keys. So one is a secret key, another one is a public key and private key. So one is a secret key, so which is used in symmetric encryption. Another one is the public key and the private key, which we are calling them as a pair of keys. So these will be used in asymmetry. Right? So here the question is, in the symmetric we have learned that whatever the key we are using in the encryption, the same key should be used at the decryption. So this secret key should be transferred to receiver from the sender. So how this key will be distributed among the sender and receiver is the question. So for that we have seen one algorithm, that is Diffie Hellman key exchange algorithm. So where the secret key has been exchanged between the sender and receiver only through the calculations. So coming to this asymmetric key. Here in asymmetric encryption, we are using two keys. One is a public key and another one is a private key. So here the question is, so how the public key will be available for all the users in the network? So we have learned that the public key will be available for all the users and the private key is not a shareable. So the private key must be kept secret and the public key should be available for all the users. So how this public key is available for all the users? That was the question. That means here we call it as a key distribution. How the public key is distributed among all the users in the network. So simply we have seen that the public key will be maintained in a public key ring, so that every users in the network will be having an access to the public key ring and they will get the public key of other users. So before communicating each other, right? So other than that, so how many ways we can distribute this public key among the users? So here the concept is public key distribution. So how the public key will be distributed among all the users in the network. So this can be happen in 4 different ways. The first one, public announcement. The second one, the public key authority. The third one is, public key directory. Next one, certificate authority. So these are the 4 ways how this public key should be available for all the users. So let us see one by one. First, the public announcement. So as the name itself indicates, every user have to announce their public key to all the other users. So simply we can say, coming to this public key announcement, if there are two users, user A and user B, so A will announce the public key to all the users in the network. So simply we can say it is a broadcast message. So a user will send a broadcast message of its public key. So here the public key is represented as PU, private key is represented PR. If it is PUA, it indicates the public key of user A. If it is PUB, it indicates the public key of user B. Here also similarly, PRA indicates the private key of user A, and PRB indicates the private key of user B. So here the user A will publicly announce their public key to all the users in the network. So this is PUA. Similarly, user B will also announce publicly to all the users in the network. This is PUB, public key of B. So this is a simple one, so that anyone can broadcast the other's public key. So they can mislead the users and they can easily hack the message. So moving on to the second one, public key directory. Coming to this public key directory, so this is similar to our telephone directory, right? So there will be one directory and so all the users in the network will place their public keys in this public key directory. So example, simply a telephone directory, similar to our telephone directory. So we can have any person's number in this telephone directory. Similarly, the user A will send the public key of A in the public key directory. Similarly, user B will send the public key of B to the public key directory. So if any user wants the public key, they will find out the public keys in the public key directory. So anytime this public key directory can be accessed by all the users in the network. And if user A modifies the public key of A, automatically that must be done in this public key directory. If user B modifies the public key of B, and that modified public key should be placed in the public key directory. If any user adds into the network, the new public key must be placed in the public key directory. And this public key directory will be available to all the users in the network, so that anyone can access the public key of other users. So this is the public key directory, second thing. So coming to the third one, public key authority. So there is no security in this, so anyone can access the public key. There is no security. The next one is public key authority. So here the public key authority is the trusted third party. trusted third party by all users in network. So it must be trusted by all the users in the network. So if one user wants to get the public key of another user, the user A should send a request to this public key authority, and this public key authority will send the public key of user B to public key A, user A. And similarly, if user B wants the public key of user A, the user B should send a request to the public key authority requesting the public key of A. Then the public key authority will send the public key of A to the user B in a secure manner. So here completely the message will be encrypted by using some keys, secret keys. So here how the message will be secured. So the message will be secured by using KR of authority. That means private key of authority. And public key of authority will be available to all the users in the network. Right? So public key of this authority will be available for all the users in the network, and the message will be encrypted by using the private key of authority. So the message is receiving, the message which was received by any user will be definitely coming from the authority itself, because this private key is not shared among different users. So this private key will be secret and this will be not shareable. So the message received by any one of these users can know that the message is coming from only the public key authority. See, let's write here. First one. So here user A wants to communicate with user B. Right? So before starting the communication, how to share the public key of B with A and public key of A with B. First one, the first message is, this is from A to B. Right? The first message is from A to B, sending the request, and timestamp. So here the timestamp means when the message has been created and when the message has been generated. So this can be used to identify the recent message which has been sent by the sender. So for that purpose we have to include this timestamp T1. Here T1 is a timestamp. Right? So when the message has been generated. Next, the second message is the reply from, here A to B, no, not A to B, A to PKA, public key authority, right? So next one is a reply from public key authority to A, sending the public key of user B. So here the request is public key of B. So next message is from public key authority to A, sending the public key of B appended with the first message, that is request and appended with timestamp 1. Right? So this message is encrypted by using secret key of authority. That means a private key of authority. So here E is a encryption. E stands for encryption. And automatically now A will receive this message. So user A is having the public key of authority. So the A can decrypt this message and will use the public key of B. Now the third message is A will send a message to B. So A will send the message to B, which is ID of A. So identity of A appending with nonce value. So here nonce value is for unique transaction. N stands for nonce value. Nonce value which gives the unique transaction. Simply we can say it as authentication purpose. Right? So this will be encrypted by using public key of D. Hope you understood. So first one is A will be sending the message to public key authority, that is a request and the timestamp, and the request is here the requesting the public key of user B, and the second message getting the reply from public key authority. That means this public key of user B and the first message, which is encrypted using private key of public key authority. So that now the A will decrypt with public key of authority and make use of this public key and will send the message from A to B of identity and nonce value, unit transaction. So this eliminates the replay attack. This is for eliminating the replay attack. Next, if now the B wants to communicate with A, if B wants to communicate with A, first B should have the public key of A. So the same process will be repeated in the user B. That means now B will send the request to public key authority. So request appended with timestamp 2. Here the request is public key of A. Public key of A. Now the fifth one, similarly the public key authority will give the reply to user B as a public key of A. Right. So public key authority will send the message to B, which is encrypted by private key of authority, public key of A, and the first, the previous message, request and timestamp. Right? Now the sixth one. Now the B will receive this message and decrypt by using the public key of authority and make use of public key of A. Now B will send the message to A as a reply to the message of 3. So here in the third message, A is sending the message to B, just an identity and a nonce value. Now B will send message to A encrypted by using public key of A, the nonce value which is given from, the nonce value, second nonce value which is generated by user B, appended with nonce value of N1 which is generated by using A. So this gives an acknowledgement. Right? So this implies the message has been received by only B. Next, 7. Now A will give an acknowledgement to B, just receive the message from B. So A again sends to B, which is encrypted by using public key of B, the nonce value. the nonce value will be encrypted by using public key of B. So here in the third message we are encrypting by using the public key of B, and at the receiver side B will decrypt by using private key of B. So this is valid. Here also in the sixth message B is sending to A by encrypting the message by using a public key of A. So at the receiver side A will decrypt by using private key of A. So this is also valid. So these are the steps how the public key will be exchanged or distributed between the users. So this will be happens only by means of public key authority, which is a trusted third party for all the users. So if one user wants to communicate with another user, first the user should give a request to the public key authority, so that the public key authority will provide the public key to the particular user, and with the help of that public key the sender will send the message to the receiver. So hope you understood this one, right? So let us draw the diagram. So here totally 7 messages are required. Excuse me. So here user A wants to communicate with user B. Now first step, user A should get the public key of user B, and if B wants to communicate with A, B should get the public key of user A. So this will happen only by sending the request to the public key authority. The first message is sending the request appended with timestamp 1. Second message is from public key authority, which is encrypted by using private key of authority, public key of B, request and timestamp 1. Request and timestamp 1, that is a message 1. Now the user A will send the message to user B. So which is encrypted by using public key of B, ID of A, which is appended with nonce value. Now user B will request for public key of A. So this is the fourth step. Here also the request appended with timestamp 2. So here the request is requesting public key of B. Here the request is public key of A. Next, public key authority will send the request, send the reply, the fifth message, which is encrypted by using public key of, private key of authority, public key of A appended with request appended with timestamp 2. Now user B will send the message to A, which is encrypted by using public key of A and new nonce value appended with the old nonce value. And again A sends to B acknowledging the received message with the public key of B and the new nonce value which is generated by B. So this is actually happens in this public key authority. So this is a time taking process, continuously requesting for the public key of another user and sending the reply with a public key of another user to the user, and then the user A will sends the message to user B. So all these are the time taken. So to avoid this, the next one, that is the certificate authority. So every user will be having their own certificates, which includes their public key and identity. And if user A wants to communicate with user B, the certificate will be generated and the certificate will be issued by the certificate authority to every user in the network, so that the user A will exchange their certificate to user B and user B will exchange their certificate with user A, so that the communication will be started. See, let us move on to the next one, the last one. Last one, certificate authority. Certificate authority. Similar to this public key authority, here the certificate authority is also the trusted third party. It's also a trusted third party to all users in a network. So this certificate authority will issue the certificates to all the users in the network. So before starting the communication, they will just exchange their certificates each other and then authenticated each other. So what will be included in that certificate? So in the certificate, the identity of the user and the public key of the user will be included. So apart from this, there will be many fields that we will discuss in the next sessions. So majorly the identity of user and the public key of user will be included in the certificates which are generated by the certificate authority. So for every user in the network, the certificate authority will issue the certificates. Let us see. Certificate authority. User A, user B. So the first step is user A will give the public key of user A to certificate authority. Similarly, the user B will provide their public key to the certificate authority. Now, as a reply, the certificate authority will send the certificate of A to the user A, and similarly certificate of B to user B. So what will be included in these certificates? See, so after generating these certificates, user A will be sending the certificate of A and user B will be sending the certificate of B. So now actually what will be there in these certificates? So certificate of A will be having identity of A, which is appended with public key of A, which is appended with timestamp 1. Timestamp 1. So everything will be encrypted by using the private key of authority. Everything will be encrypted by using the private key of authority, so that the public key will be available with all the users. So user B can decrypt the message and get the public key of A and identity of A. Similarly, the certificate of B will be having the similar things which are encrypted with public key of authority. So ID of B appended with public key of B appended with timestamp 2. Right? So first every user have to submit their public keys to the certificate authority, so the certificate authority will generate the certificate in which there will be the identity of A and the public key of A and the timestamp. So when the certificate has been generated. So as I reply to the user A, certificate authority will issue the certificate of A to user A. Similarly, the user B will send the public key to certificate authority. As I reply, the certificate authority will again send the certificate of B to user B. Now, the user A and user B will exchange their certificates and then the communication will be started. So, in these certificates, the ID of A, public key of A and timestamp, everything will be encrypted by using the private key of authority. So, as it is encrypted by using the private key of certificate authority, it gives the message is coming from only the certificate authority because the private key is not a shareable. So in these ways the public key can be distributed among all the users in the network. So coming once again I am saying that in terms of secret key, coming to the secret key can be shared by using this Diffie-Hellman key exchange algorithm, and in this asymmetric key encryption, so here the public key should be distributed, so which is publicly available to all the users. So in these four ways, one is public announcement, the public key directory, the public key authority and the certificate authority. The last two, the public key authority and the certificate authority, are the trusted third parties for all the users in the network. And the first two are the public key announcement and the public key directory. There is no security for these two techniques. So we are not using any encryption techniques, just we are placing the public keys in the directory, in the public key directory. And coming to the first one, we are just announcing, or the user will broadcast the message of their public key to all the users in the network. In this session, let us have a look on digital signature algorithm. So far we have seen different algorithms, that is a cryptographic algorithms which provides the security, and then authentication algorithms which provides the authentication, and key exchange algorithms where we have to exchange the secret key among the sender and receiver. Now in this session let us have a look on one more security service, that is digital signature algorithm. So before going to the algorithm, first we have to know what is a digital signature. So as we know that in the asymmetric encryption, so we will be having two different keys. One is a public key and another one is a private key, where the public key is available for all the users and the private key will be not shareable, only it will be with a particular person, right? So if the message is encrypted using sender private key, so this is very important. So if the message or hash code or anything, if the encryption is done using the sender's private key, then automatically we call it as a digital signature. So here the private key is not shareable, so only the user or a sender can only send the message, because the sender will not share their private key with any other user. So the message can be encrypted only by the sender. So that's why we call this process as a digital signature, right? So once again I am repeating, if the encryption, so here obviously the encryption will be done at the sender side and the decryption will be done at the receiver side. So if the encryption is done by using sender's private key, then automatically we can say this process as a digital signature. See, Let us see that. So consider the plain text message. Plain text message. So apply the hash functions so that we will get hash code. So this is the hash code which is appended with the plain text message. Which is encrypted by using private key of A. Here if it is A and if it is B here, then the message will be in this form. This is the hash code. So this is the encrypted message, and at the receiver side it is first decrypted by using public key of A, which is available with all the users, so that we will get again the plain text message and hash code, where again hash functions are applied so that we will get some hash code, and this appended hash code will be compared. So if the message has been sent like this, we can say it as a digital signature, because at the sender side we are using the private key. So here in this digital signature approach, there are two approaches for this digital signatures. One is RSA approach, another one is DSS approach. So this we can call it as a DSS or DSA or DSA. So DSS is a digital signature standard. Digital signature standard algorithm, or we can simply say it as DSA, that is digital signature algorithm. So anything is same, right? So one is a RSA approach, another one is a DSS approach. So first let us see this RSA approach, then we will move on to this DSA approach. See, first digital signature using RSA approach. Digital signature using RSA approach. So consider the plain text message. Consider the plain text message. So which is applied to the hash function, so that we will get some hash code, and apply the encryption. That means that particular hash code will be encrypted by using public key of A, which is appended with this plain text message. Sorry. So that we will get plain text message, and this is the encrypted hash code by using PUA. So this representation is hash code which is encrypted by using public key of A. So this will be sent to the receiver. So receiver will receive this one, again applies the hash function, and alright. So apply the hash functions so that hash code will be generated, and this one will be decrypted by using So this is digital signature. We have to use a private key of A, right? So it is a digital signature, so we have to use a sender's private key. So here we are using the private key of sender. So here we have to decrypt it with public key of sender. public key of sender, so that here hash code will become and both hash codes will be compared. So this is the simple approach for a digital signature, for achieving the digital signature using this RSA approach. Here we are using RSA approach, and here we have to use hash. Hash means SHA-512 or SHA-1 algorithm. Here in this encryption we are using RSA algorithm, right? So this is the encryption. So here we are using the RSA algorithm, and here we are using for hash functions. That means for generating this hash code we are using SHA-512 or SHA-1, which we have already completed in the previous session, right? So this is the simple RSA approach. Next we will move on to the second approach, that is digital signature standard algorithm. DSS approach. DSS approach, or we can simply say it as DSA approach. First, consider the plain text message, apply the hash function, and then hash code will be generated, and for this hash code input one more variable that is called k. Here k is not a secret key, it is a random number. It is a random number, and this will be given to signature algorithm. This will be given as inputs to signature algorithm, and for this signature we will use PUG, that is a public key, global public key. Along with this we will use private key of sender, that is PRA, and so that we will get the signature, and both signature and the plain text will be appended, so that we will get this is the plain text, and two components will be received. One is yes, another one is R. So what are these components, S and R? So here the signature elements or signature components are S, R. This is called a signature. So both S and R will give the signature. And at the receiver side, again the reverse process will be done. So first hash functions will be applied, and along with these hash functions, these three also will be given to the verifying function. So for this again we will use public key of global elements. Along with the global elements we will use the public key of A, so that we will get the resultant, and this resultant and this R will be compared, right? So instead of writing this public key, we can use it as a global public elements. Right? So this is the process done in DSS approach, digital signature using DSS approach. So here once again let us repeat. So first consider the plain text message, and then apply the hash functions. Again here also we have to use a SHA algorithm, either SHA-1 or SHA-512. So we have to use the SHA algorithm H, so that we will get the hash code which is given as input to the signature algorithm, as well as a k. K is a random number which is given as input for the signature algorithm. Here we will use two components here. One is G for global parameters or global components. global elements, we can call anything global elements, and PRA is private key of user A, and signature is S comma R, and verification algorithm. So at the sender side signature algorithm will be happened, at the receiver side verification algorithm will be happened. So in the verification algorithm also we will use the signature components along with the global components, and here we are using the private key, so here we have to use the public key. So here public key will be used, so that the resultant and the R will be compared. Here R is a signature, major signature component. So R should be compared with the resultant, calculated value. Right? So hope you understood this DSS approach. So let us see the algorithm. So how these will be calculated, what are the formula for these calculations, what is the G and what is the S and what is R and what is the V. So here V will be generated. So what is a V, right? So let us see the formulas. See, now this is digital signature standard or digital signature algorithm, anything. So for this digital signature algorithm, first we have to get the global public key components. So global public key components. So what are the global public key components? First one is P. As we know, P is a prime number. So we have to consider this prime number where P must be in between 2 power L minus 1 less than P less than 2 power L. P lies in between 2 power L minus 1 and L. L is the length of bits, which is multiple of 64. Next, Q. Here Q is a prime divisor of P minus 1. Prime divisor of P minus 1. So here we can say, just I will give an example. Let us consider P as a 11. So as it is a prime number. So Q must be prime divisor of 10, P minus 1. So 5 is a prime divisor of 10. So 5 will be the Q value. So hope you understood this, right? So here the Q is a prime divisor of P minus 1. Next. Excuse me. So here we are, both are the primes, right? P is a prime and Q is also a prime. It's a prime divisor. Next, G value. G is a global component. Here G is a global component, which is H power P minus 1 divided by Q mod P. So this is the G value. So here P H power, H is a any integer. H is not a hash code. Here H is any integer which lies in between 1 and P minus 1. H is any integer which lies in between 1 and P minus 1. So these all are called public key components. So after considering these public key components, and these public key components will be used at both the sender side and receiver side, as we have seen in the previous diagram, right? So after getting all these things, now we have to select the private key of user A. User private key. which we call it as x. X. So x can be any random number. So x can be a private key which is any random number in between 0 and q. 0 and q, user's private key. Next, based upon the private key, we have to calculate the public key. So, user public key. So, user's public key. We call it as y. Y is equal to g power x mod q. Sorry. G power x mod p. It is a user's public key. So this is the user's public key. So global public key components P, Q and G, and then we have to select the private key of user A, so which is a random number, and from this random number we have to select the public key. We have to calculate the private key. We have to calculate the public key. So here the private key is x and public key is y. So y is calculated by using this private key. So y is equal to g power x. Here g is a global public component. So g power x, which is a private key, mod p. P is a prime number. Right? Now, so after that we have to select k. K is any integer. K is also any integer which lies in between 0 and q. It's a secret number. It is a secret number. Next, so after getting all these things, we should get the signature algorithm R and S components, right? So next, signature component. So here signature component is g power k mod p mod q, right? So g power mod p mod q, which is r. So we have to calculate one more component, that is s. S is equal to, right? S is equal to k inverse. K is a secret key, so k inverse h of m. H of m is hash functions applied on the plain text message plus x into r. As we know, x is a private key and r is a one more signature component. So mod q. So this is the signature function. This is the signature function. So which must be applied on the sender side. Now the message will be sent to the receiver. Now the receiver will receive, and again they will apply some more functions and they will compare this signature component R with V. So here in the decryption we have to not in the decryption. So at the receiver side V will be calculated and that V and R will be compared. Now verifying function. Verifying function. So for this verifying function we will get a V value. So V is equal to G power U1, right, where G is a public key component, Y power U2, and Y is a public key. Mod P mod Q. right? G power U1, Y power U2, mod P, mod Q. Now we have to calculate this U1 and U2. So U1 is equal to hash functions applied on M dash W, hash functions applied on M dash. So here M dash is a message which has been received by the sender. So at the sender side we will call it as M, and at the receiver side whatever the message we are receiving, that we call it as M dash. So M dash into W mod Q. So U1 is equal to H of M dash, that is hash functions applied on received message into W. So what is the W now? So W is equal to S dash inverse mod Q. What is S dash? So S is the signature component which is received by the receiver. So S is generated at the sender side, and whatever the component received by the receiver is called S dash. So S dash inverse mod Q will be W value. And U2 value. U2 is equal to R dash into W mod Q. R dash into W mod Q. So this is the formula. So here R dash is a signature component which is received at the receiver side. So here M dash, R dash, S dash are at the receiver side. The message and signature components which are received at the receiver. And this V and R. So R here, R means R dash. So V and R dash will be compared. So what is the comparison? V is equal to R dash. This will be compared. So R dash is received component and V is calculated at the receiver. So this is calculated at the receiver side. So hope you understood. So once again I will repeat it. So this is a digital signature algorithm. So there are two approaches. So one thing is, if the encryption uses the private key of sender, then we can say it as a digital signature. That is the first thing. Second thing, so here there are two approaches to achieve the digital signature. One is RSA approach, another one is DSS approach. So coming to this RSA approach, previously we have seen first the hash functions will be applied on the plain text message so that we will get the hash code, and we will encrypt that particular hash code, not a message, only the hash code. We are encrypting the hash code by using the sender's private key and appended with the plain text message and sending to the receiver. So receiver receive the message, and again the receiver will apply the same hash functions on the plain text message, and again the hash code will be generated, and the encrypted hash code will be decrypted by using the public key of user A, and both will be compared. So that is the RSA approach. Coming to the second approach, that is a digital signature approach. Here at the sender side we will use the signature algorithm, and at the receiver side we will use the verification algorithm. So here also we will use at the sender side we will use the private key, and at the receiver side we will use the public key. So apart from this, we will use some more public key components like P, Q and G. So here P is a prime number which lies in between 2 power L minus 1 and L, 2 power L. So here L is the length of the bits, which is a multiple of 64. Next, Q is a prime divisor of P minus 1. So here you have to observe it is a P minus 1. So if it is a prime divisor of P, here P is also a prime. There will be no divisor, right? So Q is a prime divisor of P minus 1. And G is a global component which is used at both the sender and receiver side. So all these three components will be used both at sender and receiver side. So G is a combination of both P and Q. So G is equal to H power P minus 1 divided by Q mod P. So here H is not a hash code. H is an integer value which lies in between 1 and P minus 1. Any integer value. Right? So this is also very important. H is not a hash code. H is any integer. H is any integer which lies in between 1 and P minus 1. So after getting all these public key components, we have to select the user's private key, which is a random number generator. By using the random number generator, we can select any number which is private key, which acts as a private key. So here the number should lies in between 0 and Q. So after selecting this private key, we have to compute the public key. So here the public key is Y, which is equal to G power X. Here G is a global key component. G power X, X is the private key, mod P. So after completion of this, we have to select one integer, secret integer. Here K is not a key, it is a integer. This is also very important. Right? So here K is any integer, so which lies in between 0 and Q. So at the sender side, so after getting all these things, now we have to perform the signature at the sender side, and at the receiver side we have to perform this verification algorithm. So at the signature algorithm we will get two components, signature components called R and S. So here R is equal to G power K. Here G is a global public key component, power K. K is an integer, secret number. So we can call it as a secret number. So K is a secret number, mod P, mod Q. So we will get a value for R and S. S is equal to K inverse. K is secret key, inverse H of M, which is nothing but a hash code. Hash code plus X is a private key and R is one of the signature component, mod Q. So for this we will get two components R and S. So this R and S will be sent to the receiver side. So first these two R and S components, that means signature components, will be appended with the plain text message and then it will be sent to the receiver. So immediately, see here, I am writing here, sender side we will send M, R, S. At the receiver side, the components will be the notation of these components will be changed to M dash, R dash, S dash. So this is the receiver side, this is the sender side. Now in the verification side, that is that we are calculating at the receiver side. So in the verification we have to calculate the V, and which is compared with the received version of R dash. So V is equal to G power U1, Y power U2, mod P, mod Q. So here we have to know about U1 and U2 components. So U1 is calculated by using received message. That means again we have to apply the hash functions on the received message so that we will get the hash code. Product with W, mod Q. Here again we have to get this W. So how to get this W? W is equal to S1, that is received signature component, S1 or S dash inverse mod Q. So from this we will get a U1 and then U2. U2 is equal to R dash. R is also received signature component. R dash into W. W is again the signature component, mod Q. So that U2 will be getting. So V will be calculated and this V and received R dash will be compared. So this is the digital signature algorithm. Digital signature, or we can call it as a digital signature standard algorithm, DSS or DSA. In this session, let us have a look on one more concept of network security. So far we have seen various algorithms for cryptographic algorithms, authentication algorithms and key exchange algorithms. And now we will see one of the authentication application. So before going to that, first one we have to know about the authentication. So authentication is one of the security service we have to achieve during the communication. So authentication means verifying the identity. So first we have to verify the identity and then we have to send the message to the receiver. So if you take the two-way communication, so sender and receiver will be there. So before starting the communication, sender should authenticated by the receiver and the receiver should be authenticated by the sender. So after authentication completed, then only the process will be started. And in today's session, let us have a look on one of the authentication application, which is called Kerberos. So Kerberos is one of the authentication application. So mainly this is implemented in the client server architecture. So we know that in the client server architecture, client will send the request to the server requesting the service, and the server will respond by giving the service to the client. So before this process starts, first the client should be authenticated by the server and the server should be authenticated by the client, and then the client request should be sent to the server so that the server will produce the service to the client. So this Kerberos is implemented in the client server architecture. So in this we will have one client and server. So it's a client so this is the server, client and server, and before starting this client server communication, first the client should be authenticated. For this we will use one more server called Authentication server, which is called as AES, and the database. Authentication server and the database, and this combinedly we call it as Kerberos. Right? So how this authentication will be processed? First the client will request the server ID to the authentication server. So sends the request. What is the request? The ID of server. Now this request is protected. So here the protection means encryption. So this request is encrypted by using client password. So the authentication server will receive this request, and based upon the client ID, the server will retrieve the password of client from the database, and the authentication server will decrypt the request and then provides the ticket of server. So that means all the authentication will be done in this step itself. So after the authentication, then the client will send the ID to the server. So unless the authentication completes, the client cannot communicate with the server, and this authentication will be done by the Kerberos concept. So now the ticket will be directly sent to the server. So this is the ticket of server which is generated by the authentication server. So based upon this ticket, again the server will respond to the client. Here the response means service, providing the service. So hope you understood this simple one. first the client will send the request to the authentication server, and this request is request of server ID or server ticket. Server ticket. So the server ticket will be generated by this authentication server. So the server ticket will be sent to the client, and this server ticket is encrypted by using the session key, which is shared among this AES and V. So authentication server and server. So the client cannot decrypt this ticket. So the duty of this client is just sending the ticket of server which is received by the authentication server to the main server. So here in this request there will be ID of client appended with ID of server. So which server the client should send the request. Right? So this is a small, a simple authentication dialog. So there is an updated version. So later, in order to increase the security, the one more server has been added. That is ticket granting server. So in order to increase the security, increase the authentication process, so one more server is added to the Kerberos, that is ticket granting server. Now the process is same. The first step, client will send the request to the authentication server, and in this authentication server the authentication will be done by just taking the client's password and decrypting the message and sending the ticket of V. Here, instead of sending the ticket of V, the authentication server will send the ticket of TGS. So here the TGS will generate the ticket of server. So authentication server will generate the ticket of TGS, and TGS will generate the ticket of server. So one more step has been added. Right? So let us see once again the complete process, and then we will go to the messages. So first the client will send the request to the authentication server. So this is the request, which is encrypted using client password. As a response, the authentication server will communicate with the client, sending the ticket of TGS. So the client will get the client password from the database and then generates the ticket of TGS. And session key, which is shared among C and TGS. Now the client will send the same ticket of TGS and ID of server to the TGS, not authentication server, TGS. Again, the TGS will generate the ticket of server and session key, which is shared among client and server. Right? So this is encrypted by using, sorry, we can write here itself, there will be no confusion. So using TGS. So the TGS and AES can only decrypt this message. And this is encrypted by using server. Now the client will send the ticket of server to the server, and the server will again send back the timestamp. So in every ticket there will be a timestamp, because the timestamp will be included to avoid the replay attacks. So the timestamp which is received by the client, by the server, will be incremented and encrypted by using the secret key client and server. So this is for mutual authentication. So the first 6 steps, or sorry, 1, 2, 3, 4, 5. First 5 steps are the client is authenticated by the server, and the last step is the server is authenticated by the client. So this is the simple concept of Kerberos. See, so this is a client. This is a server, and this is a Kerberos. So here the Kerberos consists of 2 servers. One is authentication server, and one more thing is ticket granting server. TGS, and the database. So this combinedly called as Kerberos. So first step is the client sending the request of server to the authentication server. So the first step is from client. So here the request will be sent, right? So request and ID of V will be sent to the authentication server, and this process is encrypted by client's password. So here the client password is not sent in a plain text to the authentication server. Just here we are using this client's password as a secret key. So in the first step, the client's password is the secret key. So by using that secret key, this request and ID of V will be encrypted and sent to the authentication server. In here, second step, the authentication server will, based upon the ID of the client, the authentication server search for the password of the client in the database and retrieves that password and decrypts this request, and if it is authenticated, that is the authentication process, right? So if the password is equal, then automatically the decryption process will be successful. So if the decryption process is successful, the client is authenticated by the authentication server. Now, as a response, the authentication server will send back the session key and ticket of TGS. TGS. Ticket of TGS. So TGS here is a ticket granting server. So where all the server IDs will be presented and the ticket of server will be generated by the ticket granting server. Now here the client will send the session key, the client will send the ticket of TGS to the ticket granting server, and here also the authentication process will be completed, and again the TGS will send the response to the client by sending session key along with ticket of server. So here server is V, right? So ticket of server. Now the client will directly sends this ticket of V to the server, so that the server will give the response to the response or service, provides the service to the particular client. So this is the process done in the Kerberos. So here the important thing is, what are the elements to be sent in the request and what are the elements present in the ticket of TGS. So here the ticket of TGS is generated by the authentication server. So what are the elements in this ticket of TGS and what are the elements in the ticket of V server. So now let us see the messages. Right. So the first step is client. So C stands for client. Client will send the request to authentication server. So what is that request? The request consists of ID of client appended with ID of TGS, because the TGS will generate the server ticket. Next, timestamp. So timestamp is to avoid the replay attacks, right? Next, as a reply, the authentication server will send it to the client. What it will be sent? Secret key of C, TGS, the session key or secret key which is shared among client and TGS, appended with ID of TGS, appended with ticket of TGS, and all these things will be encrypted by using the secret key of TGS. All these things will be encrypted by using the secret key of TGS. Next, the third step, the client will send the message to the, send the ticket of TGS to the client. Right, what are the elements of ticket of TGS? So, the ticket of TGS consists of ID of client, address of client, timestamp. Right? In the third step, again, the client will send the ticket of TGS to ticket granting service. So here the ID of server appended with ticket of TGS, which is generated by the authentication server, and authenticator. So here the authenticator consists of ID of client, address of client, ID of TGS, and also timestamp. Now ticket of TGS, as we have discussed, so this is the ticket of TGS, and everything will be encrypted by using, and also session key, right? So and also the secret key of TGS, this will be set. Next, now TGS will generate the server ticket and sends back to the client. So what are the elements? ID of server, a simple ticket of server along with ID of client. In the fifth step, C will send the ticket of server. So what is the ticket of server? Ticket of server consists of a secret key which is shared between client and server, appended with ID of client, appended with ID of server, appended with timestamp, and everything will be encrypted by using the secret key which is shared among the TGS and server, So the client cannot decrypt this ticket, so client will automatically sends the ticket of V along with the authenticator to the server. So here, what are the elements of this authenticator? So elements of this authenticator are again ID of C, address of client, ID of server, and timestamp. All this will be in the authenticator. And now here the authentication process has been done in these 4 steps. So authentication server and the TGS have been authenticated to the client so that the server will communicate with the client. Now the client should be, the server should be authenticated by the client. So in the 6th step, the server will send back to the client the timestamp which is sent in this message is encrypted by using the secret key which is shared among server and client. Right? So the timestamp which has been sent by the client will be incremented and sent back to the client by encrypting by using the secret key which is shared among the client and server. So this is actually happens in this Kerberos. So hope you understood these 6 steps. So once again I will show you the messages so that there will be no confusion. See. So the first step, the client will send the request and the ticket of TGS to the authentication server. So authentication server will gets the client password from the database and again decrypts the message and generates the ticket of TGS and send back to the client. Now in the third step, the client will send the ticket of TGS to the TGS, so the TGS will decrypt the ticket of TGS and authenticates, and then again it will send the secret key along with the ticket of server. So generates the server ticket and send back to the client. Now the client will send the server ticket to the server and the server will provides the service to the client. Now let us see the messages. So what are the messages? So these are the messages. So first one, client will send to the request to the authentication server. The request is ID of client, ID of TGS and the timestamp. Right? So next, the client authentication server will generate the ticket of TGS and send back to the client. So here it is encrypted by using the KC, the session key, which is shared among the client and authentication server. So in that there is a secret key which is shared between C and TGS and ID of TGS and timestamp, lifetime and the ticket of TGS. And here the ticket of TGS consists of the secret key which is shared among C and TGS, ID of client, address of client, ADC means network address of client, ADC and ID of TGS to which the client should be communicated or send the request for the server ticket, and the timestamp and lifetime. And next, in the third message, the client will send the ticket of TGS along with the authenticator C. So ID of V and the ticket of TGS and authenticator will be sent to the TGS. So again here the TGS will decrypt this authenticator and authenticates and then generates the ticket of server. So here the TGS will send to the client the secret key which is shared among the client and server, ID of server to which the client has been sent the request, and the timestamp and the ticket of server. So here the ticket of TGS consists of the ticket of, so in the first step we have seen the ticket of TGS, and the ticket of V consists of the secret key which is shared between the client and server, and then ID of client, address of client, ID of server, timestamp and lifetime. And the authenticator consists of ID of client and address of client and the timestamp. And this will be authenticated by the ticket of server, and all these things will be encrypted by using the secret key which is shared among TGS and the server. So the ticket of V is never decrypted by the client because it is encrypted by using the secret key which is shared among the server and TGS. So the client will normally sends the ticket of V and the authenticator to the server. The server will again authenticates the client and send back by incrementing the timestamp with 1 and encrypted by using the secret key which is shared among the client and server. So this is for the sixth step is for mutual authentication. In the fifth step, automatically the client is authenticated by both the authentication server and the ticket granting server. So these are the important, these message exchanges are very important. So this is actually done in this Kerberos. And now the question is, if the client wants to send the request to the server which is in another network. So here both the client and server are in the same network. So this is the process has been done. So now the question is, if the client wants to communicate with the server which is in the another network. Similar, here there is a client and the server, and here there is a Kerberos, that is AES, TGS and the database.
So this is the Kerberos, and there is one more client, and again AES, TGS, database, server. So this is one network and this is another network, right? So here the question is, if this client wants to communicate with this server which is in another network, so this we call it as real M. Real M. So this is a Kerberos. So the first step is common. The client will send the request of the TGS to the authentication server. So authentication server will authenticate it by getting the client password from the database, decrypting, and sends the ticket of TGS. So this is the request. And now this ticket of TGS will be sent to the ticket of TGS by requesting the remote TGS. The ticket of remote TGS. Now the TGS will send the request, send the response to the client, the ticket of remote TGS, RTGS, we can call it as RTGS. RTGS means remote TGS. Now the client will directly communicate with the remote TGS by requesting the ticket of server. Right? So again the server, the ticket of TGS, the TGS will send back the ticket of RV, means remote server. Now the client will communicate with the server. So this is actually done. So one step is extended, that is, so here the TGS doesn't send the server ticket. Instead of sending the server ticket, the TGS is sending the ticket of remote TGS. So all the server information and the server tickets will be generated by the TGS, right? So these server tickets will be generated by this TGS, which is in the same network. And all the server tickets of this network will be generated by this TGS of this ticket, this network. So instead of sending the server ticket, this TGS will send the address of remote TGS where the server is existing. So this ticket of remote TGS will be sent to the client, and the client will communicate with the remote TGS, so that the remote TGS will send the remote server ticket, so that the client will communicate with the server. So this is how the client should communicate with the remote server, right? So actually this topic is somewhat confused, but a very simple concept. See, the first step, the client will send the request to the authentication server. So authentication server will send the ticket of TGS, ticket of TGS. The client will send this ticket of TGS to TGS, ticket of TGS. So the TGS will send the ticket of remote TGS, and the fifth step, the client will communicate with the remote TGS, sending the ticket of RTGS. Now the RTGS, remote TGS, will send the ticket of remote server to the client, and client will send the
remote ticket of remote server to the remote server. So this is the steps involved in the while the client wants to communicate with the remote server. See, so if it is a client, authentication server, TGS, right, authentication server, next database, TGS, server. First the client will send the request to the authentication server so that the authentication server will retrieve a password of client and authenticate it and sends the ticket of TGS. Now the client will send the ticket of TGS to the TGS so that the TGS again sends the ticket of server. Again the client will sends the ticket of server to the server so that the server will provides the service to the client. So this is actually done. Right. Hope you understood here. This is a simple overview of the Kerberos. So once again I am saying that the important thing is messages. So what are the elements are sent in this ticket of V and ticket of TGS. Right? So here the AES will generate the ticket of TGS, TGS will generate the ticket of V. So AES will send the secret key which is shared among the client and TGS. The TGS will sends the secret key which is shared among client and server. Right? So in the first step the secret key is a password, the client password. So by using the client password only the message will be encrypted. Right? So hope you understood this concept of Kerberos. In today's session let's have a look on the one of the important concept, that is authentication applications in network security. Authentication application. So what is meant by authentication? So in the earlier sessions we have seen the authentication means verifying the user identity. So if two users wants to communicate each other, so before starting their communication they should be mutually authenticated. So for example, if A wants to communicate with B, so A should be authenticated by the user B and B should be authenticated by user A. So once the completion of this authentication process, then the communication will be started. So how to achieve this mutual authentication? So this can be done in different ways. So one way is applying the Kerberos concept, implementing the Kerberos concept, so which we have seen in the earlier session. And one more thing is the X.509 certificates. One way to mutually authenticate is by using this X.509 certificates. So we know that there will be two keys, private key and a public key, forms a pair. So public and private forms a pair. Right? If one key is used in encryption, the other key of same pair should be used in decryption, right? So every user will be having their own public key and private key. As we know, we have to, this public key is open for all the users in the network, and private key will be not shareable, right? This is a public access. So in order to communicate each other, every user should know the public key of other users. So we have to maintain all these public keys. So in the earlier sessions we have seen how to maintain all these public keys. So in that we have seen the certificate authority. The certificate authority is one of the options to maintain all these public keys. Now let us know what about the certification authority. Certification authority. So certification authority is a trusted third party. It's a trusted third party, right? And it is responsible for sharing the public keys, right? So this will not generate the public key. So this certification authority is not responsible to generate the public keys. Not responsible to generate public keys, but it is responsible to provide an accessible location of these public keys. It provides easy way access this public keys and for authentication. So if, as I have said, that this is a trusted third party, so all the users should be having a trust on this certificate authority. And one more thing, it is not responsible to generate the public keys, but that means this certification authority will not generate the public keys, but it will provide an access to the the easy way to access this public key and for mutual authentication, right? Then, so how the certification authority will be providing this access to the public key and how it is provided the authentication for all the users. So this certification authority will generate a signature. Generates a signature. What is meant by signature? So encryption using the private key of the user, sender. That we call it as a signature, right? Using private key in encryption process. So as usual, encryption process will be done on the sender side. So sender's private key is used for encrypting the data, that we call it as a signature. So this certification authority will generate a signature. So for which this signature will be generated? This signature will be generated for user public key and user identity. For both the things, this certification authority will provide the signature, right? So let us see the process. See, there will be user public key plus user identity. The combination of both the user public key and user identity. With this we call it as unsigned certificate. So this is not as signature, we are not adding the signature. So for this we are applying some hash algorithms. We are applying some hash algorithms so that we are getting some hash code. Right? We are getting some hash code. And this hash code is encrypted by using the certificate authority's private key. So this hash code is encrypted by using private key, right? Sorry. And we will get the encrypted format, the encrypted hash code. So this is encrypted hash code, and this will be appended to this one. That means user public key plus user identity, right, which is in normal format, and we will append this encrypted hash code to this message. Right? This is the hash code encrypted. This we call it as a signature. So as we are encrypting this hash code by using certification authority private key, so the user who knows the public key of certification authority can only decrypt this message. So that's how this public key and the user identity will be authenticated, right? So once again I am saying this certification authority is not responsible to generate the public keys, but it is responsible to provide a signature for the existing public key. So that means we are providing the authentication, right? So by decrypting this process, we will get the hash code, and again applying the same hash algorithms on this one, we will get the hash code, and both the hash codes will be compared. So if there is a matching with both the hash codes, that means it is a authenticated process. That is authenticated. That user public key is authenticated. The user is authenticated, right? So this we call it as a certificate. A certificate consists of the user public key plus user identity as well as the encrypted hash code. So this is the signed certificate. So this is called certificate signed. Certificate signed. So this is the process how this certificate is generated, right? Now let us see what are the parameters for the certificates. And here the X.509 is one of the certification directories, right? So this certification directory is responsible to provide these certificates in a single place. That means in a single directory, so that every user can access the certificates from that particular directory. And in order to authenticate the user, one user have to decrypt this one and calculate the hash code and compare both the decrypted and the calculated hash codes. So like this, the user will be authenticated, right? So once these certificates are generated, all the certificates will be placed in one directory called some certification directory or public key directory. Next, let us see what are the fields available in a directory, certificate. So this X.509 is one of such certification directory which generates the certificates, right? See, X.509 certificate. Let us see the fields available in this certificate. The first one is version. So every certificate will be having the different versions. So this version gives the which version is available for this certificate. So here there are three versions. Versions can be 1, 2 and 3. So the difference between these versions are fields. So let us see. Once we will write all the fields so that we will differentiate these versions. What are the fields available in version 1? What are the fields available in version 2? What are the fields available in version 3? Next, serial number. So whatever the certificate generated by this certification authority, it will give an unique serial number for each and every certificate. So for every user, one certificate will be generated and one serial number will be allotted to that particular certificate, right? So this is a unique serial number. Next, algorithm along with the parameters. So this algorithm will give the the signature algorithm, right? So it gives the algorithm which is used for generating the signature. Generally we have seen the RSA algorithm along with the DSS approach, right? For generating the signature, DSS approach we have seen with the help of RSA, right? So the same algorithm can be applied here. So this field this field represents the algorithm which is used to generate the signature. So that we call it as a digital signature, right? Next, issuer name. Here the issuer name is nothing but who will issue these certificates, who issued these certificates. So obviously the certification authority name is a issuer name. So the certification authority which issues these certificates is itself is a issuer name. Next, not before and not after. So it gives the validity of this certificate. So every certificate is having the validity. So when it must be used and till when it must be used. So not before, not after. It will give 2 dates. So it shows the period of validity of this particular certificate. So from when and to when it must be used. Next, subject name. This subject name is the username. So for which this certificate is issued, right? Subject public key info. That means it consists of the public key of user along with the identity, user identity. So both will be in this subject public key info. Next, issuer unique identity. For every issuer, that means for every certification authority, there will be one unique identity, and that is this field. Similarly, there will be a unique identity for all the users in the network. So the next one is subject unique identity. Right? Next, extensions. So if there are any extensions required, then we can involve these extensions for the further usage. And finally, signature. Right? So whatever the signature we are creating for this certificate, that will be in this signature. That means this signature consists of the encrypted hash code of all the remaining fields. So which we have seen earlier, right? So the public key information and the identity, we are applying the hash code and we are hashing algorithm so that we are getting the hash code and we are encrypting that particular hash code by using the certification authority private key. So after applying the certification authority private key on the hash code, we are getting the signature that we call it as digital signature. That is the last field. So it can be defined as the encrypted hash code of all the remaining fields. So these are the different fields of X.501. Right? So these are the different fields of X.509 certificate. So the version can be version 1 till this one, right? Till the subject public key information. Next, the version 2 till this one, and the version 3 right. So version 1 ends with the subject public key info, and if our certificate consists of these two fields, issuer unique identity and subject unique identity, this is a version 2. And if our certificate consists of the extension and the signature field, that is version 3. So the version can be 1, 2 and 3. The serial number, unique identity, algorithm. So this is for, it specifies the algorithm used to for signature generation. So whatever the algorithm we are using to create to generate a signature, that algorithm information will be here. And issuer name, so this one is a certification authority name. Certification authority name, not before and not after. This is period of validity when we have to use this certificate. Subject name is user name to which this certificate belongs. Subject public key info, public key of user. Next, issuer unique identity, certification authority ID, subject unique identity, user ID, extension, further purpose, and finally the signature, which is encrypted hash code of all above fields. Right? So this is the X.509 certificate. So before this validity, every certificate should be revoked, right? That means after this period of validity, the certificate will be expired. So before expiring this certificate, the revocation should be done. And let us stop here, and we will see the revocation of certificates in the next session, right? So hope you understood this, what is meant by a certificate and what is this X.509 and why we are using these certificates. Mainly these certificates are used for mutual authentication. So which is the prior process before starting the communication. So in the previous session we have seen the one of the authentication application, that is X.509. So in that we have seen what are the fields available in X.509 certificate. In this session, let's have a look on the revocation list. So what is meant by revocation list? So that means every certificate is having some period of validity. That means after some particular time period, that certificate will be expired. So before expiration of that particular certificate, every certificate should be renewed, right? So all those revoked certificates will be maintained in a separate list called revocation list. Now let us see that revocation list, X.509 revocation list. So before a certificate is going to be expired, we have to revoke that particular certificate, right? So in that, what are the fields available in this revocation list? So this revocation list consists of all the revoked certificates. Or the revoked certificates will be available in this revocation list. Now the first field, algorithm and parameters. So this gives the what is the algorithm used to generate the signature. So which we have seen in the X.509 certificate. The same field is available in this revocation list. Next, issuer name. So as we have discussed in the previous session, issuer is a certification authority, which is a trusted third party who will sign these certificates, right? So the certification authority aim is the certification authority will not create or generate the public keys, but it will make easy accessible of these public keys, and this will be, the certification authority will authenticate by applying the signature. That means, so by certification authority public key, the complete information of the user will be encrypted. Right. The issuer name is nothing but our certificate authority name, who issued these certificates. Next, this update date. That means the date when we have revoked the certificate. That means updated the certificate. So before expiration we are updating. So that particular date. Next update date. So again, once the certificate is revoked, that particular revoked certificate will be also having the period of validity. So after completion of that particular time period, again the revoked certificate will be getting expired. So the next update date. So when we have to update next. User public key info. That means the user public key and the revocation date. Right. So this is about the revoked certificate. So user certificate, revoked user certificate, and this will continue a number of revoked certificates. So at the last algorithm parameters encrypted code, all these three are in the same field. So this is the revocation list maintained. So this one, right? The last field is the signature. Okay. So this signature is done by using the certification authority private key. So this is about the algorithm which generates the signature. This is the certification authority name. This is the update date. This is the next update. So this is the public key, user public key, user public key. And all these are this is the revoked certificate. This is the revoked certificate, and we will maintain all the revoked certificates in this field. So first revoked certificate, second revoked certificate, and so on. Right? So here it consists of serial number, certificate serial number. Right? Next, this is the signature. Signature means the encrypted format, encrypted code. So in the previous session we have seen the unsigned certificate and signed certificate, right? So this is the signature which is appended to the public key information. So hope you understood this revocation list. Revocation list consists of a collection of revoked certificates. So when a certificate is revoked, whenever it is going to be expired, then such certificates will get revoked and it will be added in this revocation list. Right? Hope you understood this revocation list. Now, see, now as we have said that a user certificate will be generated by the certification authority. Right. Let it be A is a user and X1 is the certification authority user. So A is generated by XA. XA generates A. So this is denoted as AX1. So A is a certificate which is generated by the certification authority X1. Similarly, let us take X2 and a B. So this is a B certificate B is generated by the certification authority X2. Right? So we have two different certification authorities. X1 generates A, X2 generates B. Let it be. So if there is a certification authority X and X generates A and X generates B, right? So A and B are the certificates generated by a common certification authority X. Now, if A wants to communicate with B and B wants to communicate with A, both must get mutually authenticated. That means both public keys should be verified. So here A certificate will be signed with X1. So in order to verify these certificates or public keys, A should know the public key of X, because A certificates or B certificate is encrypted by using the certification authority private key, right? That's why we call it as a signature. And in order to verify the signature, that means mutually authentication, A should be authenticated by B and B should be authenticated by A. So this is done by verifying their signatures. So A verifying the signature of B, B verifying the signature of A. That means B verifies the public key of A verifies the public key of B. So this happens only when A or B knows the public key of X, that means certification authority. So unless A doesn't know the public key of X, A can't be verified by B. Similarly, vice versa, B cannot be verified by A. So in order to get mutually authenticated, both the users should share the public key of certification authority. So if two certificates are generated by the same certification authority, there is no problem, because both the users will be having the public key of certification authority, so they both will be get mutually authenticated. Now the problem rises when there are two certification authorities. See, so here A is a certificate, A is generated by certification authority X1, right? So A knows public key of X1. Similarly, B knows public key of X2, right? So in order to get mutually authenticated, B should be verified by A and A should be verified by B. So here B is generated by X2. So this certificate is verified only, it is verified only by knowing public key of X2, because it is generated by X2. Similarly, A is verified only by knowing public key of X1, right? So if A wants to verify B, A should know the public key of X2. So unless A doesn't know the public key of X2, B signature is not being verified. Similarly, if A is to be verified, B should know the public key of X1. So unless B doesn't know the public key of X1, B cannot be verified by A, right? So here in such problem, in order to solve this one, these two certification authorities also get certified, that means signed. So here if X2 is signed by X1, so in our terminology X1, X2, so X2 is signed with X1, X2 is signed with X1. So that means A can get the public key of X2. Hope you understood this one. X2 is signed with X1. Similarly, A is signed with X1. So A knows the public key of X1. So if A knows the public key of X1, A can get the certificate of X2. If A gets the certificate of X2, A can get the public key of X2. Hope you understood this one. So X1 generates a certificate of A, X1 generates a certificate of X2. Now A knows the public key of X1. Similarly, X2 knows the public key of X1. So if A knows the public key of X1, A can get the certificate of X2. So in the certificate of X2, there will be a public key of X2. Now A can verify the B. Hope you understood this one. So now A can be verified the certificate of B, because here the certification authorities also get verified. So here one certification authority is signed with another certification authority. So in case of, this is only just a case of two certification authorities, right? So if there is only two certification authorities and if you want to communicate each other, so both the certification authorities must also be certified, that means signed. So if there are multiple certification authorities, each and every certification authority must be verified by another certification authorities, so that every certificate of one certification authority can be verified by the certificates of another certification authority. Let us see the hierarchy, so your doubt will be clarified. So don't get confused. So here, whatever the certificates generated by one certification authority can be easily verified. So A is generated by X1, B is generated by X1, so A and B can mutually authenticated. So if A is certified by X1 and B is certified by X2, so there is no possibility of mutual authentication unless X1 generates X2 or X2 generates X1. So here X2 is generated by X1, generation means say signed. So X2 public key is signed with X1 private key, or X1 public key or X1 certificate is signed with X2 public key, a private key, right? So this is happened. If there are multiple certification authorities, now let us see the hierarchy to communicate the two certifications, right? See, let us take this hierarchy. So all these are the certification authorities. So here C is a certificate, A is a certificate, and B is a certificate. So C certificate is generated by X. Similarly, A certificate is generated by X. Here B certificate is certified by Z, generated by Z. So if A wants to communicate with B, here A wants to communicate with B, unless the certification authority of A is certified by the above hierarchy, we need not reach this A. Now, so what is the procedure? What is the steps? Right? So if A wants to communicate with B, X should be certified by W. Right? Next, W should be certified by B. Next, similarly, so we have to move in this way. Right? Now, V generates the certificate Y. Y generates the certificate of authority Z. Next, Z generates the certificate of B. So in this way, A can communicate with B. So this is A to B. Right? First, X should be certified, X should be signed the certificate of W, and W should be signed the certificate of V, V should sign the certificate of Y, Y should sign the certificate of Z, and Z will sign the certificate of B. So like this, we can communicate with B. In the reverse process, starting from there, so B to A. So in B to A, first Z should be certified Y, Y certificate. Similarly, Y certificate should just verify the V certificate. Next, V certificate should be verify the W certificate. Next, W should be verified the X certificate, and X should be verified the A certificate. So in this way, we can communicate from B to A to B, and B to A. See, X should be certified by W, and W should be certified by X. Similarly, here also, W should be certified by V. Right. So this will be in upper position. Y, V, V, Y. Similarly, Z, Y, Y, Z. So one certification authority should be signed by another certification authority. So unless this process has been done, the certificate belongs to one certification authority cannot communicate with the certificate generated by another certification authority. So if there is only one common certification authority, there is no problem. So all the users will share the public key of that particular certification authority, so that every public key will be get verified. So the problem rises when there are a number of certification authorities and a number of certificates. Hope you understood this one. This is the process how the A will communicate with B. How A knows the public key, or how A mutually authenticated by B. Today's session, let us have a look on one more network security concept, that is email security. So the best one which provides the email security is PGP. So PGP stands for Pretty Good Privacy. So what are the services provided by this PGP? So the major services which we have discussed in the previous sessions will be provided by this PGP. That means the authentication, confidentiality, third one is signature, that is a digital signature. So the major services provided by this PGP are these three: authentication, confidentiality, and digital signature. And this PGP also uses two more services, that is email compatibility and along with zip algorithm, that is compression algorithm. Compression function. See, let us see one by one. First authentication, then we will go for the confidentiality, and then email compatibility and zip. So we will use all these things in the security, providing the security for email. So coming to this authentication and signature. So as we know, the signature means encrypting the data by using the private key of the sender is called a signature, right? So first, consider the plain text message. Apply the hash function for this. So hash function is independent of key, so no key will be used while applying the hash functions on the plain text message. So the coming hash code is encrypted by using private key of user A. So that's why here we are using the private key of user A. That implies we are achieving the signature itself. So it is again appended with the plain text message. That means hash code is generated and then encrypted, and encrypted hash code is again appended to the plain text message. Now apply the zip function, that is compression function. So we are compressing the total length of the message. So it will be sent to the receiver, so that here we will get the message completely in a zip function, applied in the zip function. At the receiver side, first we have to use unzip, that is the reverse process. After getting the unzip, we will get the message, message and the encrypted format of hash code using private key. So private key hash code, right? So we are encrypting the message using private key. H stands for hash code, right? So again now apply the decryption. So that means here we have to use a public key of user A, which is available publicly to all the users. So the resultant will be So apply the hash function, so we will get some hash code. Here we have to decrypt by using the public key of user A, so that we will again get the hash code here. So both will be compared. Right. So first we are considering the plain text message. Apply the hash function so that we will get the hash code, which is encrypted by using the private key of sender, so that we are achieving the signature, which is appended with the plain text message, and apply the zip function, compression function, and send to the receiver. So this is all at the sender side, this is all at the receiver side. So at the receiver side, first we have to unzip the code, that means reverse process must be done, and so that we will get the message with the encrypted hash code. And here the hash code is encrypted by using private key. At the receiver side we have to decrypt that hash code using public key of user A. So we are decrypting, so H will be generated, and apply the hash functions on the plain text message, again H will be generated. So both the generated hash code and appended hash code will be compared. So here we can see both authentication and digital signature are achieved. So both the authentication and the digital signature are achieved. But what about the confidentiality? So here we are not achieving the confidentiality because the message is in a plain text format. So before applying the Z, the message is in a plain text format. So we are not encrypting the message, we are encrypting the hash code. So the confidentiality is not achieved. So for this confidentiality we will see the second case. Consider the plain text message, apply the zip function. So before encryption we are applying the zip function, compression function, and the resultant, the output from the zip function will be encrypted by using secret key. So here we are using the conventional encryption. So here the conventional encryption means a symmetric encryption. Symmetric encryption. So symmetric encryption, we have to use the same key at both the receiver side and sender side. So we have to send this secret key securely to the receiver. For this purpose, we are again encrypting this secret key by using public key encryption, that is public key of user B. And it is appended with the resultant of compression function, and this will be sent to the receiver. This will be sent to the receiver. So again at the receiver side, see, first this will be decrypted by using, here we are using the public key, we have to use private key of B, so that we will get the KS, which is a secret key, secret key, right? So apply the DS. So now decrypt the message using this KS, and then Z inverse, apply the Z inverse, that is inverse function, which will get the again the plain text message. So this will be in an encrypted format, the key which is in encrypted format. So here we are using the conventional encryption. So in this case we have achieved the plain text message, that means we are achieving the confidentiality, but here we are using the public key, so there is no authentication or a signature. So in the first case we are achieving the authentication and digital signature, but here in the second case we are achieving only the confidentiality. So this case is lack of authentication and digital signature, and this case is lack of confidentiality. So here let us see the notations. So here H is a hash code, EP means public key encryption, right? So EP means public key encryption, right? So public key encryption means we have to use either the public key of receiver or a private key of user, sender. And similarly DP is public key decryption. So if it is a public key decryption, we have to check for the encryption process which key is used at the encryption, so other key should be used in the decryption. And here we have seen EC. So EC stands for conventional encryption. Conventional encryption. So conventional encryption means a symmetric encryption. So whatever the key we are using at the sender, we have to use the same key at the receiver side. So that is EC. DC is a conventional decryption. Conventional decryption. And we know this PRA, private key of user A, PUA, public key of user A, PUB, public key of user B, PRB, private key of user B, and Z stands for compression, right? So capital H for hash functions, KS for secret key, so which is used at the conventional encryption, right? So hope all the notations has been covered, right? So EP, that is a public key encryption, Z is a compression, DP is a public key decryption, H is a small h is a hash code, small h is a hash code. Then KS is a secret key, EC is a conventional encryption, DP is a public key decryption, DC is a conventional decryption. So by combining these two cases, we can get the final thing, that is all the three are achieved. That means authentication, digital signature, as well as the confidentiality. So we have to combine the first case and the second case. So let us see the first case and second case, combining this first case and second case. Right. See, now this is the diagram for both achieving all the three services, that is confidentiality, authentication, as well as the digital signature. First, consider the plain text message. Consider the plain text message. Apply the hash function so that we will get hash code, which is encrypted with the public key, private key of sender, which is appended which is appended with the plain text message. Apply the zip function, that is a compression function. Now again the resultant of this compression function is encrypted by using conventional encryption with secret key, which is securely we have to send this secret key to the receiver, because at the receiver side also this message should be decrypted by using the same key. So this is again encrypted by using public key encryption using the public key of B, user B, that means receiver. So which is again appended, so that we will get two fields. This is encryption of secret key, that means PUB comma KS. So KS is encrypted by using the public key. Now this is at the sender side, right? So this will be sent. By receiving, again we will get the same thing at the receiver side. So which is encryption of KS using public key, and this is the message in a zip format, because here we are applying the zip function. So first decrypt this. So here we have encrypted this KS using PUB. So we have to decrypt using PRB. That means the private key of the receiver. So again this is encrypted. This Z, after applying this compression function, it is encrypted by using conventional encryption using secret key. Now we have to use, so after decrypting we will get the KS, which is a secret key. So by using this secret key we have to decrypt this message. So after decrypting this message we have to apply the inverse function, inverse compression. So after decryption, inverse function. So after inverse function we will again get the two fields, that is plain text message and the encrypted hash code. So this is the encrypted hash code using, so here we have used pre-RA comma H. So this will be decrypted by using PUA, public key of user A, and again here apply the hash function, so that this hash code and this hash code will be compared. So this is the hash code and this is the hash code, right? So this is the process actually done for achieving all the three services: authentication, confidentiality and the digital signature. So we are just combining the above two cases. So we have seen the two cases where the first case is achieving both the authentication and a digital signature and the lack of confidentiality. And coming to the second case, we are achieving only the confidentiality and it is a lack of both the authentication and a digital signature. So for achieving all these three services, just we are combining those two cases. So here for this signature, so for achieving the signature, we will make use of DSS approach with SHA algorithm, secure hash algorithm. DSS approach with SHA algorithm or RSA with SHA algorithm. So we can use both, any one among these two, right? So for achieving the confidentiality, the CAST algorithm or IDEA algorithm or triple DES algorithm. Triple DES algorithm with Diffie-Hellman key exchange. So we have seen all these things in the earlier sessions with Diffie-Hellman key exchange. And here Z is a compression function. And after completion of all these things, the email compatibility will be there. So that email compatibility is Radix 64 compatibility. So before sending the message and after, before receiving the message, the complete message will be converted into Radix 64 ASCII values, and before getting into the message, I mean before receiving the message, again that will be converted into the email compatibility, that is Radix 64 ASCII values. So like this we can achieve all the three services by using this PGP. So this is the best service we can use for the email security, right? So let us see once again the functions. See, this is the functions. So if it is unclear on the board, you can clearly observe here. So the first case, that is a plain text message, applied the hash functions on the plain text message, again which is encrypted by using the private key of user B, is appended with this message, and applying the jet, that is a compression function, will be sent to the receiver, and at the receiver side the reverse process will be done, that is first inverse compression, that is Z inverse will be applied, and after that the plain text message will be given to hash functions and hash code will be generated, and this one will be decrypted by using the public key of user A, so that again we will get the hash code, appended hash code, so both get compared. So in this case only authentication is achieved but not confidentiality, right? So here we are using the private key at the sender side, so we can achieve the signature also. In the second case, given the plain text message, apply the zip function, and which is encrypted by using the conventional encryption by using the secret key. So here the conventional encryption is used for the achieving the confidentiality. So as the conventional encryption means the same key should be used at the decryption, so we have to send this secret key securely to the receiver side. So again the secret key is encrypted by using public key encryption, that is a public key of user B, and appended to the resultant, that is a ciphertext of a given message, and sent to the receiver side. At the receiver side, first the KS will be decrypted by using the private key of user B, and then conventional decryption will be done, and the inverse compression function will be applied, so that we can get the plain text message. So here only the confidentiality is achieved but not the authentication or a digital signature. So for achieving both these two, we are just combining these two processes. So applying the hash functions, encryption, appended, and a compression function, and which is again encrypted by using the secret key, which is again encrypted by using the public key of user B, and sent to the receiver. So the reverse process is same. So here the important is the representations. So EP is public key encryption. So here we have to use either the public key or a private key, and Z is a compression function, EC is a conventional encryption. That means only we have to use a secret key, right? So here the signature, for achieving the signature we will apply the combination of digital signature standard algorithm along with the SHA algorithm, or RSA algorithm along with the SHA algorithm. So we can use one among these two, and for achieving the confidentiality we will use CAST algorithm, IDEA, or a triple DES algorithms along with the Diffie-Hellman key exchange algorithm. So here confidentiality, here we are using the conventional decryption, that means a symmetric decryption. So we have to exchange the secret key to the receiver, and that can be done by using this Diffie-Hellman key exchange. So this process is a Diffie-Hellman key exchange. Wait, sorry. This process is the Diffie-Hellman key exchange. Again, this process is the Diffie-Hellman key exchange. So by using the public key encryption, we are exchanging the secret key from the sender to receiver. So Z is a compression function. So today's session, let us have a look on one of the concept of information security, that is IP security. this is an internet protocol security. So in order to implement these IP security, we have to implement two protocols. One is ESP protocol and AH protocol. Now first let us have a look on what are the services of this IP security, and then we will see the architecture of this IP security. Now services. So as we have discussed in the previous sessions, in the earlier sessions, the services, security services are confidentiality, authentication, integrity and signature. So similarly, this IP security also provides these services, that is confidentiality, authentication, similarly integrity. So what type of authentication we can call it as, right? So these are the services provided by the IP security. Now let us see the architecture, IP security architecture. So in order to secure the traffic or data, we need to implement two protocols, ESP and AH protocols. So IP security architecture. IP security, right? So two protocols are implemented, ESP protocol AH protocol. So ESP means encapsulation security payload, encapsulating security payload. So here the ESP protocol consists of all the encryption algorithms. Similarly, AH protocol consists of authentication algorithms. So this ESP protocol provides the confidentiality service, and AH protocol provides the authentication along with the integrity. So in order to support both the encryption as well as authentication, we will use this DOI, domain of interpretation. So domain of interpretation means the identifiers which supports both the authentication algorithms and the cryptographic algorithms, I mean encryption algorithms. And finally, there is a key management. So as we have discussed earlier, the key management is how the key is exchanged between the sender and receiver. So if it is a public key encryption, I mean if it is a asymmetric encryption, how to distribute the public keys, and if it is a symmetric encryption, how to distribute or how to send the secret key from sender to receiver. So that is the key management. This is completely the IP security architecture. Two protocols, ESP and AH. So let us have a look on ESP protocol and then AH protocol. So before going to the topic, either AH protocol or ESP protocol, the main important thing is the security association. The concept of security association. So we can call it as SA. This is a security association. So security association is the communication between the client and server. So this security association is a one-way communication of client and server. So if client, or we can say any system, here server, here one more system, right? If client wants to communicate with yes, the client should have security association of client. So with the help of security association of client, the client will send the messages to server. And if server wants to give a response to the client, server should have a security association. So with the help of security association of server, the server will communicate with the client. So this security association is a temporary message or a communication link between the client and server. So it's a one-way communication. So this security association is meant for only the one-way communication. So if both the parties want to communicate, two security associations should be established. So what are the parameters for identifying this security association? So security association parameters. So in order to identify the security association, we are having three parameters. First one is security parameter index. We can call it as SPI. So this will be carried out in both the protocols, AH protocol or ESP protocol. In both the protocols, this security parameter index will be there. So this is just like our unique number given to that particular security association. Next, IP destination address. IP destination address. So here this IP destination address means, as we said, that it is a one-way communication. If client wants to communicate with server, this IP destination address will be the server's address. So where this message has to be sent. So and the third one is protocol identifier. So as I said that this security parameter index will be carried out in both the protocols, that is ESP and AH protocol. So here this protocol identifier will say, so the security association in which protocol is used. That means either ESP or AH. In which protocol this particular security association is going to be used. So these are the three parameters to identify the security association, any security association. And security association is a one-way communication. Now, so all the security associations will be maintained in a database. So all the security associations will be maintained in the database. Right? So there are different parameters associated with this security association. For every security association there are different parameters. So these three are the parameters to identify the security association, and now we are going to see the parameters which are associated with the security association. So these parameters will be maintained in this security parameter database. So all the security associations will be maintained in security association database. We can call it as SAD. Security Association Database. Right? So now we are going to see the parameters which are associated with all the security associations which are in this security association database. The first one is, as we know, the SPI, that is security parameter index, the unique identification of that particular security association. Next, the sequence number counter. So as we know, the usage of sequence number, right? So based upon the bandwidth in the network, the message will be divided into different packets. So each packet will be given one unique number and it will be transmitted to the receiver. So that again at the receiver side they will collect all the packets and according to the number they will arrange the data. So that is the use of this sequence number. So in order to send the packets, different packets, we will just increment this sequence number. So for that purpose we will use this sequence number counter. That means messages, transmitting the messages. Next, sequence number overflow. So as the name itself indicates, the sequence number overflow means it specifies where to stop the messages. So up to when we have to send the message and where we have to stop the messaging. So that's we call it a sequence number overflow. That means we will give some threshold. If the sequence number reaches that particular threshold, we can activate this particular parameter, that is sequence number overflow, such that we can say that the messages should be stopped sending to the opponent or receiver. Sequence number overflow. Next, anti-replay window. So the name itself indicates, this anti-replay window parameter is used to avoid the duplicates of packets, receiving the duplicates of packets, right? So we will have one window, right? So these are all the numbers of packets to be received. If one packet is received, just we will put a mark on this particular packet number. And if another packet has been received, we will put a tick mark on that particular packet number, right? Sequence number. So first after receiving the packet, the number will be compared with this window. So if it is already marked, that implies that the packet has already received by the receiver. So that is a duplicate packet. So in order to avoid the duplicate of packets, we will use this anti-replay window. AH information. So here AH is a authentication header. So here in this AH information we will get all the signature algorithms or the authentication algorithms or the integrity algorithms. So whatever the algorithms we are using for achieving both the authentication and integrity, we can have all those information in this particular parameter AH information. Similarly, the next one is ESP information. ESP information. So that means encapsulation security payload. So this here we will have all the cryptographic algorithms, the encryption algorithms, either symmetric or asymmetric, everything will be in this ESP information. The lifetime of security association. So every security association will be having some particular lifetime. So if the lifetime expires, then we have to regenerate the security association or re-establish this security association. So when we have to use a new security association will be in this parameter, lifetime of SCA, security association. IPsec protocol mode. So here either AH or ESP, that means authentication header or encapsulating security payload, has been implemented in two different modes. That is, one is transport mode tunnel mode. So this protocols AH and ESP protocols can be implemented in two modes, that is a transport mode or tunnel mode. So this parameter specifies in which mode the particular AH or ESP has been implemented. So these are all the security, the parameters associated with the security association. So these will be maintained in the database, security association parameters, security association database. Now, hope you understood this one. Then we will move on to the architecture protocols, different protocols. Here, so we have seen two protocols in the architecture. One is encapsulating, security, payload. Another one is authentication header protocol. So ESP protocol and AH protocol, and this will be implemented in two cases. One is ESP with optional authentication, and ESP with authentication. So in two ways this ESP can be implemented, with optional authentication or with authentication. That means in the first case we will get both we can achieve both the confidentiality and authentication. In the second case only the confidentiality will be achieved but not the authentication. And this authentication header, this can be implemented in only one way, that is by achieving the authentication along with the integrity. Authentication along with integrity. Right? So we have to see all these three cases. One is ESP with optional authentication, ESP with authentication, and authentication along with the integrity. So this can be shown by using this simple IP protocol, IP header format. So we will see the IP header formats for both the version 4 and version 6. So which fields are authenticated and which fields are encrypted. So before going to that, first let us see the packet format of ESP. The packet format of ESP, that means encapsulate. Let us see the authentication header protocol. The packet format, the length is 32 bits. The length of the authentication header is 32 bits. Next header, the first field is next header. Payload length, reserved. So the length is 0 to 31. So there are three fields here. First one is the next header, the payload length, and the reserved. Next one is security parameter index. We can call it as SPI. The next one is sequence number. The next one is authentication data. We can call it as integrity checksum. So this is both the with this field we can achieve both the authentication as well as the integrity, right? So next header is the next payload. The payload length, here the payload is the actual data, right? So payload length means the data length of that particular data, and some bits will be in a reserved. So 0 to 8 and 8 to 16, right? So some bits will be for the reserve for some future extensions for future purpose, and the next one is security parameter index to identify the security association, SA. Next one is sequence number for particular packet number, and then the authentication data. So here the authentication data means after applying, so we have seen a different authentication algorithms. So that is a HMAC algorithm or secure hash algorithm or MD5 algorithm. So whatever it may be the authentication algorithm, the result of that particular authentication algorithm, that is we call it as a message digest or a hash code. So that particular hash code or message digest we call it as an authentication data. So in order to achieve this authentication, we have to include this authentication data. So simple concept. So in this authentication, how to achieve this authentication, we have seen in the previous sessions. We are considering some plain text message, applying some hash functions or some message authentication functions. So we'll generate some fixed length value which is called some hash code or a message digest, and we are appending that particular message digest to the plain text message and we are sending it to the receiver. So at the receiver side, again the receiver will apply the same functions on the plain text message, and again the hash code or message digest will be generated. And now the generated hash code or message digest will be compared with the appended hash code or message digest. So if both the appended message digest or hash code and the generated hash code are not matched, that implies there might be some modification during the transmission. That means it fails the authentication as well as the integrity. Right? So here the authentication data means the result of that particular authentication algorithm. So that's why we can call it as integrity checksum. Right? So this is the simple packet format for this authentication header. So now let us look on IP header formats for this authentication header. IP packet format. For both the two versions, let us see the two versions of IP packets, that is version 4 and version 6. So before applying this authentication header, what is the IP packet format? I mean IP header format. So for version 4 and version 6. Let us see that. Original IP header. Okay. The original IP header, the TCP and the data. So this is the IP version 4. IP version 4. Now what about the IP version 6? So there will be some extension headers included with this IP version 4. We get the IP version 6. So now IP version 6. Similar original IP header, some extension headers, TCP and the data. So these are the IP header formats before implementing this authentication header. Now let us look the header formats after implementing the authentication header, right, for both the version 4 and version 6. Original IP header, authentication header, TCP and data. Right? So this is the IP version 4. Now what about the version 6? Original IP header, extension headers, authentication header included TCP and data. This is the header format for IP version 6. So after implementing, so we have to include this authentication data after the TCP and data. We have to include this authentication header field, right? So in this version 6, this one. Now, as we have discussed in the parameter, one of the parameter of security association, that is a protocol. IPsec protocol mode, that is, these IPsec protocols will be implemented in two modes, that is transport and tunnel mode, and this is called a transport mode. Normally just one the data and the TCP protocol and including the authentication header. After including the authentication header, we will apply we will append the original IP header, and then this packet will be sent to the receiver. This is normal transmission, so this is called transport mode. So there is one more mode, that is another mode of implementation, that is a tunnel mode. Now what is a tunnel mode? Tunnel mode means, so considering all these as a data, this inner packet, so everything is considered as a inner packet, and we will this considered as a data, and again we will include one more authentication header, and again we will append the new IP header and then send to the receiver. So this complete packet will be considered as a inner IP packet. So simply we can call it as a box in box. So this complete packet will be considered as an inner packet, and a new IP header will be included and will be sent to the receiver. That we call it as a tunnel mode, right? Now let us see the header formats for tunnel mode. So this is a normal header format for version 4. Now this will be considered as an inner packet. Now include the AH here and include the new IP header. So this is the IP version 4 in tunnel mode. So this complete we consider as an inner packet, and we are applying the authentication data for complete inner packet. That means we are providing the authentication for complete inner packet and appending this authentication header field, and then we are appending the new IP header and it will be transmitted to the receiver. Now coming to the version 6, that is also similar. The new IP header, extension headers, the AH, and similar original IP header, and everything is same. Extension headers, the TCP and the data. So this is the header format for IP version 6 in tunnel mode. So both the AH protocol and ESP protocol will be implemented in both the two modes, either transport mode or tunnel mode. So here also this is the inner packet, right? So this is the inner packet. For this inner packet, the authentication is provided and it will be appended to the inner packet, and then extension headers and new IP header will be included, and then it will be sent to the receiver. In the previous session we have seen the IP security. We have started the IP security concept. So in that we have seen two protocols, ESP protocols and AH protocol. So among those two we have completed the AH protocol. So in today's session let us have a look on ESP protocol. So similar to the AH protocol, here also in the ESP protocol we will see the packet format of ESP protocol and then the header formats of IP version 4 and version 6 in both the modes, transport mode and tunnel mode, and the key management of IP security. Now let us see the encapsulation security payload. So here also we have to see the packet format first, and then we will move on to the header formats after implementing this ESP header. So both for both version 4 and version 6 in two modes, that is transport and tunnel mode. Now ESP, encapsulating security payload. Right. So here also the first one is security parameter index. Packet format is the security parameter index. Right. So this we call it as simply SPI, which is used to identify the security association. Then the common thing, sequence number. So both are same for the AH and ESP. Right. Next, the payload data. Payload data. That is, actually we call it as the normal data, that is a plain text data. And then here there are two more fields. One is padding and next header. Padding and next header, padding length. Right, this is all for padding. And then authentication data. So as we have said that this ESP protocol is implemented in two ways. The one is with authentication and another one is optional authentication. So this is optional field. This is an optional field. If we are implementing this ESP with authentication, this field will be enabled. And if we are implementing this ESP without authentication, this field will be removed. So here the extra fields are there, that is a padding field and a padding length field. Here this ESP is used to is implemented to achieve the confidentiality. So in order to achieve the confidentiality, we are supposed to use some cryptographic algorithms. That means if it is a symmetric algorithm, we can use DES or a triple DES algorithms. And if we are going to use asymmetric algorithms, we can go for RSA algorithm or cast algorithm or idea algorithm. So whatever the algorithm we are using, this plain text is processed in number of blocks. As we have seen in the DES algorithm, the data is processed in number of blocks, that is 64 bits. The block size of DES algorithm is 64. if the plain text message is less than 64, we have to pad, that means add some number of dummy bits so that the length will be equal to 64 or the multiple of 64. So if our length of the plain text message is 63, we have to add one bit to get the length is equal to 64. And if our message is 65, the length of our data is 65, as it is more than 64, we have to pad 63 more bits to get the length of multiple of 64. So that's why in this ESP protocol, in order to achieve the confidentiality, we are going to use some encryption algorithms. So for that encryption algorithms, we have to use this padding. That means adding some duplicate bits. So how many bits we are going to add? And the next header, the further reference. And then this authentication data is simply, it's an optional thing. So this length of this packet format is also 32 bits, 0 to 31. 31. Right? So hope you understood this ESP protocol. So the common thing for this both the ESP protocol and AH protocol is the SPI and the sequence number. So as we have said that SPI is used to identify the security association. So this SPI should be carried out in both the implementations of AH and ESP. And after that, sequence number, for every packet we have to use a sequence number, so that particular sequence number should be presented in this packet format. And then for the authentication data, for the authentication header, we are going to use this authentication data, and for the ESP, to achieve the confidentiality, we are using the payload data, that is a plain text message, right? And next a padding, pad length, and next header. So these will be in an encrypted format. Right? So this will be in a encrypted format. So everything, all these will be in a encrypted format. Okay, so by encrypting this one, we are achieving the confidentiality. So if it is implemented with authentication, we can get this authentication data, and if we are implementing without authentication, we can remove this authentication data. So this field will be the optional thing. Now let us see the header formats for both the IP version 4 and version 6 implemented in two modes, transport and tunnel mode. So original header, TCP and data. So this is the normal IP version 4 packet header. Original IP header, some extension headers, TCP and the data. This is IP version 6. So these are the packet formats before implementing the ESP, encapsulation security payload. Now after applying this ESP in a transport mode, so what is the version 4 header format and what is the version 6 header format? Let us have it. Original IP header, and then we know that, so original IP header, next ESP header, original IP header, ESP header, TCP, data, ESP trailer, ESP authentication, and this field is also optional one. So this is IP version 4 header format after applying this ESP, right? So here the data will be in encrypted format. So all these fields will be in encrypted format. The TCP field, the data field, and the trailer field. ESP trailer, ESP header and ESP trailer. So this data will be in encrypted form. Now let us look in version 6. Original IP header, extension headers, ESP header, TCP, data, ESP trailer, ESP trailer, this is for IP version 6, right? So here also these fields will be in encrypted format. These fields will be in encrypted format, right? So by after applying this ESP header, so both are in transport mode. Now let us see the tunnel mode. So as we said, the tunnel mode means the complete packet will be considered as an inner packet, and then the new IP header will be included and it will be sent to the receiver, right? New IP header, the ESP header. So next, the original IP header, the TCP followed by data, ESP trailer and ESP authentication, right? So this complete thing is the header format for IP version 4 in tunnel mode. So here the complete inner packet will be encrypted. So this is all the inner packet, right? So original IP header, TCP, data, as well as tailor. The header and tailor will be included, right? So this is a simple IP version 4 in a tunnel mode. Now let us look for IP version 6. The new IP header, the extension headers, ESP header, original IP header, the original IP header, and then simple extension header, all the extension header as it is a IP version 6, and then the TCP, data, ESP tailor, ESP authentication.
This is IP version 6. Right? So here also the complete inner packet will be in encrypted format. See, this is the inner IP packet and this will be in a encrypted format. And the last field is a optional thing, ESP authentication. So these are the two header formats for both the version 4 and version 6 in tunnel mode. So simple, it's a IP packet, right? So this is the IP packet. The complete IP packet will be considered as a data, and the new header will be included for this complete IP packet and sent to the receiver. So that this is the tunnel mode, a simple thing. So hope you understood this encapsulation, security payload, and the authentication header. Both are the protocols to be implemented for achieving this IP security. Right? So ESP for achieving the confidentiality and AH is for achieving the authentication along with the integrity. So here we can use any algorithm, the DES, EES, IDEA algorithm or CAST algorithm. So any algorithm we can use, and for the authentication we can use any authentication algorithms. So finally the key management. And after implementing these two protocols, if you see the architecture, after implementing these two protocols, the next one is the identifiers to support both the authentication header and the ESP. So we have to collaborate these two because we have to provide both the authentication, integrity and the confidentiality. Right? So that is the purpose of DOI. Right? Next one is key management. As we have said that the key management, if it is a symmetric, the public key is distributed securely, and if it is a asymmetric, the secret key is distributed separately. So for this, as usual, we can use the Diffie-Hellman key exchange. So that is a refinement of Diffie-Hellman can be used. So here the key management can be implemented in two ways. One is manual. So for small networks, manually we can select the keys and we can send the keys securely. And if it is a large network, we can use automated. So here we will use two protocols for this key management. One is OK protocol, OK key management protocol. Another one is Internet Security Association Key Management Protocol. So by using these two protocols, we can use this key management. We can get this key management. So this OK key management protocol is nothing but the refinement of the Diffie-Hellman key exchange algorithm. So as we know that the Diffie-Hellman key exchange algorithm is for securely exchanging the keys from sender and receiver. So identifying the weakness of the Diffie-Hellman key exchange and refining that algorithm implements this OK key management protocol. So by using these two protocols, we can achieve this. We can implement this key management. So hope you understood this simple concept, the IP security. So a brief overview
in order to implement this IP security, the two protocols will be implemented. So one is ESP and AH. ESP for achieving the confidentiality, and AH is implemented for using, for achieving the authentication along with the integrity. So all the encryption algorithms will be implemented in ESP, and all the authentication algorithms will be implemented in AH. Right. So in that we have seen the packet formats for both the ESP and AH. And then we have seen the header formats for both the version 4 and version 6 in both the tunnel mode and transport mode. So in today's session, let us have a look on one more network security concept, that is web security. So the web security means providing the security for the data which is transmitted through the network. So here we will take the client and server example. So as usual, the client will send the request to the server, and the server will provide the service to the client. So for this purpose, we will use one protocol that is called SSL protocol. SSL, that means Secure Socket Layer. So by implementing this SSL, we can provide a security for the data over the network. So this secure socket layer will act as, will provide the security for the data which is transferred between the web browser and server. So by implementing this secure socket layer, we can provide the security for the data which is transferred between web browser and the server. So this SSL is implemented by using a different protocols. So it includes a different protocols. One is SSL record protocol, handshake protocol, change cypherspec protocol, and next the alert protocol. So all these protocols will be included in this SSL secure socket layer. So this we call it as SSL protocol stack. So this will be implemented just above the TCP/IP and just below the HTTP. So before going to this SSL, the two main concepts must be implemented. That is, first one is connection. So these are very important while implementing this SSL. And session. So what is a connection and what is a session? So first we will look at this connection and session, and then we will move on to the different protocols. So as we know, in order to communicate both the client and server, the first thing is the transport to provide the service. That we call it as connection. So first the connection should be established between the client and server so that the client can communicate with the server and the server can communicate with the client. So this connection is a transport to provide the service between the client and server. Between, we can say it a client and server, or in between two clients, whatever it may be. Right? So session. A session is an association between the client and server. So one session will be created, and based upon this session, the client and server will be communicated. So generally this session we call it as a temporary time period, right? So if you observe the bank sites, so if you log into your net banking and just keep the net banking site idle for 3 to 4 minutes, automatically you will get the message, alert message, that your session has been expired. So re-log in to use the service. So here the session means up to some time the client and server should communicate each other, right? So that we call it as an association between the client and server. So this session consists of a number of connections, the multiple connections, right? So these sessions will be created or generated by handshake protocol. All the sessions will be generated by handshake protocol. So once a session has been created, automatically it consists of multiple connections, a number of connections in that particular session. So every session will be identified by using some parameters which can be used by all the connections in that particular session. So let us have a look on parameters of session and the parameters of connection. First, session state parameters. So what are the parameters associated to identify the session, right? So session state parameters. Session state parameters, right? The first one is session identifier. It's a byte sequence to identify that particular session. Next, peer certificate. Peer certificate. Here peer is nothing but a client. So client certificate. So which is generally X.509 certificate. So in this certificate we have the public key of the client as well as the signature algorithm parameters. The next one, compression method. So this parameter is used to say the compression algorithm used before the encryption in the SSL. So this compression is an optional thing, so it can be applied or it may not be applied. Next, cipher spec. Spec means specification, cipher specification. So here we can have the encryption algorithms, and authentication algorithms. So this can be the MAC algorithms or hash algorithms, right? Next, cipher spec, and then master secret. So which is the secret key shared between the client and server. So this is the secret key which is shared among the client and server. Is resembled. So this is a flag which is used to know whether the new connections can be or new sessions can be established by this particular session or not. So all these are the different session state parameters. Now, so these parameters are commonly shared by each and every connection associated with this particular session. Now let us see the connection state parameters. So what are the connection state parameters? Connection state parameters. First one, secret server and client random. Server and client random, these are the byte sequences which are associated with the particular connection, associated with the server or associated with the client. The next, the server and the client random, server write MAC secret. So this is the MAC which is generated by the server for the data which is sent by the server. So don't get confused. This is a MAC which is generated for the data which is sent by the server. So here the sender is the server. So sender will generate the MAC. Right? So this MAC is generated by the server. Similarly, client write MAC secret. So here the client MAC write secret means this is the MAC generated by the client for the data which is sent by the client. So here the sender is the client. So MAC which is generated for the data at the client side. Right? Next, server write key. So this is the secret key used for conventional encryption. This is the secret key which is used for the conventional encryption by the server, which is sent by the server. The client write key. So this is also the shared key between the client and server, but this key is generated by the client. This key is a shared key, I mean the secret key which is shared among the client and server, but it is generated by server. So these keys are used for conventional encryption. Next, initialization vector. So initialization vectors are just like a buffers or some dummy bits which are used for the data or for the key in the mode of operation, the block cipher mode of operation. And the last one is sequence number. As we know, the sequence number will be generated and it will be appended to each and every packet which has been sent through the transmission, right, during the transmission. So based upon the bandwidth, the complete data will be fragmented and the sequence number will be allocated for each fragment. At the receiver side, they will collect all the packets and they will collaborate all the packets according to the sequence number. Right? So these are the parameters associated with the connection. Now, hope you understood this session state parameters and the connection state parameters. Now let us move on to the SSL, Secure Socket Layer. Secure Socket Layer. Which we call it as SSL. So this is implemented by using the SSL protocol stack just above the TCP and just below the HTTP. So as we discussed that this protocol stack will be having 4 protocols. One is SSL record protocol, handshake protocol, chain cipherspec protocol, and the alert protocol. Chain cipherspec protocol, alert protocol, and finally the HTTP. The next one is SSL record protocol, where the data fragmented and the calculation of MAC or the encryption algorithms or the compression algorithms will be implemented in this protocol. And this handshake protocol is used to establish the sessions, and this handshake protocol is used to authenticate the client with the server and the server with the client. And chain cipherspec protocol is for changing the state, the pending state to the current state. And this alert protocol for giving the alerts while implementing this SSL. These are, as usual, we know the TCP protocol and the IP protocol. So this is the SSL protocol stack. SSL protocol stack. So now let us look each protocol. First we will see the SSL record protocol, then we will move on to the handshake protocol, next the chain cipherspec protocol and the alert protocol. So all these protocols are called SSL, involved in the SSL, secure socket layer. Now let us see the SSL record protocol. SSL record protocol. So here the actual implementation will be done. So the first step is the complete data will be taken. This is the application data. Right? So this application data will be divided into different fragments. That means the fragmentation will be done according to the bandwidth. Right? So let us consider this fragment. So this is the fragment. So for each fragment we have to implement everything. So let us see the one fragment. So consider the first fragment and now apply the compression function. So we have to apply the compression function. It's an optional thing. So apply the compression function. So the fragment in a compressed format. Now calculate the MAC by using one of the authentication algorithms. So here we can use the MD5 algorithm or a SHA-1 algorithm. So MAC will be calculated and that calculated MAC will be appended to the compression function. So this is the actual compression function. And this is the MAC, right? So compressed function and MAC. So this is the MAC which is generated for this compressed function. Now consider the complete compression function and the MAC. Now we have to use the encryption. So we have to encrypt this data. See, this is the compression fragment. This is the MAC. Now encrypt this complete encryption is done. So encryption is done for this fragment. Now after encryption is done, now append the SSL record header to this fragment. So in order to process it to the higher layer protocols, higher level protocols, right? So here we have to, as a final thing, we have to append the SSL record header. So append the SSL record header. Append SSL record header. So what are the fields involved in this SSL record header? So here I will write SSL record header. So there are mainly 4 fields involved in this SSL record header. The first one is content type. So in this field we will mention the higher layer protocol to which this compressed and encrypted fragment will be sent. So here we have to implement, we have to include the higher layer protocol to which this fragment will be processed. And the next one is the major version of SSL. Major version of SSL. So here the major version of SSL is 3. Right? The next field is minor version of SSL. The minor version of SSL, which is 0. The minor version is 0. Next, the last one is compressed length. So the length of the compressed fragment. So if we use this compression function, we have to give the length of the compressed fragment. If you are not using this compression function, just we have to mention the length of the plain text. So hope you understood. This compression function is an optional thing. So here, if we want to include this compressed length, if we are using the compression function in our SSL, we have to give the length of the compressed fragment. If we are not using any compression function in this SSL, we have to give the length of the plain text. Right? These are the SSL record header. So this will be appended to the encryption fragment. Now, after applying all these things, how the record format will be? We will see how the record format will be. Let us see. So step by step, we are processing the fragment. First, consider the data, the application data. We call it as an application data. So, based upon the bandwidth, the application data will be divided into different fragments. So, consider each fragment, apply the compression function. After applying the compression function, generate the MAC using either MD5 or SHA algorithm. So, append the MAC to the compressed fragment. Now, apply the encryption algorithm. So, we can use either DES algorithm or IDEA algorithm or a triple DES algorithm, any algorithm we have to use. So by using all these, one among these algorithms, we have to encrypt the compressed fragment, and after applying the encryption, now append the SSL record header to that particular encryption and process the fragment to the higher layer protocols. So let us see the complete output of SSL record header. The content type, major version, minor version, compressed length. This is the MAC. This is the SSL record header. This is the compressed data, or it's a plain text. It's a plain text. So here everything will be in encrypted format. So all these things will be in a encrypted format, right? So this says the higher layer protocol to which this fragment will be processed. Major version is 3, minor version is 0, and the compressed length, the length of the plain text or the compressed message. So this is complete SSL record protocol. Now let us see the calculation of MAC. So here the MAC is calculated by using either MD5 algorithm or the SHA algorithm. And the encryption process we are performing in this SSL record protocol is we can apply either a DES algorithm or a triple DES or any other encryption algorithm. Now let us see the equation for calculating the MAC. Hash functions applied to master write secret appended with pad 2. I mean once I will write the formula first and then I will explain one by one, right? Pad 2 appended with, again apply the hash master write secret appended with pad 1 appended with the sequence number, which is appended with the compressed length, the SSL compressed length appended with SSL compressed type appended with SSL compressed fragment. So this is the equation we are using to generate the MAC in this SSL, right? So here let us see one by one. So first one is master write secret. So here the master write secret means the shared secret key. It is a shared secret key between the client and server. And the pad 2, here the pad 2 means pad 2 is the byte sequence repeated 48 times for MD5, 40 times for SHA. So this is the pad 2. That means repeating this particular byte sequence 48 times for MD5 algorithm. If you use the MD5 algorithm as to generate the MAC, we have to repeat it for 48 times. If you use SHA-1 algorithm to generate the MAC, we have to repeat this byte sequence 40 times. Now, pad 1. Repeat this byte sequence, same, 48 times for MD5, 40 times for SHA-1, right? So, depending on the algorithm we are using to generate the MAC, we have to repeat this particular byte sequence for in pad 2 and pad 1. And the master write secret, so here it is not a master write secret, we can call it as a MAC write secret. So MAC write secret, so this is the shared key. So this is the shared key between the client and server, right? Next, the sequence number we know, the compressed length. If any compression algorithm is applied, the length of the compressed fragment. If it is not applied, we can simply write it as the plain text, length of the plain text. The compressed type, that means the higher level protocols, higher layer protocols to which the fragment will be processed. And the compressed fragment, the actual fragment, the data, the compressed data. So applying this MAC, the hash algorithm for all these things, we will get the MAC. That MAC will be appended to the compressed compressed data, and then the encryption will be done. So this is all about the SSL record protocol. So in previous session, we have started the web security. So in that web security, we have seen the secure socket layer. So the secure socket layer can be implemented by using the 4 protocol stack, that is SSL records protocol, and handshake protocol, chain cyberspace protocol, and the alert protocol. So before going to that, we have seen what is meant by a connection and what is meant by a session, and also we have seen the parameters associated with the connection and the session. So we have seen one protocol, that is SSL record protocol. So where the data will be considered and the data will be fragmented. So each fragment will be compressed, and after the compression, the calculation of MAC, appending the MAC, and after appending the MAC, applying the encryption algorithms, and after that appending the SSL record header. So after that we have seen the equation for calculating the MAC. Now in this session, let us start the one more protocol, that is handshake protocol. So the main purpose of this handshake protocol is to establish the sessions. So as we have learned in the previous session, the sessions will be generated by this handshake protocol. So handshake protocol can be represented by using 3 fields. First one is type. The next one is length and the content. Length is 1 byte, type is 1 byte, length is 3 bytes, content is greater than or equal to 0 bytes. So here the type represents the higher layer protocols. The length represents the length of message. So here we will have some messages, so we have to mention the length of that particular message. And the content means the parameters associated with the particular message. Now we have to see what are the messages involved in this handshake protocol. The first one is the client hello, the client hello message, the server hello message, the next one is certificate. So usually the certificate is X.509 certificate. Next server key exchange, certificate request, server done, client key exchange, certificate verify, finished. So these are the different messages involved in this handshake protocol. So the length of this particular messages will be in the second field, and the parameters which are associated with these messages will be in the third field. Right? Now let us see the messages in different phases, involved in different phases of handshake protocol. The client, so this is the client and server. Now let us see the messages involved in between the client and server. The client will send the hello message, client hello. As a reply, the server will send the server hello. So this is the phase 1. So where all the security capabilities, including the protocol version, the session ID, and the cipher suit, the compression method, and all the initial parameters will be involved in this particular phase 1. Now, so after getting this client hello and server hello, the second phase will be started. Now the second phase, the server will communicate with the client by sending the certificate to the client, and then certificate to the client. Next, the server key will be exchanged, server key exchange, and then requesting for the client certificate, requesting for the client certificate, and then the server hello done. So until the client receives this message, server hello done, the client should wait for the communication, start the communication. Now the second phase is completed. Initializing the cipher suit, compression methods, protocol versions, and etc. will be in the phase 1. In phase 2, the server exchange certificates and request for client certificate. request for client certificate. Now the third phase will be started by the client. As a reply, the client will send the certificate. The client will send the client key exchange and the certificate verification. Certificate verified. So once this phase 3 has been completed, so here the phase 3 is directly communicated from the client to server. Client sends the certificate and verifies the certificate. After completion of the last phase, now the cipher suit will be implemented. Right? Now, so once this certificate verification has been completed, now change cipher spec. Finished. Similarly, from the server, change cipher spec. Finished. Phase 4, it is the hash value or it's a MAC value. That means after completion of phase 4, the client is authenticated by the server and the server is authenticated by the client. So this is done by exchanging their certificates and the key exchanges. So here this is called a handshake protocol. So this is called a handshake protocol. So first the client will communicate with the server with a client hello message, and as a reply the server will send the reply as a server hello message to the client. Now the server, the time to authenticate each other. Now the server will send the certificate to the client and sends the server key exchange and request for the client certificate and then server hello done. So this is just like a one-way communication. So after completion of the server hello done, then only the client should communicate with the server. So until it reaches the server hello done, it receives the server hello done, the client should not communicate with the server. So this message indicates the communication has been completed so that the client is able to communicate, start the communication. Now in the phase 3, the client will send the certificate and client sends the key exchange, and also the client will verify the certificate sent by the server. And after completion of this phase 3, the last phase is generation of hash value and the authentication will be finished. So the client is authenticated by the server and the server is authenticated by the client. So this is done by the handshake protocol. These are all called messages. So which we have to include in the length field, the second field. The length of this message should be included in the second field. Right? So next, so after the handshake protocol, this change cipher spec is implemented. So here the next protocol is change cipher spec. So after completion of handshake, the next level protocol is change cipher spec. So unless this authentication is completed, the output of SSL record protocol will be in a waiting state. Right? So now change cipher spec protocol. Change cipher spec protocol. So which is represented by using only one byte, which is only one byte as value 1. Right? So unless this handshake protocol completed, that means authentication between the client and server completes, the output of, the encrypted fragment coming out from this SSL record protocol will be in a pending state. So after completion of this handshake protocol, the pending state will be changed to the current state, right? So that is done by this change cipherspec protocol, moving from pending state to current state or running state. Right? So this is done by the change cipherspec protocol. So after completion of this thing, it will be moved on to the next level protocol, that is alert protocol. See, next one is alert protocol. So next protocol is alert protocol, which is represented in two fields. First one is level, another one is alert. So 1 byte and 1 byte. So here the level represents the one is either warning or a fatal error. So if it is a warning, there is no impact on our connection. If it is a fatal error, automatically the connection between the client and server will be disconnected. So we have to re-establish the connection. And these are the alert messages, these are the alerts are used to convey while implementing this SSL protocol. So we can receive any one among these alerts. So these are all the fatal errors, right? These are not the warnings, these are the fatal errors. And these are the some reminders of the alerts. So we can expect these fatal errors while implementing the SSL. So first one is unexpected message, as the name itself indicates, receiving the inappropriate message. And the next one is bad record MAC. The MAC generation is somewhat failed to generate the MAC. Next, decompression failure. So here we are using the compression function at the sender side. Automatically at the receiver side we have to decompress it. So while decompression, if it get failed, automatically it will send an alert. So immediately after getting this alert, the connection will be disconnected. The next one is handshake failure. That means authentication failed. So handshake is mainly for authenticating the client to server and server to client. So if any one authentication is failed, automatically this alert will be displayed. Next, illegal parameters. So the parameters which are associated with the handshake messages are some illegal parameters. So if we receive any one among these fatal errors, automatically the connection will be disconnected. And these are the some alerts, the remainder of some alerts. One is close notify, that is either sender or receiver saying that not to send the upcoming messages, right? So they are stopping the messages. The communication has been stopped. Next, no certificate. So the certificate is missing. Bad certificate. So certificate issued by the certificate authority, it's receiving the bad certificate. That means expired. It may be an expired certificate or any other else. Next, unsupported certificate. So this is also related to, so all are related to the certificates. So bad certificate, unsupported certificate, and certificate revoked by the user, and the certificate expired using the expired certificates. So every certificate will be expired. So we have to renew each and every certificate before they get expired, just like our passport. So what are the fields involved in this certificate? The major fields in this certificate are the client's identity and the client's public key and the signature parameters for the client. So these are the important fields involved in the certificate. So for every user, the certificate authority, which is a trusted third party, will generate the certificates. And for the authentication purpose, this certificate will be exchanged. So while exchanging these certificates, we may get these alerts. So certificate expired or certificate unknown. So unknown certificate may be received. So these are the different alert protocols. The major thing is we are having two types of errors. One is warnings and fatal errors. So coming to this fatal errors, if the fatal error occurred, that means any one among these messages, alerts, automatically the connection between the client and server will be disconnected. Right? So hope you understood this one. So first of all, we have seen the SSL, secure socket layer, which is implemented by using the 4-layer protocol stack, that is SSL record protocol, handshake protocol, chain cipherspect, and alert protocol. In the SSL protocol, SSL record protocol, we are considering the application data, we are fragmenting, compression, applying the compression function, and generating the MAC, appending the MAC, and applying the encryption algorithm, and finally appending the SSL record header, and then we are processing into the upper layer protocols. So upper layer protocols, the handshake protocol will establish the sessions and it authenticates the server to client and client to server by using the different messages and parameters associated to those messages. And then the chain cipherspect protocol, which is used to move from the pending state to the current state. And then the alert protocol, which gives alerts while implementing this SSL, while processing this SSL. So we call it as SET, Secure Electronic Transaction. So this is one part of web security. So in the previous session we have seen one part of web security, that is SSL, that is Secure Socket Layer, and now we will see this Secure Electronic Transaction. Here the name itself indicates we have to protect the data in this electronic transaction. So main concept we have this electronic transaction is online shopping, right? Nowadays, so everyone purchases the goods from the online store, right? So in that case, the user will give the personal information as well as the financial information in the internet. Right? So we have to provide the security for this data which we are providing in the network. So that is the concept of secure electronic transaction. Now what are the services? The services of this set is, the first one, confidentiality. That means we have to provide the security, we have to protect the data of user data, right? User data. Either it may be the personal information or the payment information. The next one, integrity. This is the main thing. Integrity. That means we are sending our personal information and the payment information through the network, so that those data, that particular data should not be altered during the transmission. Data should not be altered. That is, no modification should be done after sending the information from the sender and before receiving by the receiver. Next, so as we know, in the online store, the two persons will be there. That is, one is card holder who purchased the product, and another one is a merchant who sells the product. So card holder, simply we can say user. Card holder authentication. Right? Similarly, merchant authentication. So we can say the services, we have to provide the three services: confidentiality, integrity, as well as authentication. And here the authentication is of two, that is, one is card holder authentication as well as the merchant authentication. So card holder authentication means whether the card holder is having a valid card, and merchant authentication is whether the merchant is able to accept the cards, able to accept these cards. So these are the services which we are providing by using this secure electronic transaction. Now, so who are the participants in order to implement this secure electronic transaction? Participants. Say participants. The first one is a card holder. So that means the user who will buy the product. Next, the merchant. So here also the person who sells the product. Issuer. Issuer is bank of cardholder. That means, for example, the payment is of using credit card. So the bank which gives the credit card to the cardholder is a issuer, right? Issuer means the bank which issues the credit card to the cardholder. Next, acquirer. The acquirer is a financial institution established to merchant. That means, or we can say, financial institution related to merchant. Okay, right. So acquirer, here there are different card holders, that means different users. So everyone will be having their own credit card from their own banks, right? So the acquirer is related to the merchant, the financial institution related to the merchant. So the merchant need not have an account with all the banks, because merchant must be able to accept every card, the card of any bank, right? So the merchant need not have to maintain the accounts from all the banks. So instead of maintaining the accounts from all the banks, the merchant will relate it to the acquirer. Acquirer is the financial institution which accept the payment from any bank account. Hope you understood. So here the financial institution is not a bank. This financial institution will accept the payments from the cardholder with that accepts the cards from any bank account. So instead of maintaining the merchant the account, all the accounts from various banks, this merchant will relate to the financial institution. Right. Next, payment gateway. So the payment gateway, who will do the payment process, right? So for example, for better understand, for example, we can say we had two payment gateways. So we can observe the payment gateway on our card. That is, we can say it is a MasterCard or a Visa card, right? So MasterCard or Visa card. These are two payment gateways, right? So next, certificate authority. Certificate authority. Certificate authority is a trusted third party who will give the certificates to all the cardholders as well as the merchants. So it's a trusted third party. Gives the certificates to all the cardholders and the merchants. So immediately when the cardholder opens an account to the bank, immediately the bank will issue the certificate to the cardholder. So what will be there in these certificates? So in these certificates there will be the cardholder name, as well as public key of the cardholder. Or we can say customer, the public key of the customer. So instead of getting the public key from the public key ring, instead of using the public key distribution, so here the certificates will be having the cardholder name and the public key of certificate, customer. So if the receiver wants the sender's public key, the sender will send only his own certificate to the receiver, so that the receiver will get the public key from the certificate. So this is also one type of authentication, achieving the authentication, right? So these are all the set participants. So one is cardholder, who will have the bank account and who will buy the product. Merchant, who will accept the financial payments and who will sell the product. Issuer, bank related to the cardholder, who will give the account to the customer or cardholder. Acquirer is a financial institution related to the merchant who accepts the payment from any bank. Next, payment gateway. So it is either a MasterCard or a Visa card. Certificate authority is a trusted third party who will issue the certificates which has the public key of the customer or the public key of the user to both the cardholder and merchant. So these are the set participants, right? So in order to achieve the integrity, the customer will create one dual signature. See, we'll see that. So in order to achieve the authentication and integrity, the customer will create the dual signature. So which will be verified by both the merchant and the payment bank. Right? So how to create this dual signature? So as we know, the signature, when we call it as a signature, if the data is encrypted by using sender's private key, we call it as a signature, right? Here we are calling it as a dual signature. So why? First, so whatever the information we are passing while buying the product is a payment information. See, so while user buy the product, the user will give some information to the merchant. So that information will be divided into two parts. One is payment information. The another one is order information. So as the name indicates, the payment information will be having all our financial details. That means a card number, CVV number, expiry date, the card name on the card, and everything will be in payment information. And order information. Here the order information means, so whatever the products we are going to buy, our cart, simply we can say our cart, the products of our cart. So the information will be divided into two parts. One is payment information and order information. So this payment information should be sent to the bank. So listen carefully, here the payment information should be given to the bank, and bank doesn't need this order information. Okay, so bank doesn't need what are the products we are buying, what are the products the user is buying, right? So the payment information will be sent to the bank, and this order information should be sent to the merchant. And the payment information should not be sent to the merchant. Only the order information will be sent to the merchant. But in both the merchant and bank, we have to verify the integrity. That means we have to verify the dual signature. That's why for the bank, the plain text of payment information and message digest of order information will be sent. Here, plain text of order information and message digest of payment information will be sent. Right? So the plain text, the payment information will be sent as a plain text. Here the order information will be sent as a plain text. Right? See, this is how we will create a dual signature. Let me explain with a simple diagram so that you will clearly understood. So finally, the information will be divided into two parts: payment information and order information. And the payment information will be sent to the bank, and order information will not be shared with the bank. Similarly, the order information will be sent to the merchant, and the payment information should not be shared with merchant. Right. See. Now, we will see the dual signature, generation of a dual signature. Right. So, this is the payment information. This is the order information. Right? So, payment information and order information. So, after having this payment and order informations, we have to apply the message digest algorithms or the hash algorithms in order to generate the hash code. Here the hash code is also called as message digest. So after applying this hash code, we will get PIMD, right? The hash code also known as the message digest. So I am calling it as payment information message digest. Similarly, here also we will apply the hash, right? So that we will get OIMD. So, which is an order information message digest. So again, we have to append these two. So we have to append these two, and then again apply the hash function. Again apply the hash function. Again apply the hash function, so that we will get the one more message digest. We call it as POMD, which is the payment order message digest, and this will be encrypted by using the private key of the customer. And this is encrypted by using the private key of the customer, so that we will get the POMD in an encrypted format. This POMD in encrypted format, right? So this we call it as dual signature. This we call it as a dual signature, right? So simple. The payment information, first the information will be divided into two parts. One is payment information and order information. So payment information means the complete payment information means the complete details of the payment, the financial details, and the order information is the complete details of our product's order. And applying the hash function to the payment information will give the message digest, PIMD, payment information message digest, and here also the hash applied to the order information will be given OIMD, order information message digest. So we have to append both and again apply the hash function, so that we will get POMD. So POMD is payment order message digest. So again the result will be encrypted by using private key of the customer. Here PRC. PRC is a private key of customer. Next, H is a hash algorithm. Here we will use SHA-1 algorithm. And encryption, here the encryption we will use the RSA encryption. encryption, we will use the RSA encryption. And PIMD is a Payment Information Message Digest. Similarly, OIMD, it is a Order Information Message Digest. Right? Similarly, POMD, which is a Payment Order Message Digest. Then, this is appending, the concatenation. So, this is the dual signature, and we have to send this dual signature to the merchant and the bank, so that the merchant will again decrypt this dual signature and verify this POMD. Similarly, the bank will decrypt this dual signature and compare the POMD. So here the merchant, we have to include this dual signature with our purchase request and also the payment request. So this dual signature will be received by both the bank and merchant. So in order to check the integrity and authentication, we have to decrypt this one. So in order to decrypt this dual signature, we require the public key of the customer, right? Here we are encrypting this dual signature by using private key of the customer. So in order to decrypt this dual signature, we require the public key of the customer. So how to get this public key? So previously I have said that sharing the certificates will give the public key of the customers. So along with this dual signature, the certificate will also be sent to the merchant and bank. So from the certificate, they will get the public key of the customer, they will decrypt this dual signature, and they will again generate the POMD at the bank and merchant itself, and the appended dual signature and the generated dual signature will be compared. So if those comparisons matches, that implies there is no modification during the transmission. The data is not altered during the transmission. And if the comparison mismatch, that implies there might be some alteration in the message, that means some modification in the message during the transmission. So in order to execute or implement this set, the customer should generate the dual signature. Based upon the dual signature, we will achieve the authentication and integrity. So hope you understood this dual signature. So we will stop here. So in the next class, we will see the purchase request, the purchase payment authorization, and the capture request, payment capture. Right? So these three are the events should be done. These three are the transactions to be done while implementing this secure electronic transaction. So purchase request, payment authorization, and the payment capture. We have seen the generation of dual signature, right? So this dual signature is mainly used for the authentication and the integrity of both the merchant and at the bank side, right? So this dual signature will be generated by the customer. So the information will be divided into two parts. One is the payment information and the order information. So by applying the hash on payment information, we will get the payment information message digest. And by applying the hash on order information, we will get the order information message digest. We will append these two message digest, and again we will apply the hash so that we will get the payment order message digest. And that particular POMD will be encrypted by using the customer's private key, so it gives the dual signature. And this dual signature will be appended with the information and purchase request, and it will be sent to the merchant as well as the payment information, and it will send to the bank, so that the bank and the merchant will again generate the POMD and it decrypts the dual signature and will be compared. So by this we can achieve the integrity and authentication. So in order to decrypt the dual signature, in the encryption we are using the private key of customer. So obviously if we want to decrypt this dual signature, we require the public key of the customer. So for that public key, the customer will send their certificates along with the purchase request. Let us see. The customer, merchant, and the bank. So we can say bank or a financial institution, right? So let us write it, don't get confused. We can write here the financial institution. The financial institution. So customer will generate the dual signature, right? So this dual signature means POMD, which is encrypted by using private key of the customer. So in order to decrypt, so here the merchant must decrypt this POMD by using, so this POMD must be decrypted. So this is encrypted format. So this encrypted format of POMD must be decrypted by using public key of customer. Similarly, here also this POMD of the decrypted must be decrypted by using public key of the customer, right? So this dual signature will be sent to here as well as here, right? So dual signature, right? So in order to get this public key, the customer will send the certificate. Similarly, sends the certificate to the financial institute also, where we can get the public key, right? Public key of customer, where we can get the public key of customer. So, and the customer will send the payment information, right? So in order to compare this POMD, here the merchant should also generate the POMD, right? So here also the financial institution also generates the POMD. So for this POMD, the merchant requires the PAMD and OAMD. So the merchant doesn't want the payment information, so directly the customer will send PAMD and the order information, right? So this will be sent by the customer. Similarly, here in the financial institution, so financial institution doesn't require the order information. So here the payment information will be sent as a plain text and directly OIMD will be sent by the customer. Directly that will be sent by the customer, right? So the merchant will apply the hash on OI so that it will get the OIMD. It will be appended with PAMD, and again, so this POMD is decrypted and these two will be compared. Similarly, here also the payment information. So here for the merchant, order information will be in a plain text and payment information message digest will be sent. So here the payment information is not a plain text, only the message digest. Here also in the financial institution, payment information will be in the plain text, order information message digest will be sent. So here the order information is not sent as a plain text. So from this the POMD will be calculated here, here the POMD will be calculated and those two will be compared, right? See, to implement this secure electronic transaction, the three events should be generated, or we can say three transactions must be done. Three transactions. One is purchase request. So this is actually done by the customer and this request will be sent to the merchant. So this is from customer to merchant. So here we can call it as a customer or a card holder, right? Next, second one, payment authorization. The payment authorization will be done by the financial institution. By financial institution. And the third one is payment capture. So this is a request from the merchant to send the payment to the particular bank. I mean, through the merchant's bank account. By the merchant. This payment capture is a request. We can call it as a request by the merchant to the acquirer. Right? So in order to get the amount. So these are the three transactions should be implemented in this secure electronic transaction. So let us see one by one the purchase request. So what actually done in this purchase request? So this purchase request is from customer, generates the customer, sent by the customer to the merchant. So here the payment information which is in a plain text plus order information message digest, OIMD, payment information and order information. Once again, we will write here. So payment information plus OIMD, order information message digest. The order information message digest as well as the dual signature. The dual signature. Right? So payment information plus order information message digest and the dual signature, and all these three will be encrypted, right? So encrypted by using the secret key. The secret key, it's a conventional encryption by using the secret key, which is again encrypted. This secret key is again encrypted by using public key of the bank. Public key of the bank. So carefully. So first these three informations will be encrypted by using the secret key, and this secret key will again encrypted by using the public key of bank. Right? The output of this one is, see, this is the output of these three, right? Okay. Now, so this encryption, we call it as a digital envelope. Here plus digital envelope. So the digital envelope is the encrypted format of this particular secret key, and this secret key is used for decrypting this information, and this information consists of the plain text of payment information, order information message digest, as well as the dual signature. And along with this digital envelope, we have to send the PIMD, the Payment Information Message Digest, right? So the Payment Information Message Digest and the order information in a plain text plus the dual signature, plus the certificate of user. So this is a dual signature, right? See, this is the purchase request sent from the customer to the merchant. See, so this is the information received by the merchant. So merchant doesn't know the secret key, so this part will not be decrypted by the merchant. So if this part should be decrypted, the merchant should know the secret key, because this part is encrypted by using secret key. So to decrypt this part, the merchant should have the secret key, and that secret key is encrypted. The secret key is in digital envelope, and this is encrypted by using bank's private key. Bank's public key. So in order to decrypt this part for the secret key, the merchant should have the private key of the bank. So only the bank can decrypt this digital envelope, so that the bank only can get the secret key. So only the bank can decrypt this information, right? And this will be accessed by the merchant. So PIMD, order information, dual signature and the certificate. Now, what is actually done by the customer? So first the customer will apply the hash on this one. So the customer will get OIMD. The merchant will get OIMD, order information message digest. And again, it will be appended with this PIMD, which is sent by the customer, right? So this PIMD is not an payment information plain text. It's a message digest from the payment information. Message digest of the payment information. So which is appended, and again apply the hash, so that we will get POMD, payment order message digest. Now this is a dual signature. As we know, this dual signature was generated by the customer, and this POMD is encrypted by using the public key of the customer. The private key of the customer. So in order to decrypt this dual signature, the merchant requires the public key of the customer. So the public key will be available in, this must be decrypted by using public key. So the public key will be available here in the certificate. So PUC, public key of the customer, is by using the public key of customer, this dual signature will be decrypted, so that the POMD will be generated. So this and this, the appended and the generated will be compared. So if this comparison success, that means if these two POMDs are equal, that implies there is no modification done during the transmission. So we have achieved the integrity and the signature and authentication. So by passing the certificates, we just achieved the authentication itself. Right? Here we are using some encryption and decryption, so we achieved the confidentiality, so that the merchant cannot see the payment information directly, and at the same time the bank cannot see the order information directly. So instead of sending the payment information, we are sending just a PIMD. And so this is the actually purchase request, the first step, the purchase request. The payment information in the plain text, order information message digest, and the dual signature. All these three will be encrypted by using one secret key. It's a conventional encryption. So the same secret key should be used at the decryption also. So this secret key is again encrypted by using the bank's public key. So that we call it as a digital envelope. So here the digital envelope is the encrypted form of secret key by using bank's public key. So as we are using here the bank's public key, only the bank private key only, the bank can only decrypt by using the bank's private key. So private key is not shared by anyone, so the bank only can decrypt this digital envelope, so that the bank only can get the secret key. So the bank only can decrypt this message. And along with these two, we are sending, the customer is sending PIMD and the order information in plain text. So merchant should know the order. So the order information will be sent in a plain text. At the same time, dual signature and the certificate. And this certificate is for public key of customer. So PIMD and order, apply the hash, the same hash, SHA-1 algorithm to the order information. Will get the POIMD. So OIMD. Both will be appended. Again, the hash algorithm will be applied. So POIMD will be decrypted. Generated. So from the dual signature, by using the public key, it will be decrypted, so that POIMD will be decrypted, so that decrypted POIMD and the generated POIMD will be get compared at the merchant side. So this is the purchase request. Next, payment authorization. This is done by the customer to merchant. Now, the second step is payment authorization. So here the payment authorization means how the financial institution or how the bank can decrypt this one, and how the bank can achieve the integrity, right? So this part, the complete this part will be directly sent to the bank by merchant. Right? So this part will be ended here. So this will not be sent to the customer, merchant. So this part will not be sent to the bank. Only these two parts will be sent to the bank by the merchant. So at the bank, first this digital envelope will be decrypted by using bank's private key, bank private key, as it was encrypted by using bank's public key, private key will be having. Now we will get the KS, which is again decrypted here by using KS, so that we will get the payment information, at the same time OIMD, at the same time the dual signature. This is the dual signature, right? Dual signature. Now, again, the bank will apply the hash on this one, so that PIMD will be generated. PIMD will be generated, and this will be appended here. Apply the hash, so that POMD will be generated, right? Now this DS will be decrypted by using public key of the customer, right? So public key of the customer, and so that we will get POMD. So these two will be compared. These two will be get compared. So along with this, the certificate also will be sent. So here we have to send the certificate. The certificate will all be sent. From this certificate, we will get the public key. So by using this public key of the customer, POMD will be decrypted, and this decrypted POMD and the generated POMD will be get compared. So this is the process done at the bank side, right? So this is the process actually done at the bank. This is the process done at the merchant. This is the process done at the bank. So this is the payment authorization. So this digital envelope, first it is decrypted by using the private key, bank private key, as it is encrypted by using bank's public key. So that a secret key will be decrypted, and by using this secret key, this part will be decrypted. So payment information in plain text, OAMD and digital signature. These three will be, dual signature. These three will be getting along with the certificate. And again, applying the hash on payment information, we will get the PAMD. This OAMD will be appended with this PAMD, and again hash will be applied so that we will get the POMD. And from this certificate, the bank will have the public key of customer, which is used to decrypt this dual signature so that POMD will be accessed. So this POMD and the generated POMD will be compared. If both matches, that means the payment information is also not altered during the transmission. So like this, both the merchant and the bank will authorize the data. Will integrates the data. And the third one is, so after completion of all these things, the third step, that is payment capture. So after successful completion of these two steps, the third step means the merchant will send the valid transaction ID along with the request to the acquirer, so that the acquirer will check it and the acquirer will debit the amount from the card holder and it will be credited to the merchant. So that is called the payment capture, the third thing, right? So the third thing, after successful completion of these things, the merchant will send the request payment, the purchase request ID and the transaction ID to the acquirer, so that the acquirer will check everything and the acquirer will debit the amount from the customer account and it will be credited to the merchant's account. So as I have said, the acquirer is a financial institution related to the merchant, so it will accept every transaction which is coming from any bank itself. So the merchant need not have an account with all the banks, right? The merchant can have only one bank account, so that the acquirer job is to accept the payment from any bank and it will be credited to the merchant's account. So this is a simple concept. This is a very simple and a very interesting concept of secure electronic transaction. So this is one topic of web security. So hope you understood this simple thing. If you really understood my videos, like my videos, and if you are having any doubts regarding this network security concepts, feel free to post your doubts in the comment section so that I will definitely try to clarify all your doubts. And share my videos with your friends, and don't forget to subscribe to our channel. Thanks for listening. Thank you very much.